simulations, but we use that across the board. Can use idealized simulation to learn from data. We can use complex models. All of it is totally fine. So in this case, we're going to learn an equation just for the lateral part of momentum fluxes. So the idea, input data, we're going to use an algorithm that is actually quite simple. It's almost like sparse regression. You give the algorithm a set of basis function, and it's going to prune from that set of basis function and learn an equation from data that represent the lateral momentum fluxes. That's what it comes up with. This kind of course, it's after we did some massaging of the equations and so on, right? So you end up with a stress tensor that is symmetric, and that depends on the rate of strain and stretch of the velocity fluxes. There is a parameter in front of it that depends on the resolution to some extent. So now you have something that is relatively simple, depends basically on derivatives of velocities, to first order, right? So technically very easy to implement in a climate model, but doesn't look like negative viscosity, by the way. It has some ingredients of it, but it's not just negative viscosity. So the advantage is it's an equation, so technically, and again, I say in principle, it's easy to put into a model, right? It conserves energy and momentum, it's interpretable, so we could do some GFD on it, and that was a lot of fun. It reduced some of the biases in the North Atlantic, and that's the plot you see here. So when we put the parameterization in OM4, that's the response of the model. So where the Gulf Stream was too warm, now it's colder. Okay, so it reduced the bias compared to the observations. And the North Atlantic that was too cold, now it actually gets warmer. So when you sum those two up, the bias is going to be reduced in the North Atlantic. So all of that sounds great. And by the way, that's what the negative viscosity parameterizations are doing as well. Just want to make it clear. So that's for the good news. There is information in the data that tells us that there is more than just the negative viscosity overall, and that there is some physics that is hidden in the data, and that we can use that as a parameterization. Bad news, numerical stability. Okay, it's actually very hard to constrain because you re-inject energy in different scales, and there is very little constraint on it. So sometimes you build up entropy, which make the model numerically unstable. So we had to put some filters to make sure that the model does not basically become too noisy. It's very numerics and model configuration dependent, and we haven't quite figured that one out yet. So we get different responses depending on the dynamics of the model. And we believe that's why we actually see a deterioration of the Southern Ocean, both because the dynamic is different than the North Atlantic, and also probably because we haven't done anything about the buoyancy force incoming from the mesoscale. So again, Drew and Kelsey will talk about the buoyancy aspect of it. So again, there is some good, right? So you can learn something from data if you have good data, right? So you learn a new parameterization. In this case, it worked out quite well for parts of the implementation, but not for all of it. But again, still, that's something we wanted to do, and some things we did not expect, and we still have some, more work to do. But nonetheless, you can learn an equation for subgrid physics directly from data. Okay, so those I'm going to go a little fast. Mostly because there's still work in progress. I mean, everything is work in progress. You can see the disclaimer at the bottom, right? Simulation are in development, not, optimized. Nothing is published, by the way. Everything is actually being done as we speak. So again, there is no tuning, no optimization. We are actually developing things. So I want to show you again the good and the bad. Now you could say there might be more, right, than that simple equation for the lateral momentum fluxes. If we were giving it more degrees of freedom, and use a neural network that has more parameters and more flexibility. So in this case, the idea is the same. Use data, extract the information of the subgrid forcing, learn it. And here it's being learned with neural networks. So again, more degrees of freedom. And with a constraint, with some physics constraint. And the physics constraint does not come by adding something to the loss function or anything like this. It comes by the way we do the normalization of the input and output, trying to make it more faithful to the physics of the problem. The same way you use Reynolds number, right, to non-dimensionalize the fluid equation, or the deformation radius to try to understand different scale. So that's kind of the same idea. It's the way the normalization is being done that is different. And again, you're going to hear more tomorrow about this. So now a new lateral parameterization coming out of the neural network. The results are actually very similar to the equation discovered, but not quite. So we see a similar behavior, but not with the same amplitude. So it captures some of the equation discovery, but not exactly everything. So now the big question is, what is it in this, higher, kind of larger number of parameters that we have that we didn't have in the equation itself? So what is the physics that the equation missed that the neural network that has more degrees of freedom has learned? And so that's where the challenges comes about, right? How do you extract information from something that is very, convoluted, so to speak? So the final one is more of a technical one, but I wanted to mention it, especially since Gustavo is in the room, and that's work that is also being done at NCAR, which is what if you take a very large type neural network, now suddenly you're actually faced with a lot of challenges to plug it into a real climate model. And so there are tools to do that. So again, that the work that I'm showing here is one done, is one done at GFDL, but Gustavo was part of a study that used the same tools called SmartSim. And I think Andrew Shao is talking at some point, right? Yeah. Oh, yeah, yes. So we'll talk more about SmartSim, but now this kind of ideas is kind of finding the right tool for which you can actually implement complex, neural network into a real climate model without, a massive computational cost. So here it's only a 1-year run in OM4, but again, there are long runs where you can actually take those tools and implement them into climate model. Of course, how you do that is a whole different story, but it's not because we're talking about big data and, need for GPUs that it's the end of climate models as we know it, right? We just need to adapt to the new technologies and how to do it. And all of that is doable, but definitely requires a lot of work in the back end. Okay, so I want to finish by very quickly just mentioning a few other things. So that's all the parameterizations I told you about and that you're going to hear on the ocean side. We do have, machine learning parameterization for the atmosphere as well. Most of the work is being done at NCAR, actually within CAM. So different type of neural network. So for moist convection and boundary layer. We also have CI heterogeneity by Lorenzo, who's not going to talk about that here, but you can talk to him about this. This is work of Marika Holland as well. And we have also corrections learned from data assimilation. So a different way to do parameterizations, actually. And so Will Chapman, who is here, actually has been doing some of that work for the atmosphere. So different ways to extract information from data to improve climate model, at least the subgrid part of climate model. Now, of course, the goal is, at the end of the day, is to make climate models better, right? And that's what I told you in that original slide. We're going to learn subgrid forcing from data. We're going to implement that in climate models and hopefully have better physics. Now, it's a one shot, right? You know that we need ensembles in general. We need to run a lot of those simulations, and we want to be able to do that in a cheap way. So can we machine learn those new, better, improved simulation with machine learning? So now you can run that at basically at least an order of magnitude faster than you would the regular simulation. And so our goal is to try to create surrogates of climate models, okay? And now we're not talking about forecast or for a few years, we're talking about decades-long simulations of climate models, okay? And so you can think about them for many things. You can run ensembles to learn extremes, you can do uncertainty quantification, you can replace the model that you begin with for data simulations, you can spin up component models, and so on and so forth. So now you won't even need to be a climate modeler to actually run a climate model, which I know sounds horrifying. We still need the model to begin with, right? So I want to make clear, this is not a full replacement of the model. It's just when you start with the model, after that you get the data and you actually can build a surrogate for that simulation, okay? So you still need the modeling centers, you still need the model of people who know what they're doing, but then after that, you can do that many, many times and very cheaply. Okay, so here's something brand new. We're actually trying to submit it in the next few days. So everything I say might change within the next 48 hours. So right now, it's data from, again, OM4, GFDL, forced round with GRA. We are using data which is coarse-grained to 1 degree, 5 days averages. It's mapped onto 19 vertical layers. Again, it's all done conservatively. And the model, what the machine learning model is trying to do is learning from input from sea surface height, velocities, temperature, salinity, at a given time step and the previous time step, and learning the next 2 time steps, okay? And again, time step is 5 days averages here. So it's trained on that data. It's forced by the same forcing that the OM4 simulation is having. And we train on basically, I can see from there, so 1958 to 2012. So that's the data we give the machine learning model to learn what would replace, if you want, the numerical simulator that you have. So it's machine learning just from the data. It knows nothing about the PDEs. It just knows the input-output. You can see that the machine learning model is gigantic. It's 135 million parameters, right, to learn the dynamics of the ocean, if you want. Now, when you have this new matrix, if you want, this new gigantic model, that's it. That's your forward model. And the question is, does it do as well as OM4? So you want to test that on data that you didn't touch. And so that's what I'm going to show now. So we keep 8 years of data that the machine learning has never seen, and we plot it against it. So the left column is OM4. It's a temperature cross-section. Top is Drake profile, is Drake Passage. Bottom is a section in the Atlantic. It's as a function of latitude. So you can see the depth structure, right? You can see the balls of the gyres and so on. And the middle plots are what's coming out of the prediction of the emulator. So you can see the broad structure of what you would expect, right? It does a pretty decent job. If you calculate the correlation, it does relatively well on the climatology. So we can actually reproduce the structure of temperature without, again, the emulator has never seen that data, to be clear, right? It's just a box that has learned from different type of data and now can actually move forward in time the same way a numerical climate model would do. And it reproduces basically what you would expect. The PDF on the side is to show you that actually gets the full distribution of temperature and salinity. You would get the same if you were looking at other variables. So it does really well at capturing all the type of values you would get in a numerical simulation. And so this is a time series of ENSO Niño 3.4. So the red is the prediction, the black is the original OM4. Again, does a decent job, right? I mean, there are some, you can't expect it to be perfect. You've seen the amount of data we give it. It's a lot less than you would expect. And does a good job if you look at the structure. Again, for Niño and La Niña conditions, we get the right structure of Kelvin and Rossby waves. We get the right magnitude, roughly. We get the right timescales. So it does a pretty good job, again, at capturing the time evolution over time. Now, the grand challenge is, does it work if you were doing multi-decadal simulation, right? And anything is possible. The good news is it does. So like every ocean model, even though it's a machine learned one, it'll adjust just to a new type of forcing. So here we do a repeat year. We give it a year at the start. It's going to do its own adjustment in the interior, and then slowly basically kind of settle on its own steady state after multiple decades. So we now have a new version of OM4 that is completely learned from data, that runs 40 times faster than the original OM4 on one GPU. And again, unoptimized. So you can see the potential, right? So if you start with a great model, but then you want to run many of them, many emulations of them, now you have the possibility to do it with one GPU. Okay, so I have 2 minutes left, so that's perfect. That's my last slide, just to give you a little flavor of where we're at. We started coupled runs. So again, this is, Mitch Bushak at GFDL is been kind of spearheading this. We're going to implement the backscatter equation discovery, and there is already the EPBL backscatter. And this is a plot of a coupled run right now at 1 degree spear, showing again an improvement in the biases, but some places there is no improvement. Again, the models are not Chuno optimized, but again, talk to Akash if you're interested in it. We had some great discussions with Dave Lawrence about the new version of CSM, machine learning enhanced. And so the hope is that several of our parameterization will make their way towards CSM. It can be tested in a different coupled climate model. We're using a lot of those parameterization also for data assimilation and creating a new product of heat, carbon, and oxygen uptake. So this is a project led by Ralph Killing. So the idea will be to, again, replace the original model with emulators, but also includes some of our parameterization into that. And the final one is we're actually trying to build a coupled climate emulator of CM4. So this is work with the Allen Institute, Chris Bretherton, and GFDL, obviously, and NVIDIA. So now not just the ocean component, but the full coupled simulation. AI2 has an atmospheric component already. All right, that's it. So hopefully I give you a flavor. I told you it's like drinking from a fire hose I show you a lot of examples, mostly so to generate discussions and so you can talk to people who are actually doing the work. But the philosophy has been trying to learn from data because there is a lot of information. There's a lot of physics in it, and that's kind of a good way to shake things up and try to build low-order models that represent, again, the impact of the small scale onto the large scale and improve our climate simulation. We try to embed physics as much as possible, and that can mean many things, right? I show you different examples, but there are many others, and I think at the end of the day, we want models that have good physics in them, not that have just a good skill, and I think that's important to remember. And we try to develop everything across the model hierarchy, right? I think we want something that is robust and lasts a long time. So thank you very much for having me again. All the credit has been a lot. Thanks.
Thank you so much. We have time. Questions, starting from early career first. Oh, I see you. Next. Greg?
I think a lot of the show the source of the data was a model. Is that a goal that you have? Is that a goal that you have, or is that is it not feasible now, or is it are you actively working on it?
Yeah, thanks for that. That's a great question. Definitely. Everything that I show, most of what I show come from data. I think the one example that we have that is observation-based is Lorenzo on the sea ice, and some of our data simulation product that combines model and data. So my dream was to do it from observations directly. There's just not enough observations, or the quality is not good enough for the bigger parameterization. Now, what we've been trying to do, and we've started already, is to learn from data and then calibrate with additional observations. And that works a lot better, actually, because you let your model learn from a lot of data because it's easier to converge, and then you calibrate with obs. But I agree, I think observation has to be part of it, but it's still a challenge, yeah.
So my question was very similar to that. If when you say you apply equation discovery, if you apply it to real data or model output.
Yeah, it's all model output for real data, right? So the best data that we had, if we wanted something global, is altimetry. But actually altimetry, as we all know, right, it's a path every 11 days, and actually the effective resolution is much larger than the resolution that we need to capture the effect of subgrid. It's wonderful, don't get me wrong, but doesn't have the enough flux information that doesn't rely on the optimization.
Thank you.
Okay, last question from Paul.
Hi, thanks for the great talk. It was really understandable. Sea surface salinity restoring, like in ocean models, is there any way that, is anyone tackling that with machine learning, how to turn this off? Or is it like, how do are we going to have this forever? Or is it just...
Okay, I'm very biased. No, we should not. So we should not have salinity restoring forever. So I think one of the ideas is, can you replace the atmospheric boundary forcing, if you want, with an emulator, right? That was one of Alistair's original idea, which we're still going to do, by the way, as we couple the model. And that will be one way for us to actually move away from that, to learn the fluxes. Yeah, so no, that's a goal. No more restoring of salinity.
All right, let's take our speaker one more time. So much. And our next speaker is Greg Wagner from the Massachusetts Institute of Technology, and he'll talk about opportunities and pitfalls in automated calibration.
Trying to understand this, how the pointer works here. How does this work? Okay. Interesting. Okay. Trying to go back to the previous slide, but I can't. Okay, there we go. Okay, so I'm Greg Wagner. I'm a research scientist at MIT. And I'm working with the Climate Modeling Alliance to build a new climate model that can be automatically calibrated and that has quantified uncertainty. And so what I'd like to talk about today is the benefits of automated calibration and also the pitfalls and how we overcome them. So first, I'd just like to explain what I mean by automated calibration. So Laura already gave an excellent introduction to parameterizations. I think everybody sort of understands what these are, but in short, all ocean and climate models have parameterizations to represent either unresolved or irreducible processes. And these parameterizations are associated with free parameters that have to be determined from data. So an automated calibration technique is a way to find those parameters using a computational method to minimize some sorts of error. So that's in contrast to hand tuning the parameters. And all climate models use some combination of automated calibration and hand tuning, essentially. But I don't think any climate models are solely based on automated calibration right now. So the benefit of using automated calibration, there's three main benefits. One is that it's repeatable. So you press a button and you calibrate. This greatly accelerates the process of parameterization development, especially if the calibration is relatively cheap, because you can find the answer for your parameters, deduce what the errors in your parameterization are, try to improve it, and repeat. Another benefit is that the error that you minimize can be formulated much more flexibly. So in particular, you can account for much more data when you're computing the error than you could if you were using hand tuning, which requires a person to assess each source of error. And then we can include uncertainty quantification as an additional step, which I'll mention a little bit in the talk, but that's not the main point. Okay, so to illustrate the process of automated calibration of parameterizations, oh, there was a movie, but still, you won't get to enjoy it, I'm sorry. Yeah. Okay, this one we got. Okay, so to illustrate automated calibration, I'm going to present an example of automatically calibrating a boundary layer turbulence parameterization. So not a whole model, but rather a subcomponent of the model. And in this context, when we calibrate a boundary layer turbulence parameterization, my source of truth is, as in the previous talk, it's going to be a high fidelity model, so a three-dimensional large eddy simulation. And the parameterization is embedded in a one-dimensional single column model. Okay, so that's what I'm illustrating here with the red box. And yeah, so the error that I'm going to use is going to be the difference between the horizontal average of the large eddy simulation and the prediction of this one-dimensional single column model with the parameterization embedded inside it. And so, okay, yeah, ooh, it's not pretty. I used Keynote and had to convert it to PowerPoint, but anyways, the equations don't really matter, so don't worry about that. Yeah, it's just okay. There's a couple things that matter. So the parameterization I'm going to calibrate, it's a traditional parameterization that is not it's based on theory, not machine learning. It's an eddy diffusivity parameterization. So we have a eddy diffusivity that is the product of a mixing length, the curly L, and the square root of a turbulent kinetic energy. So the most important thing here to note is that we have a prognostic turbulent kinetic energy variable, and that's going to become important when we understand what the opportunities and pitfalls are when we in the process of calibrating this this parameterization, which is called cat key. Okay. Okay, so the way that we calibrate cat key is we use this method called ensemble common inversion. So this is a gradient-free method. So some methods for automated calibration, you need gradients of your model with respect to the parameters. Typically, you don't have that. There's other methods like ensemble common inversion that don't require gradients. So with ensemble common inversion, we are iteratively improving an ensemble of models. So it's illustrated by this. This is not cat key, but this is an illustration of calibrating a two-parameter parameterization. Cat key has like 20 parameters. And so what happens is so the way you do this is you initialize an ensemble of models, all with different values of the parameter, and then different parameter values. And then you use the error estimate from each of those ensemble members to compute an update to all the parameters. And through this process of iteration, the parameters converge to some optimal value, hopefully. Of course, it doesn't always succeed, but the hope is that, when you add enough data, eventually you're going to be able to find unique, reproducible solutions. In this case, we're going to use, so we have 35 large eddy simulations in total. We'll use 21 for calibration and 14 for testing. And then in addition to that, we're going to, in our error estimate, we're going to use evaluations of the single column model at 3 different resolutions. So that means that in total, we actually have 63 estimates, 63 independent simulations that form our estimate for each ensemble member. Okay, so opportunity 1 realized when we're using automated calibration for this problem is that cat key exhibits, it's more accurate than other parameterizations. So this is showing 3 examples. 2 of them are out of sample, 1 is in sample from 3 different cases. Comparing it to KPP and the second moment closure. I should have mentioned the large eddy simulations have surface waves, so that's why we compare to this Langmuir turbulence second moment closure. And in particular, usually they're actually predicting that the boundary layer depth is too shallow, and cat key fixes that. Now, of course, the simulation, the data that I'm using to do this test is quite similar, even though there are some cases that are out of sample, like they have more extreme forcing or weaker forcing than we use for calibration. It's still similar to the large eddy simulations that were used for calibration. And in particular, the SMC, the second moment closure and KBP, they were both calibrated in a different way. So we can't really tell, and this is one of the reasons why we need to use automated calibration. We can't tell whether the other parameterizations are doing poorly because they weren't calibrated in the same way, which would be kind of uninteresting. We just need to choose better parameters or different parameters, and we'll get this. We'll get a better answer, or because of the structure of the parameterization, which is the thing that we really care about. So we can't tell the difference when we calibrate parameterizations differently. We can't tell why they're different from one another. And so that's one of the reasons why we need to use automated calibration, so that we can make informed decisions about which parts of parameterizations are better or worse than another. Okay, opportunity number 2. So we were able to, this is sort of not in the way that you would hope to do in a climate modeling scenario, but still it's useful for boundary layer parameterization. We were able to incorporate interesting sources of error into the calibration. So in particular, we incorporated error from, as I said, we used 8 meter, 4 meter, and 2 meter resolution in the calibration. And now here I'm showing you a test of cat key at 1 meter resolution and 16 meter resolution. You see that it's relatively insensitive to resolution, which is it's the outcome of being able to use more error during automated calibration. So being able to use more error can be a significant advantage in realizing interesting properties of your model, like resolution independence. Okay, and opportunity number 3 is that I'm going to argue that because we had automated calibration available from the start to finish of the development of cat key, we were actually able to develop it much more quickly and in a much more informed sense. So this is showing you a comparison between 3 versions of cat key that were all calibrated in the same way. And interestingly, you'll see that, so the minimalist version has the least physics and the fewest parameters, and then progressing to the right, we get until the final version of cat key, which is called a favorite version. And the improvements that we see are actually a decrease in the dependence on resolution. And so it would have been hard to, basically we're able to observe this structural error because we have automated calibration, and that allows us to accelerate the process of parameterization development. Okay, but now let's get to the problems, or it's kind of a straw man argument here, but the quote unquote problems are a pitfall of automated calibration, which is mentioned. There's this paper by Horton 2017, Art and Science of Tuning Climate Models, and they mention automated calibration, and they say one of the reasons we don't do it is because there's a serious risk of developing compensating errors. In other words, when you calibrate to data automatically, you might get the right answer for the wrong reasons. And in calibrating cat key, you could actually interpret cat key's accuracy in that way, because, so here I'm showing you a plot of, from one case of buoyancy and the turbulent kinetic energy. And what you see is that cat key is actually making, okay, and I'm comparing it to a K epsilon. So cat key is making a much better prediction of the boundary layer structure, boundary layer depth, based on buoyancy. But when you look at the turbulent kinetic energy and compare that to the LES, it's making a far worse prediction of turbulent kinetic energy. And that may not be an accident, because the way that the parameters in K epsilon are determined actually is by making arguments about the behavior of turbulent kinetic energy in certain idealized situations. So although it's not calibrated automatically, you could argue that K epsilon, in a way, its parameters are chosen to, they prioritize accurately predicting turbulent kinetic energy. But it turns out that when you prioritize that, you may actually deprioritize calculating boundary layer depth. And I didn't say this explicitly, but we don't use the turbulent kinetic energy error to calibrate CATKey either. So in this case, we believe we have the flexibility. The way we solve this problem, which is a quote unquote compensating error, is to reinterpret what the TKE variable means. So rather than, while K epsilon is interpreting TKE as being the physical turbulent kinetic energy, and therefore it's a real error, we interpret the TK in CATKey as a latent variable that can't be observed. It's a mixing kinetic energy, and as a result, its errors are acceptable. And we're willing to get TK wrong if it means that we can get boundary layer depth correct. Okay, so that's one way to solve compensating error, is to sort of just pretend it doesn't exist, or reformulate how you interpret the variables in your model so that it's not an error. Yeah, which is, I think this is a legitimate method, right? Because ultimately, when you're making climate model predictions, you might be interested in only a small number of metrics, right? And so other things that you're getting wrong, you may be able to accept that. Okay, so now let's look at some more serious issues where that method is not available to you. So now these are thought experiments. We haven't done these. So thought experiment number 1 is if we calibrate CATKey together with a surface flux parameterization in order to predict, say, sea surface temperature. Now, when we would do that, because both the mixing coming up from the interior and the air-sea flux coming down are both contributing to what the sea surface temperature is, you might imagine that we can compensate for errors in one or the other. You would develop compensating errors, because errors in CATKey could then be compensated for by developing errors in the surface flux parameterization, and there's no way to tell the difference between the two if we only have the limited data of sea surface temperature. So that's kind of the classic case of compensating error, where you just don't have enough data. And so the solution to that is simply adding more data. So in this case, for example, if we add data on mixed layer depth and sea surface temperature, then we can't get mixed layer depth wrong in order to get sea surface temperature correct. And that just simply solves the compensating error part. And that's an important method for reducing compensating errors, just incorporating as much data as possible, because then you'll explicitly ensure that compensating error is minimized too. Okay, and then my last example, or the second thought experiment, is if we calibrate a boundary layer turbulence parameterization in a scenario where we have missing physics like submesoscale restratification. So submesoscale restratification is a very small scale process that could require a model as fine as 2 kilometer with 2 kilometer resolution, which is something we may not have. And it's going to, submesoscale restratification is going to make the boundary layer depth shallower. And so if we're trying to calibrate in the context of a coarser model where we don't have this physics, then you would easily, what CATKey is going to do is it's just going to undermix in order to get the boundary layer depth correct, because we're missing the physics that's actually trying to cause that. And in this case, there's no way to add more data to fix the problem. One of the ways to solve it is actually to capture submesoscale restratification with a parameterization. But if we can't do that, there's another solution, which is to use uncertainty quantification. So all the examples I showed you, we calibrate CATKey against large eddy simulations. So we have generated tons and tons of samples of CATKey being evaluated. That's what's being illustrated in the bottom right. And so we can analyze all of that data and develop a priori bounds on the range at which CATKey parameters can take and still be physically plausible parameter values. So if we use uncertainty quantification systematically, constrain CATKey's free parameters, then we'll prevent it from being able to do unphysical things to compensate for missing submesoscale restratification. Okay, so here's my summary slide, and thank you.
Right, we have time for a few questions. Sorry for yours. Goodbye. Can you get this?
Thank you. Very nice talk. When you're talking about increasing cat key parameters, are those different from your model parameters? And I guess a related question is, so the eddy diffusivity model is pretty simple. Did you try it with other model forms like a second moment closure or anything else, I guess?
No, I mean, yeah, so like one clear thing that we would like to do is calibrate K epsilon to see what happens, see if the difference, the error we're seeing here is something that can be resolved simply by choosing different parameter values for K epsilon, or if there's actually a structural difference between cat key and K epsilon that would lead to more error in one or the other. So that's like a clear avenue for future work. It wasn't possible. It wasn't possible until recently because now we have K epsilon in our own model, so we can do it. I think your question about the parameter, these are the free parameters in cat key. I think, if that's answering your question. No, the model form, these are different models. Yeah, the minimalist one is a simplification, dramatic simplification of cat key, which only has, so, simpler model means fewer parameters, basically.
Can you introduce yourself also?
Oh, hi, my name is Jessie. Jessie Liu.
Hi, Akash. Nice talk. I was curious about the challenge of tuning both tracer and TKE. Was it challenging because they depend on each other? And so you decided that we should go for tracers instead of the TKE?
No, it just turns out that when you try to minimize the error, if you include error from the turbulent kinetic energy, you typically make worse predictions for momentum and tracers. So basically we've decided that there's a physical reason for that. In the large eddy simulation, there's elements of the turbulent kinetic energy that are not associated with mixing. For example, internal waves at the base of the boundary layer. So solving the problem is simply saying, why don't we just interpret this as a latent variable that we can observe, which could, you might want to revisit that in the future if you did want to use the turbulent kinetic energy for some other parameterization. But at the moment, we only care about the boundary layer depth. So we were able to do that.
We have less than 1 minute left. One last question has to be quick while Andrew gets ready. Nope. Oh, okay, Dan. Please introduce yourself when you ask the question. I got you.
I'm Dan Amrine from NCAR. I guess I'm interested in the edge of knowability in this problem. And if you have parameters that aren't constrained by data, are you beholden to your selection of a prior distribution at that point? And in this problem, do you really have to start thinking about the multivariate priors that you might have, and are there just things you'd never expect to constrain?
If you have parameters that aren't, constrained by data, you may need to eliminate them because then you can't know what your uncertainty is, I guess. If that makes sense. But maybe I'm interpreting what you said wrong. Say what?
Knowledge from other than observation.
Like from first principles theory or something like that. Right. Yes. Okay. Yes. Then in that case, that's when an a priori constraint might become important. Generally, we sort of don't. I've never seen actually that situation where you truly know from first principles. You can always make an argument, but it's always a little bit. There's always some holes you can poke in those arguments, I think. So parameters. I mean, even universal law of gravitation has free parameters. So.
All right, let's thank Greg one more time.
Oh, you need that.
Our next speaker is Andrew Shao. Andrew is from Hewlett Packard Enterprise, and he will talk about an online continuous learning framework for training surrogates of ocean models.
Mic check, test one. Okay, good. Okay, great. Yeah, so I'm Andrew Shao. I'm from Hewlett Packard Enterprise, and I hope all of you, some of you know who I am and will forgive the affiliation. And for those of you who are, why is there somebody from industry coming to talk to us about climate stuff? My background is actually in climate. I worked on KNSM5, worked a little at OM4, which hopefully gives me a little bit of a pedigree to talk about some of these things. One of the things I really want to kind of set up here, though, is that This idea that we're talking about, that a lot of people are talking about here, of how do we use AI in combination with our scientific simulation. You know, Libby yesterday was mentioning that there's a lot of effort in the ML community to advance ML, and that some of our understanding is relatively naive, or within our domain is relatively naive or maybe misunderstood. I will say that one of the things, having worked at HP and worked along with a lot of our collaborators at the national labs, is that this question of how we combine AI with our traditional scientific simulation is very nascent, and we are looking for people who are really interested in trying to look at this, because it involves new ways of thinking about how to combine numerical methods. It's changing the ways that we think about how we do computation, how we do scientific simulation. And so some of the things I'm going to talk about today are kind of more statements of practice about lessons we've learned in terms of what we mean by these things and how we do them, and some of the challenges that challenge the traditional ways of thinking. And one of the things I really want to stress is that, you know, we all come with a certain worldview, right? Some of us are theoreticians, some of us are numericists, some of us are machine learning people, some of us are data analysis. And it's really easy, and we've all met people who are zealots in each of those directions, right? We've met mathematicians who said, give me enough chalkboards and I'll just derive the entire world for you, and you don't have to bother with anything else, right? We've met modelers who have said, like, just give me enough compute and I'll compute the world for you and you don't have to worry about anything else. We've met numericists who said, just give me enough whatever and we'll get your truncation error down to order infinity, right? Epsilon infinity. And really what it does, and I think one of the beautiful things about climate modeling, ocean modeling, is that it brings us all together, that we have to, or we are forced to work together to work across these worldviews and actually come up with something that is really interesting, unique, and relevant for humanity. So with that part of the spiel done, of the philosophy side, I'm going to jump into this. I won't terribly spend a lot of time with this because both Laure, Libby, and other speakers have spent a lot of time with this. I think the main thing that I really want to point out, right, is that when we talk about surrogate modeling, there is an implicit definition here about mimicking something else, right? And it's, if something is an exact replica of something else, that is not a surrogate. A surrogate is almost always a lower order representation of something else, right? It is not, there's a lot of magical thinking sometimes in machine learning, that machine learning will do something better just because it's machine learning. It's just because something is more complicated makes it better. And that is falsified, but that has not borne out in a lot of different things. So I think that's one thing to keep in mind, right? One thing that we always need to remember is that despite all these things, these are always lower order representations of whatever process that it's being trying to model. And that applies to climate modeling too, right? Our ocean models are low order representations of the real physics of the ocean. You know, our climate models are low order representations of the real climate. Three kind of classes of surrogates that I've encountered when talking about this are the subgrid scale surrogates. So those are like the parameterization work. The lower right hand is an image where we did the CNN backscatter parameterization embedded in MOM6 and ran it on Frontier. The full surrogates, we've heard some mention of that, like some of the work that Laure's doing. The weather models are obviously being like super high in the news and people are using it, like ECMWF is now incorporating full surrogates. And then one of the things that I think is being less talked about, but that I want to kind of talk about today, is this idea of a numerical surrogate, right? Like, can we replace a numerical scheme with a surrogate of the numerical scheme itself? And so there's some of these papers out there, they tend to be not as well published. Like, you know, the atmosphere, they trained a neural network to replace the 1D advection operator in an atmospheric chemistry model. You know, we saw a talk by Yuri yesterday, which he was trying to train a neural network to essentially like replicate what the barotropic solver is doing. Okay, so one of the questions is, okay, well, like, you know, if we want to do this, we need to motivate this, right? So I get asked oftentimes by the marketing folks who are like, cool, I hear you're doing good things with AI models. So what are you doing? Are you making them, like, what are you doing? And I'm like, oh, we make them more accurate, blah, blah, blah. We can do that. But can we do it faster? And I'm like, that's a hard problem. And that's not always the thing. So part of this talk is self-defense for me to say, yes, I think I might have a way to accelerate a model so that I can talk to a marketing person and be like, just give them the yes answer. So that's kind of what we talked about. And one of the things that Laure was talking about, right, where it's like there is a potential to accelerate computing because these things are more performant in GPU. And if you're interested in certain quantities of interest, you can get orders of magnitude levels of improvement. Accuracy, you know, we saw some of those. There was a really nice talk yesterday by Fabrizio, and he was like showing how you could basically like learn the error of a numerical algorithm and try to translate across. Adjoint surrogate. So I haven't seen this talked about before, but one of the things that's really interesting about neural networks, right, is that the back propagation that's needed for training a neural network is essentially an estimate of the gradient of the solution, right? It is the mapping from one set of variables to the output variables, and so you automatically get an estimate of the adjoint if you have a well-trained surrogate model. The other thing that I think is super important, especially, I'm preaching to the choir here, but I hear a lot of talk about people just replacing these models outright, but the actual solvers in the numerical models are just a part of what we actually use with the models, right? There's a lot of machinery in place. We have diagnostic managers. We have ways of running these models, and if you have a full surrogate model, they're usually only predicting a handful of state variables. So if you want to do something like budget, right, close a tracer budget, well, you could train a model to predict fluxes, right? But then you're adding more and more variables for the machine learning model, and that tends to scale out the size and complexity of the model needed to actually do that. So I don't know how many diagnostics OM4 spits out, but if it's on the order of 100, that's 100 state parameters. That's 20 times more parameters than most of these full surrogates are actually predicting. And then the question also becomes, just because you're predicting fluxes, does the budget actually close, or are there errors in it? And then 5, one of the other things for reasons why we might want to look at a numerical surrogate is that we can actually keep these models really small, right? Because what are we doing with a numeric solver other than trying to do a small amount of arithmetic, right? Like if you look at all these solvers, it's just like, cool, you do a couple of additions, multiplies, divides, and bam, you've got a barotropic solver, right? But it's a small amount, whereas machine learning, the whole point of it is kind of to brute force it by just doing a lot of mathematical operation. And so we can actually rely on a lot of the efforts done by the derivers and implementers of the numerical algorithms to kind of help with this problem. Okay, so I'm going to start going into what we actually did and like to kind of showcase what we could do with this. So we're taking the MOM6 double gyre case, upping the resolution so it resolves some eddies, so it's kind of a more interesting solution. The neural network is a very simple neural network where it's going to just be ResNet, which is a classic kind of architecture coupled to a GRU layer, so we can predict things. And the things we're actually going to predict, we're going to take U, V, and H, right, just the velocities that we get from the momentum equation and the layer thicknesses. And what we want to do is we're going to output 6 snapshots of the mass transports, right? And so in MOM6, this is actually kind of an easy problem because it's just using U and a stencil about 2 points wide in each direction to do this estimate of the flux. So that's only like 5 floating point operations, right? And so the question is like order 5, maybe depending on your schemes, it's a small amount, right? Whereas a neural network is going to do like a small neural network is 100,000, right? So the question is, well, why would we want to do this then, right? Like why would we want to blow out the computation by factors of like tens of thousands or hundreds of thousands? Well, one, a hard problem comes into play when we want to think about doing a long time step, right? Because now information is propagating throughout the entirety of the grid in a way that we don't know how to capture with just a fixed stencil. You normally would do like an upwind advection scheme or something, but like, what does that even mean when the solution space is actually evolving underneath you? And so the idea then, if you want to take a look on the lower right-hand side, let's assume that layer thickness doesn't change. We just wanted to predict velocity, right? So on the left, on the blue is basically 6 snapshots of the velocity in the top layer. And we want to say, can we use that to predict the next 6 time steps? Right. And so the question then becomes, like, if you look at the solution, right, it's nonlinear. It's not just a straight line. There is structure to it, but it doesn't seem like it has a huge amount of discontinuity to it. So maybe this is actually a learnable problem. And so when we extend this to this idea of like, can we predict 6 time steps in the future? This is a harder problem and something that we don't know how to write down a priori using traditional numerical techniques, but maybe with a neural network, we can do this. One challenge to actually doing this is that if you want to train on the numerics, you want to train at the time step level, you need the time step level data, right? And if you just take a look at the, you assume there's 5 state variables, U, V, T, S, H, and you calculate how many time steps OM4 does in a year, that's a petabyte worth of data, right? Are you really going to blow out and store petabyte birth data? No. And so we need to think about this again, right? Are we really trying to train on every single time step, or are we doing things like where we want to map a function space to another function space, right? And that's really what we're doing with a lot of these operations, right? It's just transforming the model state from one time step to another. And so what we end up doing a lot of times, if we do a naive thing, is that we just take all the data available to us and don't ask, is it redundant? Is it useful, right? And so if it's redundant, that's a really bad case scenario, because if you're just doing a standard error function, you're essentially overweighting that portion of the space. So that's one thing to point out. And then the second part of it is that, these algorithms, right, the operators are not changing in time. The state is changing in time, but the operator is not, right? So can we actually train this in a streaming manner? Because every single snapshot is potentially a valid source of training data. And can we actually do this and not have to store the full petabyte, but still effectively train on the full petabyte, because we're still kind of doing the selective sampling. Forward point out. So one of the things I just want to point out here is that the very traditional pipeline for us, right, is we think about doing things in stages, right? Where we're doing a simulation. That simulation is storing something to the disk, and then we're doing something after it to load it from the disk. There are, again, if you want to try to do this, right, you have to store and process a petabyte worth of information. If you do this kind of in an asynchronous way, you might be able to, you need some kind of solution. You can't just swap it to the disk. And so the idea that we are going to play around with, and what my team works on, is how can we do this in an in-memory fashion? And so the way that we do this is the one corporate shell slide, I promise. This is the project that I work on. It's called SmartSim. It's an open source, completely free library. And really what we're trying to do is make it so that people can think about loosely coupling these kinds of applications to each other. And by loosely coupling, I mean that they don't interact directly with each other. They're not involved in the time stepping of each other. Like, they don't have intimate knowledge of what the other component is doing. And so the way that we focus the loose coupling is on whether data exists or not. And there's a central location that we call the feature store where that data is stored. And so essentially what happens over the course of the simulation then is that we send the data from the simulation to this database. There might be other things that are looking for the availability of this data to consume it, to train a model, to do some kind of processing on it, and then just stores it back in the database itself and stores artifacts or whatnot. But this is all done kind of, in memory over the high-speed interconnects, and there's no touching of the file system whatsoever. So it's actually pretty performant. We have a new paper talking about some ML techniques that we use in CF's computational fluid dynamics, which has a lot of similarities to the work we do. Okay, so to break this down, what we actually did in order to do this. For MOM6, we store 12 dynamics time steps. So that's U, V, and H at the beginning of the dynamics portion of the code. And then we store UH and VH, the mass transports, at the end of the time step. These are staged in that Smart Redis database. We have an intelligence sampler, which I'll talk about a little bit, where it just basically pulls the database for a bunch of new data sets and does it, and then says, like, should I include this in the training data set or not? And then we just have another training application that's just in an infinite loop, constantly training, and just checking every so often to see if there's new data to train on and incorporate into the training. So the intelligence sampler, this is essentially the problem that we're talking about here. So if you just have randomly sampled data, right, you often will concentrate it around certain clusters. That is not appropriate for a function space because you're essentially saying that you love different parts of the function space more, you care about the solutions in those spaces more. What you can do is that you can do, basically what's called inverse sampling. And so you take an original data set distribution, like what's shown in the black points on the rightmost figure there. And then you can use essentially the PDF, invert it as a way to say, like, should I accept it or not? And so what you end up getting if you apply this technique is you get a sample data set that is much more uniformly distributed over the entirety of the data set and is more representative of the function space itself and not of the data that you sampled, right? So this is a long kind of way of saying, like, it's kind of increasing the diversity of the data, right? You're not saying that everyone falls into this, 99% of the data falls within a certain range. You want the model to gain skill across the entirety of every single sample point. We can extend this to multidimensional data, like, the same kind of idea of like, okay, should we accept, how do we increase the diversity of the data set? again, won't go into too much, but everyone's friend, EOF analysis, PCA analysis, you can kind of break down a snapshot into its constituent parts and then ask the question using a statistical technique, how similar is this snapshot to some corpus of data that I already have? And you can make it a statistical test to say, like, there's a 20% likelihood that this data is due to this data set or not. Okay, so then the actual results for this little model is that we ran this, we trained this, and what does it do? It does a pretty good job, right? So on the top left panel, if we just look at the zonal transport, for the top layer, the neural network is on the left panel, the middle panel is the true. And so it comes up with this kind of like, interesting pattern of a mesoscale kind of field that looks like it's evolving. And the difference, if you look on the top right, is plotted there. And so it's actually 2 orders of magnitude less than the absolute value. So that's nice. The question is it good enough if we were to say, like, wanted to use it to get an estimate of the free surface height? So if we then just integrate over these 6 sequences that we predicted the mass transport and just update the column thickness, that's what you get on this bottom plot here. And so again, for the neural network, the change in the column height over these 6 time steps is plotted on the left. The center panel is what the actual model was doing and computing as the change in sea surface height. And the difference that you see is plotted there on the right. And it's on the order of 0.4 millimeters, right, of a difference between the 2 states. So that's basically saying over the course of 6 kind of dynamics-ish time steps, we're making an error about 4 millimeters. And so there's obviously another question about whether that's good enough or not. One thing that's really important to note here is that we were predicting the mass transports, right? So we were predicting fluxes. And so we can still take advantage of the fact that flux form is conservative, right? Because we were just updating the state with the fluxes themselves. And so we can still take advantage of the finite volume to say that if we add fluxes, we're taking away a certain amount from one column, putting it into another column, and everything is conservative. Even if the flux estimates are terrible, they could still be conservative, right? And so we're solving one of those problems of, can we conserve? The answer is yes. Is it the correct one from a dynamic standpoint? Well, that really depends on the quality and the scale of the model itself. One of the things we see here, and as the claim for the speed up portion of it, is that if we do this on the GPU to do one inference and roll out these 6 time steps, we get it's 20 times faster to do it on the GPU than it is doing it on the CPUs, right? And one of the reasons for this is that the GPU is essentially unrolling the time step, whereas the numerical solver has to take one iteration at a time, right? Okay, so here's the proposed algorithm. We have not tested this, but this is what we're trying to think about doing. We're basically, to solve this problem of acceleration, we're thinking about kind of like overlapping the numerics portion of it and the predictions from the neural network. And so we can take a longer time step. We can take advantage of this kind of 20x speed up, maybe have it so that it's like 10x speed up, but we still get something that still is operating in the same way that the model is integrating itself. All the other machinery around the dynamics there, the tracer transports are all still preserved. One of the things that we've seen, especially in early versions of full circuits, is that they dissipate over time, right? And that's kind of, if you're a numericist, you're like, oh, that's an overly dissipative numerical scheme. And so by doing this, we kind of take advantage of both things, right? Where we still can take advantage of numerical algorithms that are designed to dampen and control noise, to not be that dissipative. If you think of, again, these surrogates as a lower representation of the numerics, then it's kind of like just a slightly lower order accuracy numerical algorithm that we're trying to intertwine here. And so I'll leave it with this. There's a lot of, obviously, a lot of work that we still need to do to kind of showcase this and to try to prove it out in a more formal context. One thing I just want to note is that this online continuous learning framework, we've used it in a different domain, basically for chemical reactors with multi-phase flows, and we were able to scale it out. And we essentially trained on 47 terabytes worth of data from 33 ensemble members that were using like 5,000 GPUs, and we needed one GPU to do the training. because we just were able to compress the data set so much. Yeah, and we've got some interesting work, and my entire job is to work on scientific collaborations. So if you're interested, just let me know, and we'll have a talk.
Thank you so much, Andrew. To save some time, we're going to move on to the next speaker. Andrew, can you give us the microphone? You can catch Andrew during the break, or we'll have a discussion session at the end of this morning session. Our next speaker is online. It's Tuomas Karna from Intel Corporation. Tuomas, are you there?
Yes, I'm here.
Cool. And the title of the presentation is Exploring Python-Based Frameworks for Geophysical Modeling.
Okay. So I hope you can see the slides now. My name is Tuomas Karna. I'm at Intel nowadays, but as many of you know, I've worked a lot with different kind of models in the past. And first of all, I want to thank the organizers. I think it's great to see that the COMMODORE meeting series continues. I think that is a great venue for discussing modeling related issues. And I'm also happy to see that this year we have a lot of AI related talks. So this year I'm going to talk about exploring Python-based frameworks for geophysical modeling. And this is work done with my colleagues Frank Schlimbach and Chuck Yont, and also Matthew Piggott from Imperial College. And to distinguish from the previous talks where you used AI methods to build surrogates for modeling, what we're doing in here is that we're kind of building classical modeling solution on top of Python-based frameworks. So these are not surrogates that I'm talking about. Now, the motivation is that, you know, a lot of geophysical modeling is done with Fortran-based codes and some C++ codes that are becoming hard to maintain, and especially now that we have GPUs and other accelerators, they are becoming increasingly difficult to port to accelerators. And at the same time, we know that in machine learning and AI world, there are these Python-based frameworks like PyTorch and JAX and TensorFlow that offer like very high level, easy to use Python interface to the users, and seem to be performing well in both CPU and GPU environments, like seemingly transparently. So the question is that, can we do something similar for geophysical modeling as well? So the goal is that to have some kind of a modeling interface where the model developer works at higher level. So really the only thing that the model developer wants to focus on is to write the equations, the operators that we want to implement. And at that level, you don't really care what the loop structure is going to look like when you run it on the CPU or GPU. You just want to express the physics that you're instead interested in solving. Much like in the same way as you do with machine learning, you only describe the layers that you want to use, not how the layers are being implemented at lower level. The user interface needs to be flexible enough so that we can express all the operators that we need in let's say ocean modeling. And of course the big question is performance. So computational performance has to be there. It has to scale to large problem sizes. It has to be portable across CPUs and GPU environments, and also run in distributed mode, meaning multiple nodes, multiple GPU environments. And one benefit of looking into these machine learning frameworks is that, as it has already been mentioned, they kind of have built-in support for inverse modeling, because when you do training, what you're actually doing is that you generate the adjoint model automatically. So if you use this kind of a framework to build your, let's say, ocean model, what you get is the adjoint model for free. And this is very attractive for, let's say, data assimilation or parameter optimization and so forth. So when we started to think about this, we figured out that we need a way to evaluate different modeling frameworks and whether they are suitable for geophysical modeling. So we need to have an idea whether the programming interface is such that we can implement physical operators on it. And of course, we need to verify the computational performance. and also the portability that we can run it on different target hardware. So we essentially need simple but representative benchmarks that are easy and quick to implement in any language or any framework, but they are still realistic enough in terms that they represent real patterns, computational patterns that arise in more complex realistic simulations. And one important aspect is that these benchmarks, we should have a good correctness test so that we can verify that the solution is always correct. So in this talk, we're starting from very simple. So I'm only considering two-dimensional structured grid finite volume benchmark. So essentially based on the Arakawa C-grid formulation. And I'm focusing on two cases. So the simplest case is the wave equation, and the more complex is nonlinear shallow water equations. So the wave equation benchmarks is kind of the simplest one that we could think of. So linear wave equation and also constant bathymetry. So the benefit here is that it's very simple to implement in any framework, and you already can infer something about the computational performance that you might get in the end. But what I want to focus on is the shallow water equations, because this is more complex, it's non-linear, there's more compute, you need to allocate more memory, and it's also a realistic use case in the sense that it's used as a part of ocean models, and then there are also like flood and tsunami modeling that is already done on shallow water models itself. So the formulation we're using here is kind of the energy conserving formulation by Arakawa and Shao, 1990, and we use explicit three-stage Runge-Kutta solver, so a strong stability preserving Runge-Kutta solver here. And we use the analytical solution, just the geostrophic gyre in this case. So what we did in the end is that we took these two benchmarks, the wave equation and the shallow water equations, and we implemented them on a lot of different frameworks. So for the Python frameworks, we're considering here PyTorch and JAX, which are existing machine learning frameworks, and they both have like NumPy-like array user interface. And in order to get good computational performance, they both have just-in-time compiler and support for CPUs, at least in single node mode, and then GPUs as well. And because they are machine learning frameworks, they have this built-in adjoint modeling capability. And on top of that, we are also comparing against our own proof of concept system, which is called sharded array for Python, or Sharpie for short. So it's a fully distributed NumPy-like framework where distribution is done automatically using MPI, and we use LLVM MLR-based just-in-time compiler there. So these Python implementations, we are then comparing against some references. So we have NumPy implementation, which is not really interesting because NumPy is very slow. But we are also comparing against YASK, which is a C++ library, yet another stencil kit. And it's highly advanced stencil compiler targeting CPU environments. And we're using YASK here to demonstrate what is like the best performance that you could possibly get in CPU systems. So it's kind of our golden standard for CPU performance. And then we're also comparing the shallow water case against NEMO. So the recent NEMO version has a shallow water solver or example, and I modified the example such that we're solving exactly the same problem. And we're also using a three-stage Runge-Kutta solver there. So we're kind of using this NEMO 2D shallow water solver as a proxy for existing Fortran models here. All right, so then how does it look like when you implement geophysics on structured grids in NumPy-like arrays? Well, as you can probably imagine, is that if you need like the pressure gradient operator, like in this case, when you write it in Python in NumPy-like notation, you use this array slicing, which is also you're familiar with in Fortran. So the API is relatively easy to use and easy for model developers to use. And we use this array-like formulation for all of the Python frameworks. JAX is a little bit different because JAX arrays are immutable, but it's only a detail in the implementation. And really the key ingredient to get good performance in these Python frameworks is that you're not running Python at runtime, but you use just-in-time compilation. So it means that you have a sequence of operators and there are different ways you can compile these operators into a single function that is then highly optimized. And in JAX and PyTorch, you can do this by using a Python function decorator, and then depending on the cheating system you have, it does a lot of optimizations to get the performance. And of course, depending on the target, it can optimize code for CPUs or GPUs. And this is really the key, how you get performance and how you get portability, so that you write your Python code once and you can run it either in the CPU environment or GPU environment with good performance. And then for our own proof of concept system, Sharpie, it's similar. So we use NumPy-like interface again, but not the full NumPy API, but something called the Array API, which is a well-defined subset, and it's becoming a standard. But basically, you write code that looks very much like NumPy code. And if you want to run it in serial, you just execute your Python code and it runs on a single core. If you want to run it in parallel, you just run your Python with an MPI run or MPI exec. What happens under the hood is that the halos and communications are automatically computed. So the size of the halos and also when the communications need to happen. Current limitation is that we only have 1D row distribution in parallel, but in the future, we're going to have general distribution as well. And for the just-in-time compiler, we use LLVM MLIR, which you may know is like compiler technology and quite widely used now in the machine learning world as well. And it's basically a framework in which you can apply many different kind of optimizations to get to the performance where you want, and also target hardware, CPUs or GPUs. GPU support is under development, and basically the only difference is that if you want to run things on the GPU, then when you're allocating arrays or creating arrays, you need to indicate that you want this array to live on the GPU. And after that, all the computation is being offloaded automatically. All right, so to the results, these are the wave equation results on a single CPU node and GPU, but I'm going to skip it. I'll go directly to the more interesting shallow water equation case. It's more complex, and you also see it in the results. So on the left-hand side, this is time per time step for all of these different implementations running on one CPU node with 112 cores. And you see that there's quite a lot of variability in the performance. And interestingly enough, JAX is the slowest of the plotted ones. And that's because for some reason, the threading in JAX doesn't work too well on the CPU environment. Then we have the other two Python frameworks, PyTorch and Sharpie, which are considerably faster, the green and red bars. And the blue bar is the Nemo 2D Fortran code that we use for comparison. And the interesting thing to note here is that PyTorch is running like 1.9x faster than Nemo on the same system, although we are essentially using a Python framework. And then the purple bar is YASK here that you can hardly see. And this is just to remind you that if you take this kind of stencil problem and you apply all the imaginable optimizations that you can do, there's still another 10x speed up possible to achieve. So the big question is that with these just-in-time compiler systems, could you actually improve the compilation so much that we could push the performance closer to the purple bar? But the interesting thing, of course, is that you can take the same Python code without any changes and you can run it on the GPUs, and the performance is shown here on the right-hand side. So there's quite a lot of variability. Sharpie is about 2x lower than JAX, and PyTorch is then 2x faster roughly than JAX. So also here to note is that compared to the Nemo code running on the CPU, we get 4 to 16x speed up with these Python frameworks. So this looks kind of promising. It suggests that you can implement geophysical solvers and operators on these Python frameworks and get good performance and run across different types of hardware. Now, in here, we're only considering single CPU nodes and single GPUs, so not fully distributed. And currently, JAX and PyTorch, I haven't been able to run them in fully distributed mode for these problems. So we don't have numbers for that. But for Sharpie, since we're using MPI for parallelization, we can just run it on multiple nodes in the CPU environment. So here I'm running the same problem size with 1, 2, and 4 nodes, and you see the timings here. So basically what you see is that we get about 60% scaling efficiency, which is not great, but it's also not completely terrible. And you need to keep in mind that in Sharpie, we are currently only using row decomposition. So if we do 2D decomposition, we can probably get much better performance. But again, remember that the user only writes NumPy code that looks serial and there's nothing communication related, and you get this performance out of the box. So that is pretty encouraging. So to conclude, Python frameworks do look promising in terms of implementing, let's say, classical geoscientific models. And the benefits are that you get much better user interface for the modelers to work with. You don't have to deal with the low-level loop structures, for instance, anymore. And we do get performance portability, and the key ingredient is this just-in-time compiler. So we get good performance both in the CPU and GPU environment. And in order to do this kind of work, we need rigorous benchmarking of different frameworks, and we need correctness tests, and to be able to choose what kind of framework we should be using in the future. And here in this table, I'm just listing some of the properties of these 3 Python-based frameworks. So all of them support both CPU and GPU environment. There are some important differences in the performance that we see. Sharpie is MPI, so you can always run it in distributed mode. Whether JAX and PyTorch can in the future be also run in distributed mode, that's an open question. I know there's a lot of work being done in this at the moment. And then JAX and PyTorch, because they are machine learning frameworks, they have this built-in adjoint capability, which is very nice, and we don't have that in Sharpie at the moment. So for the future work, I mean, we started very simple 2D test cases only. So we need to extend to more complex test cases and to 3D, find good benchmarks there, test potentially different frameworks. There are open questions related to implicit solvers. If they're local, maybe doable. If they're distributed, then we need a distributed linear algebra library. Supporting unstructured mesh models is going to be more tricky, because you need to, instead of just doing 1D tiling or 2D tiling for the partitioning, you need to actually partition the mesh first. So we're also looking into that. But that's all I had. So if you have any questions or comments, you can ask them now, or you can ask them later. And since I'm not in person there, you can at any time send me email. Thanks for your attention.
Thank you so much, Tuomas. We have time for one quick question. No VCR, so then goes to Bob.
Thank you. I really appreciate the shallow water test case, but it's limiting in one very important regard. The Arakawa and Shou dynamic core uses a linear continuity solver. Su and Arakawa, the next paper in the journal, says it's not positive definite, and they come up with something where the stencil is flow dependent, which is exactly the sort of small step towards complexity that sometimes has gotten in the way of application to GPUs. Have you considered using a positive definite and nonlinear continuity solver as a next step to evaluate one of the first ways that some of these kind of techniques, by virtue of the fact that you have to put logic in that varies from grid point to grid point, might struggle in a way that you would actually realize in real GCMs?
That's an excellent point, and as I mentioned, we're starting very simple, and there's many ways that you could extend it, and certainly, yeah, extending it in this direction, and also implementing more complex advection schemes and things like this are things that need to be considered. But yeah, that's a good suggestion. Thanks.
All right, let's thank Tuomas one more time. Hi, Patrick. Can you share your screen, please? Okay, so welcome everybody to now the second part of the session of this morning. And our next speaker is Patrick Heimbach from University of Texas at Austin. And the title of the presentation is Learning from Sparse Observations Through the Lens of Models.
Yes, hi everyone. I'm sorry I cannot be with you, but I may still join for the hike on Thursday, now that I've heard this one. No. I thank you for giving me the opportunity here to present. And I would like to start here with the question of, clearly we're in an age of big data science. And the question here, of course, is Earth science a big data science? And in view of all the existing and forthcoming satellites that are coming online that we're quite excited about, for example, SWOT, the answer might be yes, but I'd also like to take the contrary answer here, no, from an oceanographic observational perspective. We still have a very sparse data problem. Many of you have seen this figure here. I don't have to belabor this to this audience, but just to show again here, the top 2 kilometer depth in the northern hemisphere and in the southern hemisphere as a function of time from 1950 to 2010 here, where we see that basically below 700 meter only until recently, basically until the advent of the Argo float program, we begin to have a somewhat decent coverage of the ocean, but this is just the 2 kilometers and the mean ocean depth is 3,900 meters. And we also see here the distribution of the oceanic volume as a function of latitude here. Of course, much of the volume here in the southern hemisphere, but much of the observational coverage here in the northern hemisphere. Just to drive home the question is, at least observationally, we're still a sparse data problem. So we're dealing with an eclectic and patchy global ocean observing system. And on the other hand, we have another information reservoir, which is numerical models. But these models, of course, as you all know, they are uncertain. And in particular, they require uncertain inputs. And, I'd like to raise the question that was asked yesterday, question number 2. How can we better use observations to evaluate and advance ocean models? And of course, the answer here is, we use data assimilation or inverse modeling. So what is data assimilation? I'd like to take these 2 quotes again because they're really quite powerful and really crystallizing what this is trying to do, right? So from Kaminsky et al., ideally, all observational data streams are interpreted simultaneously with the process information provided by the model, and which leads to a consistent picture of the state of the system that balances all the observational constraints. Think about heterogeneous observing systems and taking into account all of respective uncertainty ranges that we put into the data assimilation system. And also quite important here, data assimilation allows information provided by the observations to be propagated in time and space to unobserved areas that we're actually interested in, and that is provided by this propagation by the numerical models. But data assimilation is much more than oops, what I have here. Data assimilation is much more than its use in numerical weather prediction. And, again, the answer to the question number 2, in some ways, yesterday was given sort of 3 decades ago with this one of these textbooks here. But I'd like to go and say, we're talking about sort of that we are the inverse problem that's learning from a set of available but usually sparse and heterogeneous observation in known physics and dynamics. But I'd like to point out, what do we mean by learning, actually? And that applies to both inverse methods and also machine learning. And for the audience here and for the question that we have, improving models, right? So we have a physical model here. Blue, you might think of it as a dynamical core. And in green, everything that's uncertain. In the model, these are uncertain inputs. These could be these parameterization schemes. These could be the initial conditions, and these are also the boundary conditions. So all of these are uncertain, and so all of these are up for grabs in trying to think about, how do sensitive perturbations in these uncertain parameters actually change the model solution. And of course, for the audience here, what we are interested in is learning model parameters. So basically, I'm marked here in red. So what we're interested in this specific context here. We have, of course, empirical parameters through constitutive laws and subgrid scale parameterizations. And an inverse problem, so that deals with this, is basically the parameter estimation problems to use the observations in order to estimate, calibrate, reduce uncertainties in these parameters and have a better calibrated model. And again, to the question asked yesterday, there is actually some work that has actually used observation directly to at least infer some of these parameters. So here, the paper by Forget et al. 2015 on the observability of turbulent transport rates using Argo data. So supporting evidence here from an inversion experiment. Or more recently, actually an attempt to actually not just use the hydrography in the Argo data and other data to invert for example, tracer mixing, but actually use mixing estimates directly and see whether those direct constraints actually, how do they affect, for example, state estimates. And then we've heard this morning, we say, well, maybe these parameterization schemes have structural errors and we don't trust them. And so can we use neural networks, right, to basically replace in this modeling framework, can we replace parameterization scheme by a neural network? And this very nicely shown and worked by the M² Alliance teams here, for example, Zanna and Bolton 2021, where you're using simulated data here on the left here to try to, for example, estimate eddy stresses. And then using a well-trained neural network, you plug that neural network back into your full model, and then you hope that the model will perform better. But you can potentially do more, right? So you want to actually say, well, not only as I've pointed out, not only is this neural network uncertain, and so we need to train the weights, but we also still have the other parameterization schemes and the other uncertainties as well. And so we don't want to actually train on only simulated data to estimate sort of a specific process in the model, but we want to do what's called online learning, where we basically still learn on the actual state of the model, which is both what we can, of course, simulate, but which is also what we can actually observe, right? And that gets us much closer. If you were to remove here the inverse, the neural network here, you would basically come back to just the conventional inverse problem, but with the neural network here, we now then call it a posteriori or full model or online or end-to-end learning, different uses of languages. So this would be very powerful to embed basically the surrogate model in the form of a neural network within this physical model to do full model learning. The other things, of course, very quickly, if we go back to what we actually want to learn is the initial condition. So we trust our parameterization. We get back to the filtering problem of optimal estimation and control, and which is then basically just what's practiced in numerical weather prediction, namely you have a forecast. At an analysis time, you estimate a new optimal initial condition that hopefully will give you an optimal forecast for the next period. Or you come to the smoothing problem, and that's what we prefer to call sort of the state and parameter estimation problem, where you basically hear the blue curve, where you try to come up with a solution of the problem over a long period of time that is consistent with the model trajectory of this longer period of time. So this would be the smoothing problem or state and parameter estimation problem. Finally, what we haven't talked about, so we could also learn or invert for the surface boundary condition. For example, the air-ice ocean fluxes, which are the air-sea fluxes of CO2 that we could infer from the measurements of interior, right? So this is the classical inversion of boundary conditions from well-observed interior. And that gets us to sort of a flux inversion problem. So the overarching key unifying computational framework, at least the way how we'd like to look at this, is through learning from data, is through gradient-based optimization. And so either from conventional inversion, we basically use an adjoint model of the physical model to basically minimize the model data misfit. Or in the machine learning world, you then now call this a loss function. And what we're now training or learning is the weights of your functional representation that is now not a physical model, but it's a neural network representation. And so this adjoint model or the back propagation in neural network, as Tuomas Karna has already pointed out eloquently, is basically, these are basically mathematically conceptually the same thing, and they are essential tools for high-dimensional gradient-based optimization. And so we then ask the question, how do we do this full model learning, and how can we integrate surrogate model training within sort of full model calibration? And that leads us to a project that's sort of currently underway. Has a long name, but so the short abbreviation DJ for Earth is differentiable programming in Julia for Earth system modeling. And so what we're trying to do here is exactly what I've just described here. So we have our dynamical core, we have uncertain inputs to the model, in particular, the surrogate models that are now called just generally surrogate models, which could be physical parameterization schemes, or they could be some neural network representation, neural ODEs that we can plug into the system, but we're learning data that is basically generated by the full system in advance. And to do that, we use what's nowadays called differentiable programming to do this end-to-end learning, which in turn relies heavily on general purpose automatic differentiation. So differentiable programming, that notion has taken off very recently here. Reviews papers just here from last year, 2023, differentiable program for Earth system models here in geoscientific model development. Another just perspective also the same year, just last year, here a perspective piece on differentiable modeling to unify machine learning and physical models for the geosciences. Here just a paper and review on sort of the computational tools on how to do this. And quite excitingly, in the atmospheric community, this has actually recently been implemented and fulfilled, right? So the neural general circulation model for weather and climate, so the rewrite of a dynamical core of an atmospheric model in JAX to be able to take advantage of JAX's AD capabilities to do this sort of end-to-end learning. So what we're doing here, as I've mentioned in DJ for Earth, right? So we're using Julia. And the main reason here for using Julia is that we'd like to basically take advantage of model development that is already underway, currently by this Climate Modeling Alliance, or CLIMA here. Secondly, sort of the Julia community is taking very seriously the notion of differentiable programming and the use of either automatic differentiation or composable adjoints in what's called the scientific machine learning infrastructure. And then, of course, Julia's power to harness GPU computing and to really be sort of this this scientific programming language that should be very powerful for this emerging heterogeneous compute architecture. So we're trying to harness this in the context of this ocean model component of CLIMA that's called oceananigans.jl, or I think now more recently ClimaOcean.jl, a finite volume rotating stratified fluids model here. It's written from scratch in Julia, and that can run on GPUs or CPUs via Julia's kernel abstractions method, and then parallelize using MPI.jl and multi-threading. And so we are endowing this oceananigans.jl now with a new, also being developed general purpose automatic differentiation tool called Enzyme. And one of the powers of Enzyme here, it actually acts at the LLVM, so at the compiler level that, again, Tuomas just previously highlighted. So we can actually take advantage of compiler optimization that is performed by LLVM before we do the automatic differentiation on the physical model, or the combined physical model and surrogate models here, to then generate a highly optimized code, again, that is differentiated code either for CPUs or for GPUs. So some of the GPU automatic differentiability or adjoint capabilities are, again, done through kernel abstractions, and that we provide directives, that we provide information for how kernel abstractions should deal with the to be differentiated code. And so here, Enzyme, again, I highlight some of the key developers here, formerly at MIT, William Moses and Valentin Shiravi, now at University of Illinois, Urbana-Champaign, and Valentin just moved to Germany, and then colleagues here at the Argonne National Lab. And again, one of the powers here of enzyme is that it also handles arbitrary GPU kernels. So we're really looking forward here to an ocean model that not just in a forward sense really harnesses from natively GPUs, but also the adjoint or the differentiated code also being able to harness the same type of scalability that the forward code already has implemented. So to basically inherit this in the adjoint code. The applications here of DJ for Earth are an ocean model. So that's oceananigans.jl. We're also working, colleagues at MIT, on a sea ice model that we'd like to basically look at coupled ocean sea ice simulations. And then finally, the project member also include some of the actually leading ice sheet model developers like Mathieu Molligem and Shenggong here at Dartmouth College. Mathieu, for those of you who know, is one of the core developers of NASA's ice sheet system and sea level model, ISSM. And so they too have been involved in this project to develop Julia-based ice sheet model, and with the AD capabilities develop these hybrid adjoint and machine learning tools. And so so we're in the process here of building this tool. We have actually working on the Oceananigans side a simple advection diffusion problem now. So we have had to work through a lot of hoops to deal with type instabilities in the Julia language and some other structure problems that Julia presented itself. That's all been worked through. We have the ability now to work probably also with the kernel abstractions to work both in a CPU and GPU implementation. We're actually also working with colleagues at Los Alamos National Lab to side by side work on a prototype Julia implementation of the AMPAS ocean model, which actually is very exciting because we have the same AD tool enzyme that will work on two different ocean models. So we basically almost never had this actually in the Fortran world, but we may have this now in the Julia world, working on two basically dynamical cores of ocean models. And so this I'm just going to finish here with highlighting sort of a set of mini tutorials that you can actually access here online that basically work through both the Julia and the AD tool enzyme development, and then basically some simple implementations, initial Earth system models in Julia and how we basically differentiate through them. And with that, I'm happy to take questions.
Thank you, Patrick. We have time for a few questions, starting from early careers. Is there early career here?
Thank you, Patrick. Stephen Griffiths. I think I'm probably a decade or two behind the bar with automatic differentiation. And my question is related to nonlinear advection and nonlinear diffusion operators, which are all over the place with ocean models. Are they handled pretty seamlessly with the automatic differentiation tools, flux limiters, and ready diffusion, that kind of stuff?
Yeah, so not seamless. Great questions. Always the obvious questions, the nonlinearities in the model, switches. So the model, I mean, it's a very loaded question, right? And so one would have to go, I mean, we could talk for hours now. The nonlinearity as such is not necessarily a problem, right? So for example, switches, flow controls, because the adjoint will basically keep track of where in your flow control you are, right? So that's actually one of the powers of AD. The nonlinearity will, especially if it's strong nonlinearity, of course, will hit you as you go out to long integration. Your sensitivities will start to increase exponentially. But this is actually a power. So this is actually could potentially be, you can turn this around. Actually, you can turn this around in two ways, right? So the one you could say, well, we can think about approximate adjoints that will still be useful, and where we actually have a surrogate in the adjoint of or a simplified version of the of the, for example, nonlinear scheme that you're interested in, and to replace it, for example, by another surrogate model, right? So this has actually been done, ECMWF basically hand codes its simplified, its approximate adjoints into their adjoint model. The second, you can actually turn this around and say, well, look, to the extent, if you think about under the hood of a neural network, right? So you have it's a highly nonlinear functional representation, right? So where you have nonlinear activation functions upon nonlinear activation function. If you look at this function from a conceptual point of view, it's a highly nonlinear function, and they are still able to use gradient-based optimization. And of course, the reason why it still works is basically that you basically have to go into the detail and look at how, if there are places where you need to alleviate this. But, the MIT GCM, we're running, I have to go back now. So, we're running a nonlinear free surface, and we've been running the adjoint with the MIT GCM nonlinear free surface very successfely for the state estimation product. So the answer is the devil is in the detail. And so it's clearly not that you basically just, throw your model into the AD and then basically you're done, but you have to work a bit harder to get it to work. But again, look at what the Google folks have achieved with the neural GCM.
Okay, let's thank our speaker one more time. Our final speaker for this session is Lorenzo Zampieri from ECMWF, and this is an invited talk. Is it working now? Okay, great. Cool, great. So, no, disappeared. Okay, perfect. Yeah, sure. Yeah, in the meantime, I can start saying thank you for the invitation, also on behalf of ECMWF. I'm very glad to be here. And yeah, let's wait for the slides and then I'm ready to go. Yes, perfect timing. And let me start the timer so I don't abuse your lunch break. Okay, so towards a fully machine learning Earth system model at ECMWF. I will start saying that this is not my work. It's the work of many, many people. So I want to start acknowledging the work of this very long list of co-authors and people that work on this problem. So let me start by talking about weather forecasting. I know this is an ocean conference, so bear with me. Traditionally, the way we do weather forecasting is to start with an analysis, which is a great fusion of short-range forecast with the latest observations. So it's a very good representation of our atmosphere and of the Earth system. And then we propagate this forecast in time with the numerical model. And then we get our numerical weather forecast. This has been established for many, many years. But recently, there has been an alternative way of doing weather forecasting. So with the data-driven model that replaces the numerical weather prediction model. This is very new and is very promising, and there is a lot of excitement in our community regarding these developments. Not only the methods are changing, but also the players in the game are changing. There are new tech companies that are interested to this problem. I also just want to mention that not only tech companies, but want to flag the work of Keisler 2022, which was really fundamental, I think, to kick off this new endeavor. So if we look at what we call the quiet revolution in weather forecasting, we see something like this. These are the skills of our IFS model at ECMWF that grew slowly year after year. And these developments are due to increasing resolution, better observation, better the simulation scheme, better parameterizations.
And yeah, it's a tough job, but we got these very nice improvements. And now with machine learning models, you see that there has been a very big jump. And this is something we don't see often in this field. So yeah, the excitement around these new techniques is understandable. So here you can see, okay, yeah, the pointer. Okay, yeah, here you can see at day 6 and at day 10, the substantially higher skill of our AIFS model, for example, in this case. This is just a more general overview from the Weatherband 2 scorecard. You see a lot of blue, and this means that these machine learning models in pink are doing a better job for these variables than the traditional AIFS high-risk. So yeah, there is a lot of interest, but also a lot of open questions that arise from this. And the first one is how much there is still to gain from these ML techniques in weather forecasting. Have we done the big step and now it will be incremental again, or can we progress at the same speed? Also, can we extend ML weather forecasting beyond the 15 days of medium range that we typically target? Can the same methodology be applied to other Earth system components? For example, the ocean, the sea ice, the land. And also, can we have a reliable ML model, not just for weather forecasting, but also for climate? These are all open questions. I don't have a good answer for you, but this brings me to the presentation structure. So in the first part, I will explain how we are approaching the medium range weather forecast problem with AI at ECMWF. And in the second part, I will talk more about our exploratory work and future perspective on non-atmospheric ML components. So let's start with the artificial intelligent forecast system, the AIFS. This is our data-driven forecast model. We train the model on approximately 40 years of the ECMWF Era 5 reanalysis, and we fine-tune on operational analysis. And the idea is the following. So we have reanalysis data at 6 hourly time steps. This is a very good representation of the evolution of the atmosphere because it is observationally informed. And basically, we learn how these pictures evolve. And then when we forecast, we basically autoregressively step the trained model in the future with the same time step. I just want to mention that similar approaches are followed by many research groups and tech companies around the world, both for the type of models that are implemented, but also for the use of Era 5 dataset, which has been very well established. Now, the current version of the model, like the most recent update has been released in 2024. And we have a quarter-degree atmospheric model. It's based on an attention-based GNN, graph neural network, for the encoder and decoder. And we will see briefly in a second what they do. We have a transformer backbone in the processor, so in the latent space. And we, just to give you a rough idea, we trained this on 64 GPUs in roughly 1 week. And there is a preprint now out that illustrates the AIFS and many more details. So there are a couple of components which I think it's interesting to analyze. The first one is the encoder and decoder. So you imagine that we live on the Era 5 grid, but then a lot of our minimization and computations are not done at that resolution, but we go to a latent space at lower resolution, roughly 1 degree. And this encoder and decoder are the neural network that bring our data from the Era 5 into the latent space and back. And inside we have this processor. So the processor is a transformer, so something like we have in large language model. It works with sliding attention windows. Here you can see a schematic, basically, of how this works. Conceptually, you can imagine we have an orange point. This is our target node, and it communicates in one processor layer with all the blue points. And since we iteratively repeat this operation for multiple times, then in the end, that point will communicate and it will be able to find correlation with wide space around the globe. Here is just, the resolution is actually a bit higher. This is just to illustration. And we use this new transformer architecture since February 2024. We also have new development with graph transformers, but I think the concept is similar. And this is the main point. So how costly is AIFS? Well, it's much faster than our traditional model. You can see our high-res deterministic forecast, which is the little mouse, and then we are more like an ant. But you should keep in mind that to train these models, we need to run the big elephant, so ERA5, which has been a huge endeavor. Of course, then it benefits many more people because a lot of different people can train on this reanalysis and can be used also for many other applications like climate monitoring. Okay, so what about the skills? These are forecast scores, average for the year 2022. You can see in red our traditional IFS, the numerical model, and the newest version of the AIFS in blue. And you can see that basically we outperform the traditional model, and the performance of the AIFS are in line with those of other state-of-the-art machine learning weather forecast systems. I think it's more interesting actually to look at test cases compared to average scores. So this was an extreme precipitation event in the United Arab Emirates. In April 2016, you see a lot of rain that typically we don't see in these regions, up to 100 millimeters and more in certain locations. These are the observations. Here, the top panel, you cannot see it. It's the AIFS forecast, so the machine learning model. And at the bottom here, we have the traditional NWP forecast. You can see, of course, the resolution is different, but we capture very well this signal. This is a day 3 forecast. And I think what's very important to point out here is that this is really an extreme event that has never been seen from the training data set. So this is the maximum climatological value of precipitation below here that has ever been observed in ERA5, and this is the prediction in Chan of the AIFS model. So definitely the model is not just emulating the reanalysis, it learns something about the physics and it's able to give us a skillful prediction a few days in advance. We are not just doing deterministic forecasting, but we are also building an ensemble prediction system. This is very important for the medium range. And we are using different approaches. So the first one is to inject some noise in the latent space at the process level. And then instead of minimizing mean square error, we minimize the CRPS across the ensemble. So we try to get the best distribution rather than the best deterministic forecast. This is one approach. Second approach is to use generative AI. So this technique has been promoted by GenCast, and we also rapidly adopted it at ECMWF. It works very well. And basically the problem here is posed more like as a denoising task rather than a collective minimization technique of the ensemble. And this is currently our choice for the ensemble at the medium range. Okay, before moving away from the AIFS, I want just to mention that we have a lot of information on the AIFS blog. So we regularly post our developments. I encourage you to have a look and check it out. I think it's, the updates are regular, and it's helpful to keep an eye on it. And also, I want to mention that we are actually running this forecast in almost real time. And the forecasts are made available freely. You can download the AIFS data, but you can also have a look at the charts from our AI model and also many other machine learning weather forecast models, compare them to our traditional IFS. And I think this helps to build trust on these new tools. And it's also helpful for our verification team then to verify and do a thorough evaluation of these new systems. Now, to move away a bit from the medium range, we can do also funny things with this model, and we can bring them outside of their comfort zone. This is an example. So we model models that have been trained on Era 5, so on the present climate. We can use them to produce forecasts in the future or in the past. And that's what you see. Every spaghetti line is a 10-day forecast with Pangu, AIFS, and GraphCast. And you see that basically what happened, I think what happens is what we expect. So in the future, we get a cooling signal because the model has not been trained on the future climate. This cooling is particularly strong for Pangu weather. It actually happens also in the past climate, a bit less for AIFS, and GraphCast does a slightly better job when we look at global mean 2-meter temperatures. Actually, if we look at the spatial distribution of this cooling after 10 days, you see that actually GraphCast does a good job just because there are compensating biases. So it warms over the ocean and it cools over land, whereas AIFS does a better job over the ocean, but it still cools substantially over land. I think this makes sense because the atmospheric model doesn't have any information about the land state in the future climate, doesn't have any information about the sea ice in the climate model from which we initialize. So there is the hope that by including more model components, we can actually improve on this. And that's what we are trying to do. So, sorry. The slide doesn't change, it's a bit slow. Yeah, here we go. So we are thinking at more model components. We want to go beyond the atmosphere. We want to, to simulate with machine learning, the land, the waves, the sea ice, and the ocean. I think in general, for the land and waves, the problem is a bit easier from our perspective because these are strongly driven from the atmosphere. Whereas for the sea ice and the ocean, the situation is a bit more complicated, as we will see in a minute. Just want to mention that the work on this new model component is made possible by the Destination Earth initiative, so funded by the European Union. Let's start with an example. So wave modeling with AIFS. We tried very pragmatically to add additional variables to the atmospheric AIFS. So we tried to simulate the significant wave height, the mean wave direction, the wave period, and the drag coefficient with waves. And the objective is to learn, if we can learn these variables, to avoid deteriorating the atmospheric skills as usual, and to test potential benefit of adding these waves. You can see here in this plot where we show the loss that these wave parameters are trained all together with the atmosphere. So there is no real coupling here. The results look like this. So this is a comparison of the AIFS and IFS against independent observations from altimeters. So you can see that the take-home message is that the machine learning model does a good job also in simulating waves. Of course, there are caveats related to the fact that we have a lower resolution in the machine learning model for now. So all this testing is done at 1 degree, whereas the high-resolution model can resolve more spatial variability. Also, we didn't see strong deteriorations of the atmospheric model by including the waves, but also we didn't see strong benefits or improvements, for example, in the 10-meter wind prediction by having additional wave information that the model can learn. Now, when it comes to the sea ice, we are still at the very beginning, so this is just kind of it's more like intentions than our result. We know that CI's emulation with machine learning can be done. It has been done, for example, in the SASIP project. Here I'm showing a plot from a very nice paper by Tobias Finn and colleagues. And what they do here is to use a diffusion model, generative diffusion model, to simulate the CI's evolution by keeping, for example, all the nice linear kinematic features that they simulate in their NextSim simulation. So it can be done. There are a lot of open questions, I think. So, for example, how do we normalize the CI's variables? What's the optimal architecture for CIs? Do we need a global net graph? Do we separate the tuples? There is a lot of flexibility, and we need to test different strategies. And also, do we have a suitable data set for training the model? You need to remember that I think a big success of the weather forecast model come from the reanalysis, which is observationally informed. And of course, when we move to sea ice and ocean, the amount of observations that we have decreases. And yeah, this brings me to ORAS-6. ORAS-6 is the sixth generation of the ECMWF ocean and sea ice reanalysis that we are now developing. And I think our first approach will be to try to learn the ocean and the sea ice from this reanalysis. And we hope that with the additional informational context that there is here, we can get skillful ocean and sea ice prediction. So ORAS-6 is based on NEMO-4 with the SI-cube sea ice model. It's an hourly product forced by ERA5. It has a 3D VAR, but it's also framed with an ensemble. So we have an ensemble members. It spans reasonably large time scale from 1950 to present. And also it will be used to force ERA6 when it will be run next year. So yeah, it's nice to have a consistent data set, also planning a bit ahead with the new developments in the atmospheric reanalysis. We assimilate oceanic and observations and sea ice concentration. Now, towards modeling the 3D ocean with machine learning, there are many challenges that we see. So the first one is that the ocean has complex geometry and coastline. We have limited resolution and observational constraint in our ocean reanalysis, so just 1/4 of a degree. We have varying time scale. The surface evolves much faster and it's much more coupled to the atmosphere than the deep ocean. So we need to frame somehow this learning problem by separating the time scales. And also, yeah, it's very likely that the very long dynamic time scales of the deeper ocean will not be able to be captured by any reanalysis. So the approach is to customize our training and roll out specifically for the ocean. We want to design a specific graph that takes into account the ocean coastlines, but also the bathymetry. And also we are thinking if it's worth simulating the full 3D ocean for all our applications. So do we need the deep ocean for weather forecasting? Probably not. Probably we can survive with the surface. But yeah, at longer time scales, for example, for seasonal prediction or beyond, the ocean might become important. And yeah, just to put a few faces and names here, these are the team that's working with me on tackling this problem. It's a mixture of machine learning scientists and domain scientists. So hopefully you will hear from us soon regarding this. There is also thinking that we're putting in coupling. So it's not obvious what coupling means with these machine learning models, because in principle, you could train a big ocean and atmospheric and sea ice model altogether, having a big loss function and try to minimize them altogether. But we recognize that there is value in having separate emulators and then coupling them, and this brings flexibility. So the design, for example, of the OLAM model by NVIDIA is towards, I would say, traditional coupling. It's still unclear what we will do in the context of AIFS. I think, again, it will depend on the application. Now, to conclude, I want to mention that for now, what I showed you here is basically learning from predictions from analysis. So what we do, work, yeah, okay. We go from model space to an internal representation, we advance in the future, and we go back to the model space. But there are many more options, actually, and a lot of them are being explored currently at ECNWF. For example, you could learn the observational space and basically emulate the 4D bar. This is interesting also to build new observational operators. And yeah, there is a lot of effort in doing that. And it's very nice because they are differentiable. But there are also nice activities, for example, learning directly from observation, the model state, and learning to predict directly the observations with the current observation. This is very promising. I just want to show you this proof of concept. So here with the transformer, we are learning to evolve satellite observations of 12 hours into the future. So completely replacing the 4D VAR and the model. And I think this is can be very valuable, in particular for the weather problem. Here there is an article on our newsletter that explains what our current approach and efforts. And of course, this is all very experimental and working project, but we are also tackling this type of problem and not only the emulation of our current systems. Finally, last couple of slides. I think it's important to mention that all this has been developed in the Anemoy framework. Now, this is an ocean audience, so please don't confuse Anemoy with Nemo AI. It has nothing to do with it. So I think it's just an unfortunate name choice, and the logo, it's even more confusing. So yeah, two separate things. So what's Anemoy? Anemoy is our, basically, it's a set of tools that we are building together with our member state that we can use to basically develop our machine learning applications. And we can use Anemoy for preparing the training data set, conducting model training, building graphs, a registry for dataset and trained models. We can use it for inference, and also it has a very nice interface with the verification software at ECNWF so that the forecasters can look into that. This is all open source. It's currently under development, so like the documentation is very shaky, but the idea is that, it will become established in the next years and also used at the European level by the member states that want to train their emulators and ML weather models. And in that respect, I just want to flag this very nice work to show what's possible within Anemoy. So here, this is work led by Met Norway. And what they do is basically regional modeling with machine learning. So they modified the graph and the training scheme of the AFS to increase the resolution over Scandinavia, so to resolve better the orography of the model, and you can see here basically how the flow seamlessly transitions from a low resolution to the higher resolution. And basically they train the high resolution part on the analysis of their forecast, whereas the exterior is trained with ERA5, and the pre-training can be done completely on ERA5, and just the fine-tuning is done on this high-resolution mesh. I think it's very cool work, and there is a preprint out. And with this, I thank you for your time, and I'm happy to take questions.
Thank you, Lorenzo. Questions for Lorenzo? I don't see any CRs. I'll go with Gökhan first.
Yeah, I have a sort of chicken and egg question, I guess. When you create your ocean data assimilation,
right? Or
Yeah.
whatever, ORA, I guess, ocean.
Or a 6.
Or yes, you are actually forcing it with ERA5 data sets. But we know that ERA5 has its challenges, right? It's not balanced. It has moisture balance issues. It has heat flux balance issues. It has really warm temperatures in the Arctic. Wind speeds are who knows what. So how are you, I mean, when you impose that, you know that there are known issues with ERA5 atmospheric reanalysis, and you are imposing it onto an ocean product, which will try to do something with that. Is that the best approach going forward, or do you have any other alternatives?
So at the moment, this was the surface variables which are simulated. Solution. It's on. Okay, cool.
Griffiths?
Stephen Griffiths, one mic.
Steve.
Thank you for the talk. Is there a mic that works?
The problem is with your hand.
I'm turning it off when I touch
No,
it.
when you touch it, you do something.
Stephen Griffiths, the mic is on. Stephen Griffiths is in the auditorium, yes. Thank you for the talk. You mentioned that you hope to use, have some neural net climate model with an ocean included, I guess, right? I mean, that was one of the sentences that I saw there. What are you going to do? I mean, this is more philosophical. What do you think is the feasibility of that with deep ocean? Very little data down there, models that drift very differently if you want to train your neural net or whatever with models. Is that feasible? I mean, the weather problem, you have so much more data because everything, the long-term climate, I mean, climate change and so forth. I just want to get your thoughts on that.
It's definitely a much more difficult problem, in particular at the deep ocean. And I mean, our approach is really to build step by step. So we are, first of all, weather forecast center. So we are starting from the medium range, and then we will increase our time scale. So I think we don't have yet, we don't have the ambition to solve all these problems altogether. We are having a look at the performance at the seasonal time scale. I think it's a matter of one thing are models for understanding, but we also use models for making predictions and for providing services. And I think for providing services and informations, we don't necessarily need to have a full description of the 3D ocean, for example, for providing a seasonal forecast or decadal forecast. A lot of these artifacts or a lot of this information about the deep ocean could be somehow present already in the Argo float. There are definitely limitations, and the problem is much more difficult than for the atmosphere. I don't know if we will have, if machine learning can give us the benefit compared to a traditional model. I think it should also not give a disadvantage. I think that's my view.
Hi, Andrew Shao here. Thanks for that really nice overview of what ECMWF has been up to.
One question I had was the jump in the forecast score. Is that primarily because you have a larger ensemble member? Is that related to the way that you initialize it differently because you can input more stochasticity in the system? Or do you have any insight into why that jump in the forecast score is there?
In the, you mean, so do you mean this jump in the 2000?
No, sorry, the next slide.
The next slide, yeah. Okay, at day 6, you mean, and day 10, the jump. Now, this is a deterministic forecast, so it has nothing to do with ensemble. It's just a more skillful prediction of the atmospheric evolution. I think there are some, for certain metrics, the fact that we have a smoother field at lower resolution and because of the neural network smooths a bit, also brings benefit in some scores, in particular for the precipitation. But in this case, for the geopotential light, I think this is a real improvement in skills compared to the model. And it, like the system is initialized from the same analysis. It's just that it somehow leveraged on the observational constraints of the ERA5, I think.
2 more questions, one from Paul, then Peter Jim will be the last one.
Paul Spence from the University of Tasmania. Thanks for the great talk. I'm pretty naive on this whole world of machine learning, but my general understanding is that if the climate system is really going to change and we're looking at longer time scales, you know, you have to train your model on this new state. For example, if ocean stratification changes or whatever. But you're sort of hinting that, you know, with your that extreme precipitation in the United Arab Emirates, that maybe that's not the case, or like, do we? Well, so we'll always need a physical model to provide to train the system, and in that case, what the machine learning models are really there for improving the skill or making, you know, more ensembles.
I think so. Like at least for the atmosphere, it's not just an emulation, and that what that test case with better skills in the precipitation. I think what it shows is that somehow we are not sure like exactly how and what are the correlations, but that the model learned something about the physics and it's able to a certain extent to extrapolate. Then, of course, like what I showed here with running the forecast in future climate, there are still issues, like it cannot extrapolate indefinitely, so it doesn't do any magic there. I think so what I want to say, like our understanding is that we just need to try and see. So there is not good recipe. What we do now is to regularly fine tune the model on the analysis in the most recent years, and this helps. But yeah, in principle, if there is in ERA5 a climate change signal already, the model could learn something out of that.
Can you go to the next slide?
Here.
Right. So you said blue was improving. So the bottom line says climatology, and it's nearly all red. So what's happening? Is the climatology getting worse?
No, it's just this is really for single forecasts. So it's like how good is the climatology compared to an initialized forecast. And of course, it's red because, first of all, there is a climate change signal, and it's red because it's not initialized. So yeah, it's not that the climatology is getting worse. It's just that the climatology doesn't provide a good forecast. I think that's the way of seeing this.
So this scheme does provide a decent climatology?
I mean, you could build a climate, like the climatology is built on the analysis. So yeah, it's like the climatology is the same. It doesn't change. It's just the skill of the forecast.
Okay, let's thank Lorenzo one more time. We now have time for it's a 30-minute discussion. And I want to thank again Drew for being our note taker. Let's thank Drew one more time. Thank you so much, Drew. We'll put up the next set of questions. So this is following up on yesterday's discussion. Is this the only microphone? No. Oh. Can you put up the slides for the questions, please? Okay, I'm not gonna read them. This is the continuation of yesterday. So yesterday we had these questions. That's part 1, 2, 3, 4. Okay, I hope you remember, but I can leave here for like 30 seconds. There you go. Thank you. Okay, now next one. Okay. Anyone would like to start? Dan?
Thanks. I had a question partly inspired by Andrew's talk about the needs for AI ML training and how they might differ, in particular for saved data and output of models, how that might differ from what we've saved traditionally. And I guess particularly thinking about if there are ways of doing data compression or dimensionality reduction that can be more efficient. So for instance, maybe we want to simulate a climate model for 100 years to get a bunch of different flavors of ENSO variability, but maybe we don't need to save all of the fine scale eddy features in order to accurately represent that. So are there opportunities there for us to better output models in order to facilitate AI training?
Yeah, so I'll respond to that. I mean, I think that it is really interesting because it depends on the application of the ML model, right? If you're trying to build a surrogate and you're just doing UV-TNS and you want to predict UV-TNS, there's a question of, okay, like, what do you want to do? I think that there is really interesting things to think about though, like, how do we make the problem simpler for the ML model so that training is faster, so it doesn't take 2 weeks to train a full surrogate. And I think that that's where some of these statistical techniques are really key, right? Like, what is the novelty that is being added to the neural network if you include this data set? And I think it's really hard to do that a priori without having done that as kind of a test before, right? Like, you need a kind of hero run to have saved a lot of data, and then you can do that test to estimate like which of these samples was important. And there's machine learning techniques to do that, but then our job is to say, now, if we know which samples are more important or less important, can we come up with a way to do that while the simulation is running? So we know, yes, drop a data set, no, don't drop the data set. And that's a really interesting problem that I've not seen people work on yet.
Arne Biaster. I would like to come back to the question that Stephen raised about the long time scales, the deep ocean. And I would like to hear the thoughts from the other speakers on that. Here we are not facing only sparse data, which will not be cured in the future, at least on a long time scale. We are also facing the fact that we are looking at very small scale signals, sea level rise, trends in the deep ocean, which are way below our typical model trends and errors that we are facing. So I'm wondering if that is a general problem, or if that will be solved one after another when the timescales increased in the ML-based approach. I see there's already an answer.
So one thing that we've seen just in general for machine learning is that oftentimes machine learning does a way better job of learning the errors or perturbation than it does the actual state. And so I think if you apply that to the question of the deep ocean changing, right? Like there is an underlying kind of like slowly changing state. But if we care about potentially, if we think about the long climate scale as a perturbation, it's potential that we would be able to predict, you know, from high resolution climate simulation or something, what the perturbation on top of that and how that projects onto that, and or predict the things that project onto that slow anomaly. So I think otherwise the machine learning model is going to do the easiest thing and say there is no change because over the course of 1,000 years of a PI control, it didn't fundamentally change. But if we can learn to do the time varying perturbation on top of that, that's a potentially much more learnable problem.
Yeah, so I think Andrew said pretty much everything I would have said. So I think we should acknowledge the fact that, yes, we do have slow timescales and we have a lot of timescales, right? So the question is, what is the machine learning model is going to do? It's not magic. It's going to learn from data that you give it. Now, again, it's extremely good at predicting changes. And so I think the way we design it is more important than anything else. And I think assuming that it will be magic and grab everything, that's not right. Actually, we did show that getting the climate change signal, if you learn on PI control, it will do a terrible job. We actually published that, just come to make a point. But then if you have enough additional data where you capture a little bit of those trends, you don't need a lot of data to superimpose on it. So I think everything goes back into the design of understanding what it can do well and what it will never be able to do. Now, of course, we will never have enough observations to do all of that, right? So we're still heavily relying on the model world.
I saw Anna first.
Thank you. Yeah, Anna from the Met Office. So my question kind of touches at the fact that we don't have enough observations. And related to point 7, could we, for instance, try to think together, perhaps this has already been discussed, of what would be the set of models that would be the benchmark to be used for training machine learning, and would using stochastic models complement the fact that there isn't enough observations in the model, in the real world? Could we set the targets for the range of parameters that those stochastic models should be looking at? Does that help in any way, the fact that we don't have enough observations in the deep ocean?
Does anybody want to comment on that one?
Is it okay?
Yeah.
I think related to that, Theresa, GFDL, when we train these models on like a champion model, like you said, and then we try to create ensembles for prediction, how are we making sure that we're getting a good spread in those ensembles? Do we need each ensemble member to be trained differently, or can we do perturbations to still get the sort of multi-model mean that's pretty reliable from physics-based climate models?
Just questions after questions.
Hopefully somebody will chime in, maybe to relate both of them. So I think maybe it's an easy answer to your question, even though you have a very hard question. Benchmarks are critical, right? So I think it will be great to have a common set of, data that people can use, but it always comes back to the problem that you're trying to solve. So if this community here in this room identifies a couple of questions that we really think will be a game changer, right, for the community and for moving ocean modeling forward. And of course, we're not going to be able to do that in a few minutes. But if we target a couple of things and then try to break it down, then maybe we can identify a few data sets and a few models that we should all be using and at least try to evaluate on. So I think that would be wonderful, I have to admit. The second question for how do you actually generate ensembles? That's a good question, right? Technically, again, CMIP was designed with this idea that the ensemble mean will actually be your best guess scenario. And when you come from weather, then again, we have a different setup here. Right now, I won't say we have an answer because we have no clue. We're just starting. So I think we're trying to generate, different weights from the neural network to figure out what's going on. We're doing different initializations. We're doing different surface forcing with noise and all those kind of things to actually try to see what is the best answer. I don't know what it is, I have to admit.
This is Bob Hallberg. So if I think about machine learning climate models for long-term projection, and I put on the hat that I wore a couple of years ago as an IPCC author, we were only able to make confident statements if we could come up with multiple lines of evidence supporting what we were finding, broad consistency and other things. Machine learning models, some of them are kind of tied in, they're kind of extending the basic tools, but others are basically black box extrapolators, and no one has any idea what magic makes them work for certain timescales where you can verify them. But for the climate projection problem, we can't wait 80 years to verify the prediction of the models. And we are asking the people of the world to make big changes, perhaps if they care about climate change and want some of the things that might happen not to happen. We're asking them to take it on a certain degree of confidence that we actually understand the details of what's going on, and hence we have a certain degree of robustness in what we're doing. In my mind, this is something where this is a real challenge in particular for AI, where the public experience with AI comes from asking ChatGPT to make some statements, and it comes up with ludicrous things that are demonstrably completely wrong and very amusing. We saw a great example yesterday. So how do we think about the application of machine learning and artificial intelligence to the climate projection problem in the ocean in a way where we help with this, basically deal with this verification, this understanding, these multiple lines of evidence issues to deal with the projections that they're making, when by construction they seem to be black boxes where we're kind of skipping all that and moving ahead quickly because you have big computers and they just take care of it all for you.
Just that I don't think all of them are extrapolators. Some of them might be, but most of them are interpolators. Does anybody want to answer Bob's question?
No, I think I don't have a good answer. And yeah, the answer is let's wait 80 years and then we talk again about it. But of course, I think...
Can I ask ChatGPT to come on?
That too. I think, to me, the benefit of using these models is that they are much more flexible in incorporating observations. So I think in that sense, even though we may not understand all the correlations that happen during the training because we didn't code them with equations, I think the fact that they learn on observations could, not now, but now they learn on reanalysis, but the fact that they are observationally informed could bring some benefit and confidence. And I mean, in principle, if we get a perfect emulator of a climate model, then it will be as good or as bad as the climate model. So I think I don't know if, and it might be faster than that for sure. So I think there is still benefit also if we can just emulate what we already have, and we can definitely do we can have definitely a better understanding by training these models. We can understand what's important, which fields are worth being captured, and which fields maybe we don't need. I think, yeah, I don't know. I wouldn't exclude them altogether just because we need to wait 80 years for the verification.
So I think, yeah, kind of following up on that, I think one question is, what does it take for us to actually trust a climate model, a numerical model, right? And you know, when I started, a lot of people say, all those complex GCM who believe the things that they're in them, even though they're solving equations, they're full of if statements and tricks and parameterizations, right? I don't believe that, just to be clear. But, right, we hear that a lot. And so I think at the end of the day, you know, as a community, why do we trust climate models, right? Because they conserve the right properties. They, you know, again, they will in principle, right? And so what do we want from our emulators to do? And I think those are the check mark that we have to have, right? That if you impose a surface flux, you know, at the surface of the ocean, and you integrate what the emulator has done, then it should be taking up as much heat as you put in. So I think all those checks, we need to make them. We should not just look at the score and just feel happy about it. So I think that's definitely on us to make sure we have the right metrics, both for the climate models and those emulators that's supposed to do the same thing. But yes, we won't know in 80 years exactly if we get it right. Same for the climate models.
I think I'd like to kind of ask a related question, or maybe I have one answer and a related question, which is I think that we trust climate models when we understand the physics or the processes that they represent. And so what I'm wondering about with all these advances with AI-based prediction, I'm wondering why are a lot of the best advances associated with models that seem to have or completely based on neural networks or deep learning rather than being some blend of physics models and AI? Because I think if I was just to sort of dream about what the best possible climate model might be, it might be one that resembles a traditional model in that it solves, you know, it has Newton's laws of motion embedded in it and all of the physics that we know is true, but just is extended with AI. And I think the answer is probably, it really has to do with practical realities rather than, you know, scientific motivation, right? It's just because it's really hard to do that with software that we have now. I'm wondering what other people think.
Yeah, Andrew Shao here. I'm just going to follow on what Laura was saying. So there is an excellent paper that was published in a philosophy journal that has one of the best titles ever. I won't say the full word, but ChatGPT is BS. And there's a very complete definition of what BS actually is. And essentially it boils down to that GPT has no values, right? Its goal is to give you an answer that you're happy with. And so there is no values built into that, right? And there's no safeguard in that. But I think implicit in what, especially what Laura is saying, right? When we build our GCMs, we actually build in our values into those things. We say that conservation is important. We think that conservation of heat is important to be able to predict the climate model accurately. And I think that that is just a fundamental distinction. And again, it's like, you know, without understanding how to inject a value into an AI, like, I don't think we can trust it. I think but we can do it kind of indirectly, right? The multiple lines investigation. If we take an ensemble of AI surrogates and they behave similarly to the non-AI ones, is that enough evidence for us? And that's a value judgment that we as humans have to make in order to do that.
Yeah, coming to the point why neural networks work very well, I think the way we see at ECNWF is not that they do any magic. I think it's just the first time that they could leverage observational informed data set. And I think that's where we see the advantage coming from. It's not that the neural network is more powerful than the physical model. It's just that it could leverage very well. It's an architecture that's well suited for leveraging an observationally informed data set. And I think these are where the skills are coming from, at least for the atmosphere.
Okay, any follow-ups on these questions or new ones? We have a few more minutes left. Gökhan, there's one question on your side.
Jeff Stanley, CCCMA. I really agree with Bob, your point. And just to preface, I'm a machine learning novice or non-user, but I think that, Bob, your point about trusting these machine learning models, I certainly think that we can't go into them and understand them in their full complexity, but we can perhaps treat them as scientific objects of study. So understanding the inputs and the outputs and doing experiments on them as if we were scientists and it's some other physical system that we've never seen before. But like, imagine we voyage to the edge of the universe and we reach and we discover there's a machine learning black box out there, and we can start to probe it by the same sorts of tools that we've used in science this whole time. And that might be a way that we can harness trust in them.
Is that AI assistant working actually right now? I'm scared because that keeps writing everything, right? We say. Oh, it's okay. We are safe? Okay.
Then we'll do the photo.
Alistair.
No, he can go. I've been chatty. Well, my question is, I think, kind of just as a user. So we're always going to higher and higher resolution models, but we can't run ensembles because they're too expensive. And then we never know what the signal to noise is, or if it's just like, internal variability. But it seems like that's you guys are presenting applications where you can create this, I guess, as an emulator that is really fast at doing ensembles from using your model state. And is that easy to set up? Like, can we make that as a usable package for people? Because that's really what I want, is to be able to it'd be the easiest application for me, essentially. Does that make sense?
Yes, so if you just make that.
I mean, again, we're also not magic. It requires people and effort, right? Obviously. So there is so much we can do. But yes, that's the goal. First, we're already putting the weights of those models online. So anybody already can start using it if they want to and do, forced ensembles and things like this. There's more to come. But yes, it requires people.
Just 2 comments. One is, I really actually believe that it's going to be possible to formulate these machine learning models in a way that's consistent with the way we build our models now, i.e. satisfying the laws we do understand, which should alleviate a lot of the concern about whether they're usable for climate. The other thing I would like to say is that there's a very interesting diagram which has which I think in the future will become very dominant. There was in the ECMWF talk from Lorenzo, where he had an observations to observations prediction path, where there was no modeling, there were no equations, it was just predicting what satellites are seeing from what satellites saw. And if you think about what that means for the future, if we could do that for the ocean, predict SSTs, sea surface salinity and sea surface height in the future from what we can see now, that seems to me like a pathway for us to actually to get around this issue of not being able to observe the deep ocean, because ultimately, at some point in the future, everything we see at the surface is a function of what we saw, didn't see in the past in the deep ocean. There's been a lot of work in the past about inversion method, that we saw from Patrick. The inverse problem is solving that problem. We've got sparse observations, i.e. mostly at the surface, and from that we can invert for a state for the whole ocean. So if you put all this together, at some point in the future, I think that there's actually, this is what ML is going to enable for us. It's something where we can actually do something for the deep ocean. And if we can do the deep ocean, we can go beyond that and start looking at climate as well. So I'm actually hopeful. I'm not saying we can do it now, but I just think I can just see a pathway where that's all going to come together.
You can cut all the observational funding in the future.
It's all about observations. I'm sorry, but I'm also saying. But the other part, the first point was that as a model developer, I think that it's really important that we actually are engaging the ML methods and making sure that what's happening in the ML world is satisfying what we want models to do. Right now, they're doing increments, predicting states in a non-conservative way. I think that's something we should try and change. We can do it conservatively, for example, and then satisfying other principles like energy conservation and all that stuff. That's what I'm saying. I think there's a lot of opportunity for coming together with this other community and bringing the observations in term as well.
Does anybody have a last comment?
I'll be fast, but I wanted to make a comment on really the last two topics we discussed. And this inverse problem, when we use machine learning, we might be able to solve things where you used adjoints and it took forever to write them. It becomes really easy. And an extension is the fluctuation dissipation relationship, which really would help us to validate models like into the future, because it says, you know, how does your system react to small forcings? What's the response on long time scales? And so maybe sort of an extension of the inverse problem is if really machine learning can be used to solve problems, inverse problems that we previously couldn't do, it might actually also help with the climate change problem, the validation of models. Thanks.
Thank you. Let's thank the speakers again one more time. And we'll do the group photo right outside right now, so don't disperse.
So we'll start a new session for this afternoon about the numerical methods for ocean and sea ice models. And we start with an invited speaker. So it's Carlin Mehlmann from Magdeburg University in Germany. And she will talk about sea ice model. So.
Okay, hi. Okay, hi everyone. First, I wanted to thank for this really nice invitation. So I feel really honored to give this presentation here today. And I also want to emphasize that I never experienced this encouraging young researchers to participate so much as in this workshop. So I would wish that we can kind of continue this vibe, and I really appreciate this kind of organization. Okay, first I'll just briefly introduce my background. As you can see, I'm from the Institute of Analysis and Numerics of a university. So I'm working in the mathematics or Department of Mathematics. I'm trained in numerics and I did a lot of research in numerics. So I developed a new numerical discretization for the sea ice model used in ICIM. It's a Coursera-VR finite element. I called it, to make it more appealing for the community, the CDCrit, which is because many people use this Arakawa stuff. And to make it more familiar, I called the Coursera VR element a CDCrit-like discretization. And yeah, I think with this development, I started kind of a vibe in the ICS community to think about how can we choose our numerical methods in such a way that we represent the physics as best as possible. And this development was picked up by other models like FISM or MPAS. They tried this CDCrit, and I think also NEMO tried a CDCrit discretization out. Okay, so this is the background, but today I will not talk about numerical developments or numerical methods. So, I mean, it will be a numerical method, but not about pure numerics. So I hope you're not disappointed, but if you're interested in all of this discretization of sea ice dynamics, you can just contact me in the, in this coffee break, and I will give you some hints or can answer some questions. Okay, so today I will talk about a modeling approach. And the modeling approach, I'm not using this pointer. So the modeling approach aims to include small-scale icebergs into large-scale sea ice models. And the reason for this is that this is currently not done in climate models, and there are of course, some small icebergs around, for example, in Antarctica, which are quite important for the climate, and which also important for the sea ice state in the climate model. Because let's say in the Southern Ocean, the creation of landfast ice is due to this iceberg grounding, but this kind of effect is not yet included. And this talk today is about how can we, based on some method, so it's more as a method, it's not a full model, how can we include these icebergs in large-scale sea ice models? Okay. This was the long introduction. Okay, one aspect where this icebergs are of interest is the so-called ice melange. Ice melange is found in front of glaciers, and it's of interest because these icebergs, they store a lot of fresh water, and this, say, yeah, ice melange affects the glacier and fjord system. And yeah, you can also have some so-called butt dressing effect for iceberg breakoff from glaciers. So this is why this is, let's say, an interesting thing which we, just remove this mouse, yeah, which is worth to model also in climate models, right? And this will be kind of the aim of this talk today. How can we develop, now the numerics are coming in, an officially numerical method to introduce ice melange in climate models? Okay, some background. Of course, I'm not the first person who tries to include some sort of ice melange. For example, of course, you have some physics, you do some observations, and there are some specific effects which we want to include in a model. And this can be done, for instance, by some parameterization. Yeah. Then there's a paper which models based on particle models the ice melange. But for that, we would have a full, like if we want to introduce this in a climate model, we would need a full representation of the sea ice and all of the icebergs with particles. And I think it's interesting to test, but of course, in the first step, it's numerically expensive. And now if you want to address the whole modeling community and say, hey, let's just throw away continuum and just take all particles for sea ice, maybe this will be a big effort, right? But this is, of course, one thing which one could do. And the second approach is we can model this ice melange in a continuous way. There are two approaches in the literature. One is we formulate a single continuum, which is called the ice melange. And there's a full model how the dynamics of this ice melange works. And you can, of course, have some thermodynamics. And the second approach, and this is kind of the idea which I will pick up, is to formulate sea ice and icebergs in a joint continuum. And this has the advantage of doing this is the following, because we all have sea ice as a continuum in climate models. And if you want to introduce, if you kind of add on the icebergs in this continuum, it's quite appealing, right? Because we don't have to change the whole sea ice dynamics or the whole sea ice models. But so the idea is, I like the idea, it's quite cool. But there's one thing which is a bit, which makes this approach difficult, and this is the model resolution. Because my big aim is, I want to have icebergs in a climate model. And if I'm going with the continuums approach, I have to choose a model resolution high enough to model the small icebergs, right? And then if we want to have, let's say, projections over 100 of years, it's quite hard to do this with a 1 kilometer resolution. So this is why I'm proposing something else. Okay, and this is not only that we have a high resolution. The thing when it comes to sea ice, and this is why I'm a big fan of sea ice dynamics, it's a highly nonlinear equation, and solving this equation is challenging. And it's it's really cool. You can design cool solvers to do so, but this equation becomes more and more difficult the higher the resolution is. And the reason for that is that ice is assumed to be, let's say, it's a plastic material. It's modeled as a viscous plastic material in almost all climate models. And the higher the resolution, the more we call this linear kinematic features, like the more, maybe an easy translation is like cracks or structure in the sea ice is appearing. And this is why solving it at high resolution, this continuums equation, let's say if we want to go for icebergs like 100 meters is terrible. Yeah, so this is not what we want to do. And so what is the aim of this method I'm presenting today? So I want to represent icebergs, which have hundreds of meters in form of particles in large-scale climate models. So I will nest icebergs as particles in a continuums approach. And I'm now presenting how do we have to modify this momentum equation, which is used, so this is the viscous plastic model. How do we have to modify this equation in order to account for these icebergs, which are actually living on a subgrid scale? Yeah, so you can think of, we have a climate model, let's say a grid box is 20 kilometers times 20, and there are little icebergs, a lot of little icebergs in this grid cell. And of course, these icebergs, let's say if they're grounded, have a big effect on the ice motion. And this is the idea. Exactly, so how I'm going to do this? I'm following this approach of Vancouver and Holland, which I presented previously. And I'm treating ice melange as a joint continuum. So this is the assumption. I'm assuming ice melange is a joint continuum building up of sea ice and icebergs. And by doing so, I'm interpreting icebergs as thick and compact pieces of sea ice. So this is kind of the assumption. And this is also what Vancouver and Hollande did in their paper when they build up the continuum. Yeah? So I'm following this idea. And now I'm going to present how can we realize this modeling idea in the context of the viscous plastic model. And here's a little like idealized sketch. So you can see on the right-hand side, these are our little icebergs. Then we have the sea ice continuum, and this together will be our ice melange. Yeah. Okay. So how does the model looks like? So this is a, let's say, modification of the viscous plastic sea ice model. And I'm using this because the aim is how can we easily introduce the icebergs in a sea ice model and climate models. Yeah, so this is why I'm using the viscous plastic model. So I don't know how familiar you all are with sea ice models, so I just dropped some basics. So sea ice is modeled as a two-dimensional continuum. It's between, of course, you all know that, between the atmosphere and the ocean. And this is why also the ice melange is a two-dimensional thing. And it has a two-dimensional velocity, yeah, the ice melange velocity. And then this is also coming from this easiest version, I would say, of an ice model. The ice melange will be characterized by two unknowns, two variables, the thickness and the ice melange concentration. And I'm building up the thickness and the concentration by, and now this is the idea of deriving a joint continuum, by either accounting for sea ice, so P is a particle. The particles are round, so they're round-shaped disks. I choose round disks because this is the cheapest numerical thing when it comes to particle model, what you can do. Every particle is equipped with a radius, which I call R for radius, and a certain height, yeah? Okay. And now coming back to the ice melange. So ice melange has a thickness. The thickness is equal to the thickness of the sea ice if on a certain point in space no particle is present. And if there's a particle is present, it will be the thickness of this particle thing. And the same is done for the concentration. So I'm using the ice concentration whenever there's no particle. And if there's a particle, of course, the whole point in space is kind of covered with a particle, with an iceberg. And this is why I set it to 1. So this is how these two tracers are defined. And then this is the viscous plastic modification of the viscous plastic momentum equation. So here it's interpreted as a momentum equation for the ice melange. So in the upper part, you can see the momentum equation. On the left-hand side, we have the change of the sea ice melange in time. Then in front of that, we have the mass of the ice melange. So the H, again, includes both the mass of the icebergs and the mass of the thickness of the ice. And on the right-hand side of equations, of course, we have the external forces, atmosphere, ocean, and then the internal rheology, which kind of deforms the ice melange. And now there's the important point when it comes to modeling icebergs in the framework of this viscous plastic model. So the viscous plastic model has almost no tensile strength. This means, and I just showed a picture now. This means if this is on a continuums level, if I plug in an iceberg and then I put along a strong wind to the wall or to a glacier terminus, you can just see that the iceberg is just deforming. There's no resistance against this force. And in order to introduce some tensile strength in the presence of an iceberg, I'm modifying this rheology. And so this is equation number 1. So on the left-hand side, we do see the stress tensor. And on the right-hand side, there are the so-called, this is the strain. I can try to do this, but people struggled. Yeah. Okay, this epsilon dot is the strain weight tensor. So these are the derivative of the change of the velocities. Then here, this is kind of the trace of this strain rate tensor. And then in red, we see the viscosities of this model. The viscosities are set in such a way that it's assumed to be a viscous plastic material. So these viscosities are derived such that they're lying on an elliptic curve. Yeah, so this is the yield curve. And these viscosities, they are modified with the tensile strength. And also here, P is the so-called ice strength. This is the resistance of ice towards deforming. And also this ice strength is modified here with this tensile strength. And now the question is, of course, I just don't do this. The question is, of course, how do we assess this tensile strength? And the tensile strength is, of course, not existing if there is no iceberg. And in the presence of icebergs, the tensile strength is related to the thickness of this ice melange and some strength parameter P star. Okay, this is how the model is set up. We've seen we need this. And where's this idea coming from? So this is the viscous plastic yield curve of the sea ice model. And we can see, so in blue, this is the standard yield curve. And you can see that on the right-hand side, the blue ellipsoid is not crossing this direction. This means there's standardly almost no tensile strength in the ice. And this, by including this tensile strength, we actually just shift the ellipse to the right-hand side, and therefore there will be some resistance against, let's say, volume stress in the model. And this is not new, so people have included tensile strength for different sort of applications in ice models. For example, for modeling landfast ice, so this is by Koenig and Holland in 2010, or by people modify, there's a lot of discussion. What is the correct rheology? How should we choose our parameters? And one idea to improve sea ice forecasts is actually to kind of introduce some tensile strength for some ice regimes. Yeah, and this has been, for example, so this is not a full list of the literature, done by Ringeisen in 2021. Okay, just to show, okay, if we do this, it works. So we have, if we include some tensile strength, we can prevent actually icebergs from deforming. If we include tensile strength, if there's a divergence wind field, icebergs can stay together. So this is just, and also for shearing forces, yeah, the thing stays kind of as a block and is rotating. So this is just a proof of concept why we should introduce this tensile strength for modeling the icebergs. Okay, but of course, I'm not working on a full continuum. I'm kind of combining particle and continuums methods to make it, to make icebergs available in coarse-grained resolutions. And how do we now discretize this modeling idea? So we can assume the large K is a grid cell in our model. And now the idea is kind of we're deriving an average iceberg concentration and an average thickness distribution of the icebergs. This is just done by checking how much of a grid cell is covered with particles. And this is just done in equation number 4. And then the point where we couple this two methods, like the particle and the continuum, back to this joint continuum, which I call ice melange, is done by just adding the two ice concentrations, or adding the two derived thicknesses. And this, let's say, ice melange tracer is then entering the momentum equation. And the idea is the following. So, I mean, the momentum equation tells the melange how is the velocity changing in time. And by just creating a joint continuum of icebergs and ice, the joint mass, which is used in this momentum equation, kind of tells how the velocity is changing. So that when we calculate the velocity, this velocity actually sees both, the integrated iceberg mass, and the integrated sea ice mass. And of course, we also have the tensile strength. And the tensile strength will be present. And this is now, I mean, this is not a full model now. Yeah, it's just a method how to do it. And then I just artificially choose some switch off, switch on of this tensor strength. And so far, I just said, okay, the idea is if the density of icebergs in a grid cell is large enough that it will be matter on a large scale, this tensor strength should be present. But there need to be a comparison to observations to see how this tensor strength is switched on or switched off. But so far, I just said, okay, if I have a grid cell and it's densely packed by particles, once a large particle just fills this grid cell. So this will be, in my definition, this is dense, but of course, this needs to be adjusted. And once, let's say we have enough icebergs per grid cell, this tensor strength will be active. And then there is this point that all of these particles are single icebergs. And actually, you should have a strength, like a resistance against the formation on the iceberg itself. But I say if there's no sea ice, there should be no strength in the cell. So they should be allowed to travel, these icebergs. Yeah, because there's nothing, they're not frozen together. And to account for this, I'm weighting the whole term with the ice concentration. So the more ice is in the cell, and the more icebergs, the higher is the tensor strength, which is also active in the model. And then I also included some constant C, which is kind of a tuning parameter to say how much of the tensor strength should be active. And so we can see that in this little picture on the left-hand side, there are icebergs, but there is no sea ice around. So these icebergs, under divergent wind, they can just travel to the left and the right. But if there is sea ice around the icebergs in the cell, this ice and the cell is densely packed by icebergs, these icebergs stay together. This is the idea. Okay, icebergs. The modeling idea is that icebergs can actually interact on a subgrid scale. So if two icebergs meet each other, they should not drift over each other. There is some collision. Yeah, and also important, so I'm implemented a particle and cell scheme. So in the momentum equation, I'm calculating how does this continuum, which I call ice melange, which velocity does it have? And the icebergs are attracted with the velocity of the continuums model. Yeah, so it's kind of this is the approach. Okay, and here you can see, I mean, it's two icebergs meet and they can also collide and then they move apart. Okay, so some numerical results. So this is a idealized test case. In this lower two cells, I'm assuming that, so you can see there are a lot of icebergs. I mean, yeah, there are 4,069 icebergs per cell, so it's quite a lot. But this doesn't matter too much. It's more about the qualitative effect, which we can model. So these icebergs are small, so they have a 25-meter radius, but the grid cell is quite big, so we have 16 kilometers. And then we have some ocean drifting from the left and the right to the right. And in the lower two grid cells, these icebergs are grounded, and in the upper cell, these icebergs, they can move. And then I'm comparing, of course, the influence of the tensor strength. So here we see the ice melange velocity, and in the red box, you can see the two cells where the icebergs are grounded. And maybe it's not too easy to spot, but with the tensor strength, this which is on the right-hand side of these two images, the velocity is kind of grayish, so which is almost zero. And on the left side, in the standard viscous plastic model, there is a higher velocity in these cells because there is no tensor strength, which kind of prevents this big fat ice blocks from moving, because this is the interpretation. There's quite some velocity, and this means everything can kind of drift. Okay, and now how does it look like? So this is, I can just say, not optimal chosen time step, but on the left-hand side, we can see, of course, in the upper cell, there were these ungrounded icebergs. The icebergs are just transported, so they're moving apart. In the lower two grid cells, these were the grounded icebergs, they stay where they are. And now there's the important, interesting fact. So we can see that if you have the standard viscous plastic model, and we have no tensile strength, there is no pileup of ice on the left-hand side of this image. But this is what you would assume, yeah? If you have icebergs drifting again, if you have sea ice drifting again icebergs, of course it should stop. It should not just flow through the icebergs. And this is due to the missing tensile strength. And if we have, and this, you could also kind of see this in the velocity, yeah? Because there is some velocity, the sea ice is floating through the icebergs, but still we will have some lead behind, some opening of the ice behind this icebergs. And this is due to the fact that there are different, icebergs and sea ice build a big mass of sea ice. Yeah, this is how it's interpreted. So for the model, it's harder to create a flow. And this is why in the presence of these icebergs, the velocity is slower behind, the velocity is higher. And this is why still a kind of an opening is created to the differences in the velocity. So if we have the tensile strength active, we can see, and this is what is really nice, the piling up in front of the icebergs. And now this is what makes this picture not perfectly a perfect choice. Actually, the icebergs move in the upper cell, but you cannot see it. So this ungrounded icebergs still move, but one could argue, but I think you need observations to really come to a conclusion. If every iceberg is 20 meters, so there's a massive amount of ice in the cell, and the ocean is flowing by 0.2 meters per second. And then how quick should be the response of these icebergs to the ocean? However, there's some constant, and you can tune the ice strength. And if you want these icebergs to move faster, it can just be done. Okay, then there's some attraction tests. So we put some single icebergs in the sea ice, and then there's some the diagonal wind from the lower left to the upper right, and you can just see these icebergs are flowing with the sea ice mass. Yeah, so this is also what you would like in such a model. If they're not grounded, they should move with the overall thing. Okay, so what are limitations of this development? So one of the biggest assumptions, which you cannot ignore, is that the iceberg should be definitely smaller than the grid cell. And they should be smaller, I think, kind of by factor 10. Yeah, so this is what I think. The icebergs are round disks, and of course, if you do observations, icebergs are not round. Yeah, but I'm doing this to make this numerically fast and to have a chance that it could be run in a climate model. Yeah, and there's this threshold for the ice strength, so there need to be some observational data. And I suppose, but I don't know if it's true. I just did it for modeling purposes, that there is a linear relationship between the strength, which is created between sea ice and icebergs, if sea ice is surrounded by icebergs, because I just weighted this for the ice concentration, but it could be that there's another relationship which kind of holds this whole thing together. What are perspectives? So what is kind of cool, I think, is that, of course, we have iceberg particle models, yeah? And so far there are iceberg particle models coupled to climate models, but there's no feedback to the sea ice. Yeah, so there is no stabilizing effect to the ice, and this is an important thing, this is important. It's also important. Someone talked about deep water formation and all of this, yeah, so it's important where we have leads in the ice, like where we have the big polylinear openings. And I think this is the most, so for me, I'm super curious about this, and this is the best on this method, is that this allows for landfast ice modeling in the Southern Ocean. Because so far we can represent, landfast ice is ice, yeah, which is barely not moving. In the Arctic, landfast ice is created due to coastlines attachments. But in the Antarctic, and this is the striking point now, landfast ice is created due to iceberg grounding. And so far this aspect is not in the models. Yeah, and so far, if people want to model landfast ice, they work with this idea of the tensile strength. And we can do the same idea, of course, in the Southern Ocean, but we miss the most important aspect, which are the icebergs. Yeah, and this is why I'm super excited about this approach, because this allows us to include landfast ice in climate models and provide more realistic future projections on landfast ice. And I just picked this study because I just recently, so 2022, it's Van Archer and co-authors, they investigated in a regional model, how can we actually model landfast ice? And what they did, they included icebergs. So they did it a bit similar. They take observations, they check for the iceberg distribution, they check which might be grounded. And if in a certain area there are enough icebergs, they say, okay, this grid cell is a land grid cell. So they're representing iceberg grounding by land points. And I think it's a reasonable approach if you want to do regional modeling. But of course, if you put grounded icebergs as land points in your model, so you kind of restrict it with the model resolution. So then it needs to be a high resolution. And this is, I mean, if you have a climate model which has 40 times 40 kilometers in the Southern Ocean, you cannot just say it's a big island, I think. And this is also what they proposed in this paper. So we need, so this is the first step for a more realistic representation by actually including icebergs to model landfast ice. And we kind of need to include this landfast ice in climate models because we cannot, it's unclear if what is disappearing first. Is it landfast ice? Is it sea ice? How is it related and all of this? And icebergs, of course, they should be able to move. So if we do some climate warming thing, you can have grounded icebergs, but they can unground. And this changes the whole story because the formation of landfast ice is super regional. Yeah. Okay. I will ask for the time. Okay, so this was the outlook, but I skipped this, so I was not sure how long I will take. But I can just also. So what I also did, and this is also a perspective how the whole setting can be done, you could also say, okay, sea ice and icebergs, they are both particles. And you can kind of model the two tracers also by particles. But I think, if you do model development, it's also kind of advertisement that it's easy to include in models. And I think if you're going with this joint approach, it might be harder that many developers pick up the idea. But yeah, I investigated all of this, but we're going to skip this now. Yeah, and I'm coming to my summary. So I presented, I think, yeah, the development of a hybrid ice model. I take the word hybrid because it includes both continuum and particles. And what I think it's really cool about the approach is that the icebergs can be modeled on a subgrid scale. So you can be as coarse as you wish, kind of in your climate model, but including this response. And yes, so it's done in the context of the viscous plastic sea ice model, but of course this can be transferred to any other rheology. It's all a matter of introducing a tensile strength to this rheology. And yeah, these ideas are formulated in a preprint. So this is, I should have emphasized this in the beginning, it's a joint work with my PhD student, Saskia Karl, and with Dirk Notz, who's working at the University of Hamburg. And these ideas are, yeah, kind of written down in this preprint, and I hope it will be published soon. And I forgot this in the beginning. So all of this work is sponsored by the German Research Foundation for Antarctic Research. And this is how I pay my PhD student. Okay, thank you.
So there is one question already.
Yeah, they will not be able to hear him.
Yeah, thank you for a very interesting presentation. Icebergs in your model represent as circular disks, right? In reality, icebergs have very distinct profiles, very deep keels and very high ridges, which result in very different drag from the ocean, from the air, compared to the adjacent ice flows. Is this somehow parameterized in your model?
No.
No.
No, I mean, this is a really, you know, initial state of a modeling idea, and it's kind of checking out how does this work at all? Yeah. I'm aiming for this landface size, which I showed at the end. But I think the question is, so what the continuums model is seeing is an average response of all the icebergs, and then the question is it neglectable? Which form they really have? I mean, this will be kind of for the model evaluation, yeah. So can we get realistic results to by modeling icebergs as round disc shapes? But I think, you know, better modeling it as rounding things than neglecting it. I think. Yeah.
Is there thermodynamics in your model at all?
No, this is just the dynamical part.
Thank you.
Okay. Have a question? Okay.
Thank you, Caroline. Your equation number 5, I think, or 6, you're limiting you're combining the two concentrations and limiting a minimum baseline, like meaning of the combined 2 and 1. And when I saw that, right away came to mind questions about conservation, like does your model conserve mass and heat?
Yeah, it's not conserving.
Even though you're like limiting when you sum the two?
With the 1? Oh, this is standardly done in CI's model. So the ice concentration. So what I did, I neglected all the thermodynamical effects here, but usually there's freezing and melting. And I say if a crystal is covered with sea ice and more sea ice is floating in, the whole thing is compressed and it's getting thicker. Yeah. But this is how, yeah, this is the common practice.
Okay, thank you. I think we have no time for another question. So thank you, Caroline. And for the next presentation, it will be remotely, actually, I think. Yes. So next talk will be given by Nicolas Ducousso, who is in France, in Brest. And it's relatively late for him. So, okay, thank you. So we will talk about stability and accuracy of Runge-Kutta-based split explicit time stepping for free surface ocean models.
Okay, can you hear me correctly?
Yes, no problem.
Okay, thank you. Thank you. So, hello everyone. So my name is Nicolas Ducousso, indeed in France, and I'm going to talk about some work I've been doing in collaboration with Florian Lemarié, Laurent Debreu, and Gervan Madec on this subject of the stability accuracy of Runge-Kutta-based split explicit time integration algorithms for free surface ocean models. This work has been carried out as part of the redesign of the time integration algorithm used by the OGCM NEMO, which for years now is split explicit and is based on the leapfrog scheme with Robert Aslin time filtering. And in order to gain efficiency, we have considered the feasibility of building a reliable split explicit algorithms based on some simple RK schemes for the 3D parts, such as, for example, the scheme made popular by Wicker and Skamarok that I will call the RK3. So this scheme integrates this ordinary differential equation over a time period of delta t through this 3-stage sequence by successively advancing variables by a third and a half, then the full delta t, each time recomputing the right-hand side from the current stage. This scheme has attractive properties such as it has no numerical mode, it is conditionally stable for the oscillation and friction equations. And for the oscillation equation, the stability condition is recalled here, mu, which is omega delta t with omega the oscillation frequency, must be smaller than the square root of 3. So we have considered other RK schemes, such as the 4-stage scheme defined on the same principle that RK3. And also we have considered the variants of these schemes, which include a Schumann averaging at the last stage. But here, for brevity, I'm only going to talk about RK3. And so the issues we have addressed with this work are how sensitive are the split RK3 algorithms to the way the 2D, 3D coupling is arranged within the 3 stages. Are there any arrangements which provide better stability or accuracy, and which ones? So in this talk, first, I'm going to introduce the different 2D, 3D coupling strategies we have studied. Then I'm going to detail a stability analysis of the split RK3 algorithms. And this analysis relies on this paper by Demange and collaborators in GCP 2019 in 2 respects. The first is a framework for the analysis of split explicit algorithms, which is based on the vertical mode decomposition. And the second is the proposal to counteract the consequences of splitting errors by using dissipative time-stepping schemes for the 2D integration, rather than using the more classically used averaging filters. Finally, I will report on a few numerical experiments to help verify the results. So this slide shows the coupling strategies we have considered with RK3 as the 3D scheme. For each of the 3 sketches, the gray arrows on the bottom line represent the RK3 stages. The red arrows on the top line represent the 2D integration with small subtime steps, and the vertical arrows indicate the mechanism of the 2D, 3D coupling. The ascending gray arrows show the 3D to 2D forcing term, and the descending red arrows show the 2D to 3D corrections. So with each stage strategy on the left, all mechanisms of the 2D, 3D coupling are applied at each stage, following the logical progression of RK3. So at each stage, there is update of the computation of the 3D to 2D forcing term, of the 2D integration, and of the 2D to 3D corrections. With the first stage strategy, first stage, in the middle, the 2D integration is performed once, using a 3D to 2D forcing term computed from the initial 3D state. A correction is required at the end of the time step for consistency, and additional corrections may be required at intermediate stages, in which case any interpolation of the initial and final 2D states could be used. With the last stage strategy on the right, the 2D integration is performed once, using a 3D to 2D forcing term computed from the 3D state at the beginning of the last stage, the middle of the time step. Again, a correction is required at the end of the time step, and it may be that additional corrections are required at intermediate stages, in which case there is no choice but to use the initial 2D state. So I'll now move on to the framework by Demange and collaborators on which we rely and which I'm going to outline. So the starting point is the hydrostatic primitive equation linearized about rest for established stratified fluid between a flat bottom and a free surface. And the set of prognostic and diagnostic equations and the related boundary conditions written here are fairly standard. The solutions can be conveniently looked for by decomposing on the basis of the vertical modes. These are obtained by solving a stratification-related Sturm-Liouville problem, whose MQ of Z and lambda Q are the eigenfunctions and eigenvalues. The projection onto the vertical modes provide an equivalent and somehow simpler description of the HPEs. And if we denote UQ and HQ, the projection of velocity and pressure, the HPEs are equivalent to a set of uncoupled shallow water-like systems, where CQ is the phase speed associated with vertical modes. In the case of constant stratification, we can solve for the vertical modes. The expression involves the small parameter epsilon, which is equal to n squared times h over g, whose typical value is 10 minus 2, 10 minus 4. And it can be shown that the barotropic mode, which corresponds to Q equals 0 here, so is slightly depth dependent. And this is the second term here, which is so where the stratification appears through epsilon. And that its phase P is C0 slightly differs from the square root of GH, once again by a corrective term, which implies the stratification. The barotropic phase speed is, as usual, much larger than the baroclinic ones. And so Demange and collaborators have built their framework on the idea of formulating the split explicit algorithms and the various mechanisms involved in terms of the model projections. I don't have time to go into the details here, but I only give you an overview of the application of the framework for the split archetype with the relatively simple first stage strategy. It is written like that, where there is the first stage, the second stage, and the third stage. In fact, once formulated, it is easy to numerically build the step multiplier matrix, GQ, for a truncated set of vertical modes, and then solve for eigenvalues as a function of mu0, which is a C0 times the wave number times the delta t. And there is systematically a remarkable feature. The final state of mode Q is not only a function of its initial state, but also of the initial state of the other modes. And so this is one of the consequences of splitting errors. There are spurious coupling between modes and between waves, which can lead to instabilities. So Demange and collaborators have also proposed to introduce the damping, which is necessary to control the instabilities through dissipative 2D time-stepping schemes. A simple example is the forward-backward scheme, here made dissipative by considering these theta-controlled extrapolation of u bar in the right-hand side instead of simply u bar at time n+1. The two plots here on the right show that as theta increases, the damping increases and the stability range decreases. Here, I just illustrate the damping induced by such a scheme in a split explicit context. With these values for the parameters n, h, g, we obtain an epsilon about 4 × 10⁻², and a phase speed ratio between the barotropic to the first baroclinic about 15. Then we set a splitting ratio of 18 as a reasonable value. Oh, these values are rather unrealistic, but they will later reveal the consequences of the splitting errors, which are all the more significant the stronger is the stratification. So the plot here on the left shows the damping induced by n-split sub-time steps as a function of mu0. And for comparison, the plot on the right shows the damping induced by some classically used averaging filters. And so it appears that the damping induced by the dissipative forward-backward scheme is tunable, and for reasonable low values of theta, it is lower than that of the filters. But as filters, it is second order at large scales. And we wonder if with such damping, we will be able to stabilize the split archetype algorithms. So now I go to the results. I show here the analysis result for the each stage strategy. The black curves on the left-hand plot shows the wave amplification in the absence of 2D damping with only two modes in the analysis, the barotropic and the first baroclinic. And for comparison, the dashed gray curves show the wave amplification as obtained with an exact split archetype free of splitting errors. So instabilities are visible at different scales, which involve interaction between barotropic waves or interaction between barotropic and baroclinic waves. And the plot on the right shows the same thing in the presence of 2D damping. In the upper plot, there are only two modes, and we find that the minimum damping required for stability corresponds to a theta star, the critical value 0.28. But in the lower plot, there are four modes, and theta star increases to 0.44. And the reason for this uncomfortable increase is shown by the insets in the figure on the right. The dominant instabilities are baroclinic and involve the higher modes taken into account. and these instabilities are weakly controlled by the 2D damping. And this is a difficulty, and given this difficulty, we discard this strategy. I show now the analysis result for the first stage strategy and last stage strategies. The upper plot shows the wave amplification in the absence of 2D damping without corrections at intermediate stages. And for both strategies, large instabilities appear at medium and small scales, and the behavior is different at large scale, as the barotropic waves are unstable here in the first stage case and stable in the last stage case. But the lower plots show the same thing with corrections at intermediate stages. It can be seen that these corrections have a strong stabilizing effect. The barotropic mode is still unstable, but much less than without the corrections. So the wave amplification of both strategies become very similar. So here, this is the wave amplification in the first stage case with intermediate corrections in the presence of 2D damping. The minimum damping corresponds to theta star, which is 0.13. The same result would be found whatever the number of vertical modes, which is a very nice property. The dominant instabilities are here barotropic at large scales, and they are efficiently controlled by the 2D damping. The minimum damping is lower than that induced by the classically used averaging filters. Indeed, the gray curves of the plot is the wave amplification obtained when the 2D damping is due to the power law averaging filter by Sasha Shepetkin that is used in the ROMS family codes and in NEMO. And for barotropic waves, the difference in damping is very clear. For baroclinic waves, the curves are almost superimposed. What's interesting about this strategy is that we can rationalize the minimum damping required for stability. It is given by this relation on the right. It can be understood as follows. The left-hand term, which corresponds to the barotropic damping induced by the dissipative forward-backward at large scales, must be greater than the right-hand term, which corresponds to the barotropic amplification from the splitting errors at large scales. Finally, it is not shown here, but we can diagnose from the amplification and phase error at large scales that this split archetry algorithm is first order in time. But overall, these strategies with these intermediate corrections are promising.
Nicolas, 2 minutes.
Let me now turn to numerical experiments. The first were carried out with a toy model based on the same linearized HPEs as the analysis. So the model is spectral in X and simply discretized second order in Z. And an important point here is that it is possible to formulate and solve the discrete Sturm-Liouville problem associated with this vertical discretization. And this gives us the possibility, on the one hand, of knowing the exact in-time solution allowed by the grid, and on the other hand, of projecting the result of split archetry integrations onto the modes. So this is illustrated in the figure on the left. We consider conditions similar to those of the analysis of a deep, highly stratified water column. The model has 40 vertical levels, and we randomly initialize the waves of the first 3 vertical modes and analyze the resulting free oscillations. The dashed curves show the velocity and pressure projection of the exact solution as a function of time, and we can see the difference between the fast oscillations of barotropic waves on top and the slow oscillation of baroclinic waves below. And the projection of the solution obtained with split archetry with minimal 2D damping is shown by the square markers. The barotropic waves are damped. The first baroclinic waves slightly differ from the exact solution, and the second baroclinic waves fit well with the exact solution. For comparison, the same figure shows with round markers the projections of solution obtained with an exact split archetry, which has no splitting errors and no needed dissipation. There is a clear difference without split archetry for the barotropic waves, but little difference for the baroclinic waves. And a figure on the right shows the decrease in the relative error of the split archetry and exact split archetry solutions compared to the exact solution for barotropic waves, baroclinic waves. it can be seen that the error of the split archetype decreases like a first order scheme, while that of the exact split archetype exactly decreases as a third order scheme as expected. So the results obtained with this toy model are in line with the analysis.
Nicolas,
yes,
you have 2 minutes to conclude.
2 minutes. So just a very preliminary experiment with OGCM prototype. So just that the equations are non-linear, and it is so an experiment with an idealized internal tide configuration. This is the baroclinic velocity feed after a certain time, and here very quickly we see the decrease of the total barotropic energy, which is very small in the case of flat bottom, indicating that the 2D damping dissipates only a very few energy. The similar results to those obtained with Croco, which has a very different time stepping schemes, but still split explicit. So just the summary, which I'll pass on, hoping I've made myself clear. And just this relatively upstream work will be completed by Sibylle Techene presentation, which deals in part with the implementation of the split archetype with the first stage strategy in NEMO. And so these results of the result of this study and more are in a paper to be submitted, and feel free to ask a question or to send me a mail if you want to have additional information. Thank you for your attention.
Thank you, Nicolas. We have time just for one very quick question. So,
thank you, Simone Silvestri. Probably I missed it, but did you show what are the results with each stage strategy with filtering?
Yes.
Okay, is it that? Because probably I missed it, but was that stable?
No, that was difficult to stabilize the each stage strategy with the. How you mean with averaging
Okay.
filters?
This one, yeah. Sorry, yeah.
Okay.
Yeah. Right.
No, there was a difficulty due to baroclinic waves, and they are difficult to stabilize.
Because I guess like in the first stage strategy, you have like a different tendency that forces the barotropic step to what you use for your baroclinic variables, right? So is there some inconsistencies there maybe, or?
Sorry, I didn't really see the point, or what?
I can send you an email maybe, because I'm interested.
Okay, thank you.
Hi, this is Robert Hallberg. We dealt with a lot of these for second order Runge-Kutta with very similar sorts of instabilities back in the 90s. This is a series of papers by Higdon and Bennett, Higdon and Dzurka, and then another one by me, all of them in Journal of Computational Physics. Importantly, those whiskers of instability, if you choose slightly different ways of averaging some of your quantities to get them at the same point, with the 2-layer system, for RK2, you can stabilize them so that instead of destabilizing, the modes repel each other instead of attracting. It may be worth looking at it as a way to kind of look at what happened in RK2 as a way of saving what happened in RK3 with much less damping. That if you look on the GFDL bibliography, you'll find my paper, and then 97, and then the Higdon and Bennett's are all cited there.
Okay.
Okay, thank you. We will move to the next talk. Back to CIs, I think. Yes. Yes. Yeah. It's you. So that you can. Okay, so next talk is given by Theresa Morrison about an improved coupling between sea ice and ocean.
Great, can you hear me? Okay, great. Yes, so I'm going to talk about some work I did as a postdoc and have continued as a scientist at GFDL in collaboration with Bob Hallberg, Matt Harrison, and Kate Hedstrom, but really all of the MOM6 development group has been bothered at some point about this project. And the starting point of this project is something really, really obvious, which is sea ice actually is submerged in the ocean. It floats and it is integrated in the ocean. And so this is a really cool observation of sea ice breaking up from a gravity wave hitting it. So I recommend looking up this talk. I wasn't brave enough to put a video into my talk. But our work basically is trying to put the sea ice back into the ocean because historically it has been removed in all of these models. So what we have in models right now, I'll brave the pointer, is levitating sea ice. So sea ice models generally sit above the free surface of the ocean model. They do not deform the free surface. They do not exert pressure on the free surface. There's still coupling of the velocity and the stresses and the freshwater fluxes, but that key pressure aspect is not present. And this is important for sea ice, but it's even going to be more important when we have icebergs and calving of icebergs from ice sheet and these dynamic changes. So our goal is to develop a coupling that will allow us to resubmerge sea ice in the ocean and explicitly resolve the external gravity waves that are generated by the sea ice moving around in the ocean. This was just a slide about how coupled ice ocean stress instabilities can form whenever the sea ice is levitated in this way and lagged in the coupling, but I'm going to skip that details. Just know there's lots of problems with levitating our sea ice that we've done a lot to solve. And so to address the stress instabilities, we propose what we call the interspersed coupling, where we couple the dynamic parts of the ocean model and the sea ice model on a shorter time scale than the longer thermodynamic processes. And then to address the gravity wave issue, we propose an embedded coupling, where the sea ice rheology, which is the dynamic movement of the stresses and changes in the sea ice, are actually updated within the barotropic steps of the ocean model. So as those gravity waves are explicitly resolved by our ocean model. And this is the goal that will allow us to submerge the sea ice and eventually icebergs in the ocean model. There have been a number of challenges that we faced in this work, many of which were taken care of before I started, but are things that are sort of laying the groundwork for being able to do this in the MOM6 and SIS2 models. And I want to highlight some of those really quickly. First is making sure our sea ice and ocean are on the same grid and specifically also on the same set of processors so that exchange of information between sea ice and ocean models can be efficient. Splitting the thermodynamic and dynamic time steps of these models. So we can do just the thermodynamic step or just the dynamic step for both the sea ice and the ocean. And this has also been done for MOM6 and SIS2. And then creating all of these new interfaces to pass the relevant information at the relevant time to the relevant part of the model, which is a lot of what I've actually been doing day to day. And then as we do this development in MOM6, we're very aware that people use other sea ice models, and we're trying to maintain that compatibility with other coupling options. So in order to explain this time stepping scheme, I'm going to give a brief overview of the time steps in MOM6 and SIS2. So this is going to be a filled out diagram eventually, but the x-axis is sort of moving forward in time, and we're going to stack the different time steps up on top from longest to shortest, and then show different coupling schemes. So within MOM6, the longest time steps are the thermodynamic time steps, the tracer regridding and remapping time step, which adjusts the vertical coordinate, and then the tracer advection time step, which use the accumulated transport from the dynamic step to advect all of the tracers around. Then, similar to the last talk, MOM6 uses a split explicit time step. So the baroclinic and barotropic dynamics are split. It uses the RK2B scheme for the baroclinic step, and then there's a much shorter barotropic step that's taken that resolves the external gravity waves. And this is the time step deep within the model that we are looking to link to our sea ice model. In the sea ice, we have a similar breakdown of dynamics and thermodynamics. So there's a slow thermodynamic step that governs melting and refreezing, those thermodynamic interactions with the ocean. And then a dynamics step that would be the ice transport, moving ice from layer to layer, things like that. And then within that dynamic time step, there's the elastic viscous plastic rheology solver, which calculates the internal stresses of the sea ice and changing ice strength and concentration. And we want to essentially merge these two parts. Ooh, I see the problem with the clicker now. I will say also there's a very fast radiative exchange with the atmosphere, totally separate from this, has already sort of been separated out. So the sort of default coupling scheme is a concurrent coupling scheme. And in this coupling scheme, you have all of your tracer dynamics and steps going on one set of processors and your CIS model going on a different set of processors, and they periodically exchange information. And this introduces quite a long lag in the coupling between the two models. And that means that you can generate all sorts of instabilities. The interspersed coupling, which is the main coupling I will be talking about today, is where we take advantage of the fact that the dynamic parts of these two models have been separated out. And we couple the dynamic parts of the models more frequently than the thermodynamic parts. And what this means, in effect, is that we can do many shorter dynamic time steps to more tightly couple the sea ice and ocean velocities and prevent stress instabilities, but still maintain the performance of having long thermodynamic time steps and not having to do frequent coupler all-to-all communications. The final form of this work, though, is really blurring that line between the sea ice and the ocean model and bringing more and more of the sea ice dynamics that are relevant to the barotropic ocean dynamics into the ocean model. So we would be evolving the rheology at the same time as the barotropic step. So here it's sort of showing them alternating, doing a barotropic step and a rheology step to tightly couple the sea ice and the ocean state to allow us to embed the sea ice and resolve those external gravity waves at the timescale that they're actually resolved within the ocean model. So I'm going to show some results. These are results from a sort of very, very idealized case where we have uniform ice, sort of doubly periodic domain, flat bottom, basically just trying to be as boring as it gets, generate some inertial oscillations, and see how different coupling time steps behave. And with this, there are a few questions that we want to ask. So how does the coupling and interspersed time step change our solution? We know that coupling time steps can impact the solution of the sea ice in global models. Is the sea ice state the same if our IO here means our interspersed coupling time step is the same as our coupled time step? Can we intentionally create instabilities with the coupling and then suppress them with the interspersed time step? And then how does the interspersed time step relate to our ice ocean stress? So there's a whole array of different sort of combinations of coupling time steps that we've done to sort of investigate these different lines of inquiry. And I will say that this problem is sort of too simple for us to answer that first question. We don't see a real difference in the solution. We're sort of getting good inertial oscillations as long as our solution is stable. So starting with that second question, is the sea ice the same if DTIO equals DT coupled? This is after a couple days of the simulation, just showing the surface ocean velocity in a sort of traditionally coupled run versus a run with a longer coupling time step and a shorter interspersed time step. They agree. Great. It's a very simple result, but it's good that we can do that. And then we can also create instability. So if we extend that interspersed time step to be 2 hours, we get a crazy solution like this. It doesn't actually blow up the model, but it is obviously not doing inertial oscillations. But again, if we shorten our ice ocean time step either to 60 seconds or 1200 seconds, we can retain that long coupling time step, but get inertial oscillations still. And that's great. That's the interspersed coupling doing exactly what we wanted to do in terms of managing stress. And I actually did some experiments where I pushed that coupling time step way past what would ever be able to resolve inertial oscillations theoretically. And it actually seems like maybe it's getting the right solution. I think there's more inquiry that needs to be done to make sure that those little red stars aren't just coincidentally falling on the right points in that curve, but it opens promising results. And then we can look at the relationship between this interspersed time step and the ice ocean stress. And the reason for doing this is to understand how the ice ocean stress is going to change as we go to higher and higher coupling frequencies and as we approach that embedded limit. So with this test experiment with a given amount of wind stress, we see that maybe about 1200 seconds or so, our ice ocean time step has sort of leveled off the ice ocean stress. And at the much longer time steps, we have crazy high values indicative of instability. But we have to go to a 2-minute time step to really get to sort of maybe the floor of that ice ocean stress. And that's really the argument for going to this embedded limit of tightly linking the ice in the ocean model on this barotropic timescale. And there's sort of a middle range here that I think would be worth exploring, where we would be maybe coupling the models on the baroclinic time step to sort of further reduce the difference in the stress causing instabilities if the interspersed is not necessarily reducing the stress enough in our sort of larger experiments. So we've done a bit of testing of this as well in some more realistic runs. This is a regional Arctic model by Kate, and I've sort of put the results on this slide just to sort of preview them. But basically, we do see a significant change in our sea ice state whenever we go to this coupling, not necessarily for reasons we fully understand. That sort of gap between the idealized and the full model needs to be bridged still. But we see a huge reduction in our Jinsea sea ice, which is great. That's been a longstanding bias in these models. There's also a decrease in the bottom melt and the SST under the ice, which could be related to changing the stress at the surface. There's a really interesting change is that we start to see a higher ice concentration. So a grid cell, maybe instead of having a distribution of sea ice concentrations, we tend to have more grid cells with 100% sea ice and 0% sea ice instead of sort of distribution we previously see. And this leads to thicker ice in the central Arctic. We see a decrease in the sea ice speed, which is also related to a decrease in the ice ocean stress. And Matt Harrison has done some work that has shown that increasing the ice atmosphere drag can actually reaccelerate the ice and help with some of the issues that are related to the ice slowing down. But really understanding how just changing your coupling scheme has led to all these changes in the sea ice is future work. So this is highlighting that change in thickness throughout the sort of central Arctic in winter. And then the sea ice speed change. So it's sort of a general overall slower ice. And the ocean generally does sort of act as a drag on the ocean, on the ice. So maybe that makes sense with the tighter coupling. But it was an interesting result. Here are my conclusions. So we've created these stress instabilities by separating our sea ice and our ocean models entirely. And to resubmerge the sea ice in the ocean, we need to change the coupling scheme so that the rheology time step is updated within the barotropic time step. On the way to that, we have developed this interspersed coupling, which does the dynamic updates of the sea ice in the ocean together, separate from the thermodynamic coupling. And our results are that we found this can be helpful to resolve dynamic processes that we couldn't otherwise with longer coupling time steps. But it might not be sufficient to significantly reduce the ice ocean stress if we think that is too high and causing instabilities still. And it really made this argument that going to even tighter coupling, even shorter time steps in the embedded or baroclinic limit might be what we really need for that. In our regional Arctic model, as well as testing this in global runs, there's a tendency towards thicker ice with higher concentrations and slower sea ice. And we just need more complex idealized simulations to start to bridge that gap in how these changes are manifesting in the more realistic models. So we'll leave it there and I'll take some questions.
Okay, maybe early career scientists first. So.
Hi, so thank you for this wonderful talk. I have a question. Do you adjust the number of iterations in this EVP solver?
That is something that we, no, for these experiments, I kept the number of, yes, I adjust the number of iterations, but the time of each iteration stays the same. And I don't know which is more important, whether the DT of each iteration or the number per rheology cycle. We sort of decided that maybe DT of each rheology step was more important.
Because, you know, the longer the time step, the more iterations you need to get to a stable solution. Yeah.
Yeah, so the effective time steps within the CIS model are the same despite whatever coupling scheme that we use. So we try to keep every time step, but the coupling time step that we're trying to investigate to see.
So Gökhan and Andrew.
So one advantage of keeping the CIS model separate is that then you can essentially use different CIS models, and NEMO groups, many of them use different CIS models. When you embed, or with this approach, are you then tied to a single, or are you committed to a single CIS model, I guess?
Not necessarily. I think that, I mean, I think what defines the CIS model, with the embedded coupling, we're really embedding a rheology, but that rheology scheme could be flexible. If you could pull it from a different CIS model and just stick it into the barotropic solver, that would theoretically work, but we're not.
In practice, it won't work.
Well, yeah, because probably your rheology steps haven't been sorted out from your other CIS models, yeah.
Hi, this is an incredible amount of work, and it's really nice to see it paying off. At the last Commodore meeting, there was a really nice talk about looking at multi-rate PDEs, right? And this is a problem that we run into in the barotropic rare clinic coupling. And so essentially what you've done, right, you've kind of taken a split scheme and embedded it. So I'm just kind of curious to know, is the issues with the instabilities that you're seeing, are they fundamental to like a staggered time stepping of, or like a staggered coupling, a staggered like time step, or are these some things that you might be able to like correct if you were to take like a multi-rate approach to solving PDEs?
They're like sort of inherent in this coupled system where you have to, I will go back to that slide, but where you, that I skipped, I should have skipped. Yeah, so when you have this difference term in your stress, whatever, this difference term in your stress, you have some lag there in the stress that the ice feels when it is advancing and the ocean feels when it is advancing. And that is just an inherent issue of this coupled equation. So I think that you could maybe do more to get these dynamics closer together, but you always have to have a stress that the sea ice sees and a stress that the ocean sees.
Okay, thank you. I think we should move to the coffee break now and be back in 30 minutes. And thank you to all the speakers.
I'm walking away with it. I was like, what is this in my pocket?
Okay, so next talk will be given also remotely. It's by Michal Kopera from Boise State University, and it's about multi-layer shallow water model with high-order discontinuous Galerkin methods. Okay.
Hi, thank you for having me. I'm sorry I couldn't be there in person, but the day before the meeting, I got COVID, so I got to chug along and give the talk online. First of all, it's a great meeting so far. I'm trying to follow along, and I will try to contribute to the conversation on the high order models. Right? Do we need them? What do we need them for, and what they can do for us? I'm going to talk about the HNUMA model, which is a prototype we've been working on with my student Yao Gahunzo, who recently graduated from Boise State. And we collaborated with the group at COAPS, namely Eric Chassinier, Alan Wallcraft, and Alexandra Bozek. And we got a massive support also from Robert Higdon at Oregon State, who helped us a lot with splitting schemes for DG and share his codes and so on and so forth. So what I'm going to do, I'm going to give you an overview of the model. I will skip on a lot of the details of the, the numerical. I will focus on the spatial discretizations, and then show you the comparison of HNUMO against HICOM, and we'll talk about the accuracy versus performance. Okay, So, an H-NUMA model is a part of the NUMA family, started by Frank Giraldo at the Naval Postgraduate School. I was a postdoc with Frank, and I was working on the NUMA model, which is the atmospheric model, currently a dynamical core in the Neptune weather prediction system for the US Navy. And at some point, I got interested in ocean modeling, so I started a spin-off model called NUMO, which was the same machinery, same numerics, but for ocean. But the model was focused mostly on ice-ocean interactions and non-hydrostatic ocean modeling. But since we started working with Eric, we started to explore, can we use this machinery also to model larger scale ocean? So we implemented the multi-layer shallow water equations, which I'm going to show you briefly soon. And we did this with the DG, this continuous Galerkin method, on quadrilateral unstructured grids. And the cool thing about the model is that you can basically pick and choose which order you want to be, right? So you can be, I'm going to show you results for second, fourth, and sixth order, and we're going to compare them against each other too. And we implemented the barotropic baroclinic splitting by Higdon 2015. Right, so focusing on the spatial discretization, what we do and the way we achieve this kind of flexibility in the order of the method is that well, first of all, we decompose the domain into elements. In this case, it's going to be two-dimensional unstructured grid, and then vertically it's going to be layers. And each element we can project onto a standard element, like so, which is a square. And then in this element, we create a grid of nodal points, and they are not uniformly distributed. They are distributed according to some special distribution, LGL, Lagrange-Gauss-Lagrange points. On each of those points, we create a basis function, a Lagrange polynomial. And then depending on the choice of the polynomial order, we're going to have that number of points. So for example, here I'm showing you an example for third-order polynomials. So we need 4 points in each direction to create a third-order polynomial in each direction, and then we form 2D bases by tensor product. And this way, we can expand the solution in the basis of those polynomials, and then apply the Galerkin machinery to any equation in linear conservation form. We get the weak form, the bottom line of this is that now we choose how to display integrals in the weak form. Most of those integrals are what we call volume integrals. So they basically just integrate our solution and integrate the terms of the equation within the element without talking to the neighboring elements. So that's one part of the problem. And the other one, we have integrals along the edges of the elements. And since we are choosing the discontinuous Galerkin method, we allow the solution to be discontinuous between the elements. So here you have a 1D kind of cartoon of this. So for the method to be consistent, we have to introduce certain numerical flux, basically take into account the solution on both sides of the interface so that we actually get a consistent method. So that's going to come into play in here, right? But the most important aspect that I'm going to talk about today is that we can vary the number of nodes within this element, and therefore the approximation order of our solution inside is going to change, increase or decrease, and that's going to also affect, the resolution, which we're going to discuss in a moment. But bottom line is we can control the resolution both by controlling the element size and controlling the number of nodes inside of the element. Right, yes, so we are solving the multi-layer shallow water equations. So real quickly, they look similar to shallow water equations, right? I'm not telling you a full story here, I'm just showing you the simplest version that we have, but we follow Bob Higdon's paper so we can look up exactly how those equations look like. Bottom line is that we have layers of constant density. For each layer we solve the pressure, thickness, and the momentum. We have some terms here which might not be typical, like H here is the pressure integral across the layer vertically. There's some Coriolis force. I didn't show you the viscosity terms, but we also include. And then we apply the barotropic baroclinic splitting by Higdon. There is a lot of nuance and a lot of work went into this to make this work. It's definitely non-trivial to make it work for DG, and Bob showed that in these 2015 papers and the follow-on papers, most recently 2023, I believe, or 2024. But I'm going to skip over all that because my focus today is on the spatial discretizations. We kept many aspects of Bob's work. However, we did some changes, and the differences are that he worked with DG in so-called model basis, and we implemented in the nodal basis. Model basis is when you have basis polynomials of varying order from 0, first, second, and so on. Our basis polynomials are all the same orders, and they attach to nodes, so it's a slightly different flavor of DG. And we expanded his implementation from 1.5 horizontal directions, so one real direction and the second one is just infinitely long, to regular 2 horizontal directions. We did some changes to the predictor corrector time integration that he did, and replaced, for example, the barotropic time stepping with RK35. But again, I'm going to move on from there and show you the results. So we are comparing HNUMO against HiCOM on the double gyre test case. What I'm showing you here is the simulation with 50 meters square per second viscosity. It's a standard double gyre test case, wind-driven. There is 2,000 kilometer square domain. We're using 2 layers. And important aspect of this comparison is that we are trying to use what we call, quote, unquote, comparable resolution, right? So what I mean by that, for HiCOM, if I take a piece of the domain, like on the right here, and this blue square is 40 kilometers aside, if I have 4 by 4 volumes in this blue square, then the size of each volume is 10 kilometers, so my resolution is 10 kilometers, right? That's the traditional definition of resolution. Now for HNUMO, to achieve what we call an equivalent, not equivalent, a comparable resolution, we take, for example, an element size of 40 kilometers and then use 4th order polynomials so that we have 5 nodal points in each direction within the element. And then the average distance between those points, remember, they are not equally spaced, but the average distance will be 10 kilometers. So we're going to call this same resolution, even though I'm going to show you that the results are not the same. So how do we compare the results? You're looking at the sea surface height of double gyre test case right now at 20 years. You've hopefully looked at this animation as it was going. And the question is, are they the same, different? Which one is better, right? Which one is more accurate? And who knows? I mean, like they both look good in my opinion. So to come up with some metric for comparison, we calculated the kinetic energy for both models, for weight average in both layers as well, and plot this as a function of time. And what we see that we get very different solutions in HiCOM and in NUMO, right? And then again, which is the correct one? Of course, we trust HiCOM because it's been around for much longer, and HNUMO is just a prototype right now. But we did get different solutions. We tried different resolutions. So what you see here on the top, the blue line, is HNUMO. For solid line is the 10 kilometer resolution, dashed line is 20 kilometer resolution. Similarly, HiCOM results are red, and we have solid line for 10, dashed line for 20, and still that increased resolution here doesn't really change, or the fact that we get very different results. So we figured, okay, let's assume that both models are correct in some sense, and then try to find out what's really happening here. So if we start increasing the resolution, so decrease the grid spacing, we should converge to the same result, right? So we should get at some limit the same kinetic energy. So what we've done, we designed an experiment where we ran multiple simulations with HiCOM with different resolutions, and similarly multiple simulations with HNUMO with different resolutions and also different polynomial orders, so different order models. And we're going to look at the time and space averaged kinetic energy in the last 5 years of the simulation. And we're going to plot, like, we're going to make a plot where we have a kinetic energy here versus the resolution, right? Or versus the grid spacing. And so the high resolution is on the left, basically. Apologies. So I'm showing you results for different viscosities. The top results here are for the viscosity to 50. The bottom line is 500. I'm going to focus on 50 only. Time permitting, we can discuss 500. They're less interesting. But what you see here is the HiCom result in green squares, the H-numo second order polynomials in blue, and then fourth order polynomials in black, and sixth order polynomials in red. And what we can see is that the higher order models, right, they tend to converge to each other pretty quickly, and they tend to level off. So we hypothesize, we don't have those results because it would take a very long time to get them, but we hypothesize that if we try, and we should try probably, finer resolution simulations, they would level off here, right? So that would be the resolved kinetic, completely resolved kinetic energy in the flow field, right? And then second order model is seemingly approaching that level, and similarly HiCom is approaching that level as well, and hopefully reaches it somewhere here. So it looks like in this comparison, right? It looks like the higher order models, the fourth and sixth order, are getting way better. They resolve the kinetic energy way better than the lower order models here. So, but now the question, natural question is, hey, but okay, how much it costs you, right? How quickly quickly can you actually get those high order models to run? So initially we looked at we sliced this plot vertically and we compare the same resolution simulations and their performance, but then I realized it's the maybe incorrect way of looking at this. And I figured, let's take the best HiCom simulation we have, the highest energy we have, and try to slice it horizontally and see what resolutions of the H-numo simulations will have comparable kinetic energy, right? So for the second order, it's about 8 kilometer. For the fourth order, it's about 20 kilometer. And then for the sixth order, it's about 25 kilometer resolution. And then we compare performance of same result in this particular test, in this particular metric, same result simulations in parallel, right? How well we scale for this kind of experiment. What you see here on the left is the speed up plot, on the right is the efficiency plot. I'm going to focus on the efficiency more here. So this is the magenta line on the bottom here is the HiCom result. And those three colored lines with circular markers is H-numo. And we see that essentially all the orders here, they roughly get 80% parallel efficiency for the biggest machines we could use at Boise State. So I think that's pretty good result, right? It's not perfect. I think we can still do better than this, but it's pretty good. And even better thing that that's not maybe obvious from this plot is that I'm not plotting more points for example, this yellow line here for the sixth order normal. I'm not plotting it any further, not because I'm cheating and I don't want to show you that maybe it drops down. It's because at this point, my 25 kilometer simulation has one element in horizontal decomposition, 2D decomposition per core, right? And times 40 layers. By the way, those performance plots are done with 40 layers. So we are closer to the realistic model setup than just 2-layer model. And we don't let the barotropic solver take over everything else. So in here, we have one horizontal element per core, and we cannot break it up any further in the current decomposition. So I think it's pretty cool because, and for example, for the fourth order model, we have 2 elements per core, so we can do slightly better, but not much. So if we get 80% performance at 1 element per core, that means, theoretically at least, algorithmically, that means if I take way bigger problem and I use way bigger machine and still have 1 element per core, I still should have 80% efficiency. So that's a really good prognostic. Of course, I think to check that for bigger machines, there are some hardware challenges and whatnot. But algorithmically, this essentially tells me that the ratio of computation that I do and communication that I do is pretty favorable for high order methods. All right, but then how about the real time to solution, right? So on the left, you got exactly that. And this is the time to solution for one model day. And again, this is HiCOM result, and HiCOM is faster, almost regardless of the number of processes we used, than second order model. But the sixth order and especially fourth order models, they beat it by about an order of magnitude here to 56 processes. And remember, we expect this to, to be maintained, the efficiency to be maintained like that. And HiCOM looked like it might be losing efficiency, at least in our experiment. So we are about 10 times faster here. Also, in terms of CPU hours, so the resources, if you will, dollars spent on the simulation or energy spent on simulation. Here you have the CPU hours per 4 model days, and we get also about an order of magnitude lower cost for the high order simulations, not so for the lower order. Okay, so that's really promising.
2 minutes, sorry.
Okay, thank you. I'm getting to the shore with this one. Almost 3 more slides and I'm going to be done. And that was only on structured grids for HNUMO. We didn't use unstructured grids. So just to show you that we can, we just used an unstructured grid. We just said, okay, let's take some resolution here on the left, 3 times as big elements on the right side here, and we just use Gmesh, the software for meshing, to do just any mesh. Run the simulation, calculated the energy again, and we put the extra point for a structured grid just to show you that this works. So we put that point in here with the black cross. We put it at the 25 kilometer resolution because the structured grid uses 400 elements. Yes, 400 elements. Therefore, it's comparable to a structured simulation with 25 kilometer resolution. So we still see the massive improvement just because we use unstructured grids semi-intelligently, because we put the resolution where it's supposed to be, roughly, and we still get massive improvement. So whatever you've seen before, it still can be improved due to unstructured grids. All right, so to the shore with this, conclusions. So in the context of the experiment I'm showing you, namely the double gyre test case and the energy kind of metric that I'm using here, NUMO does deliver the same result as HiCOM, and it does it with smaller resolution, right? Or more importantly, faster and with fewer resources, asterisks for higher order methods in HNUMO, and it does it with very parallel efficiency. Furthermore, the unstructured grids will further help with making sure that we squeeze this efficiency even more we resolve things better with unstructured grids if we know where to put the grid. I can talk about AMR all day long, but it's not topic for today. It's possible in the framework that we have. But of course, you won't believe me that this is useful if I don't show you that this can work outside of the ocean in the box. So the next step is to do this on a sphere with coastline and demonstrate a similar efficiency, hopefully, in that setup. Just to tease, I'm showing you a picture on the right from a paper from 2018 where we were doing shallow water on the sphere with all the bells and whistles of structured grids and adaptive meshes. But I will stop with that and hopefully take a question.
Thank you. So we have time for one quick question. Let's look at.
What about the viscosities in these simulations? Are they identical? What kind of viscosity do you have? Because that's going to impact the kinetic energy.
Yes, excellent question. Yes, so we are using here, the nominal setting for viscosity is 50 meters squared per second, and yes, they are the same. And we are using basically just Laplacian velocity. But yes, the implementations between the two models might be slightly different. For example, you have many choices of how to implement Laplacian viscosity in DG, but mathematically, I believe they are the same.
Yeah, I have a question to this cross-grid comparison. Do the approaches have the same number of degrees of freedom?
Excellent question. No, they do not. And that occurred to me only after we wrap this up. But no, they do not. Actually, if you slice this plot this way vertically, HiCOM has much fewer degrees of freedom than either of those grids.
Yeah,
now this way, if I slice this way, then those guys will have fewer degrees of freedom.
I think let's say fair comparison should be the same degrees of freedom, no?
I don't fully agree. I mean, yeah, I agree I should do it and show it to you, absolutely. But it depends on what you mean fair, right? Because the argument I'm trying to make, I'm comparing same energy, right? So same output, and then I'm looking at the performance. If I did same degrees of freedom, and I agree I should do it and show it to you, I do not have that result yet. Then it would be equivalent to slicing this plot again vertically, right? And I would still get the difference in the energy. I would get more energy from an H-numo than I get from HiCOM from the same degrees of freedom.
Okay, thank you. I think we need to move.
Sorry.
Okay.
Sure.
Sorry, excuse me. Yeah. So yes, thank you.
No worries.
So we move to the next talk by Sibylle Techene. About the gain of efficiency from NeMo 4 to NeMo 5.
Okay. Thanks for giving me the opportunity to present these results of how we managed to gain efficiency from NeMo 4 to NeMo 5. These achievements have been made by NeMo system team in collaboration with INRIA, and we've been, well, also with Europe money. There are several ways. Okay. There are several ways to accelerate an ocean model at a given accuracy. I'll talk about three of them. How we optimize the kernel, how the change of algorithm for the time stepping, and the I/O management, the input and output management. I'll end this presentation with a little bit of science, but keep in mind that I'm a developer and I'm not a scientist. Okay, so let's start with the kernel refactoring. I'll start with a bit of NeMo presentation. I want to introduce it to understand how it works and to understand the work we did to optimize it. So this work has to do with MPI communication and memory footprint. And then I'll show you some numbers. Okay, so NeMo is a Fortran code. It was born in 1986. So it's a finite difference code. It worked on a C-grid. It has been optimized for vector machines. Still, it's actually running on CPUs. It has a general vertical coordinate capacity. It has split explicit free surface, and it has some nice features such as grid refinement, a nice model, and a biogeochemistry model. It's a parallel code, so its domain can be decomposed into subdomains distributed on computing units. This require, because we are making derivatives, spatial derivatives, this require to exchange data, to do MPI communication. And because we don't want to make a communication each time we're making a derivative, we extend a bit the domain, the subdomains, and that's called a halo. So MPI communication are really a bottleneck into NeMo. We had too many communications. So we tried to reduce the number. How we did that, we first moved from 1 halo size to 2 halo size. So it saves some communication. And this helps to gather communication, most of them at least, at the end of the time step. We also reduce the synchronization barrier with reducing the number of blocking communications. Another problem in NeMo is that it's memory bound. Yes, the more you use the memory, the slower the code. So we had to reduce the memory. Sorry, there is a typo here. There is remove the Z stuff. So we reduce the global memory by removing by removing the level thickness arrays in the code, making benefits from the quasi-Eulerian framework we are working with. And because we compute them on the fly, making benefits from their linear dependency with the SSH. We also reduce memory usage in local routines. Okay, so to compare NeMo 4 and NeMo 5 efficiency or like performances, I run 1 degree global simulation with ocean ice and daily inputs and outputs. These runs have been done with the leapfrog time stepping. And here are so I present the gain, that's the simulated years per day ratio between NeMo 5 and NeMo 4. The good news is that whatever the number of CPU, well, it's the gain, okay, the figure shows the gain with respect to the number of CPUs. And the good news is that whatever the number of CPUs, we are able to gain at least 20-ish% between NeMo 4 and NeMo 5. And you see that the extra gain we have with a low number of CPU is related to the memory optimization, because in that case, we run with larger subdomains. So it had, well, here we see the footprint memory optimization. Okay, so that's cool. We are able to accelerate NeMo by at least 20% by refactoring it. Okay, so now let's get into the the time stepping part. So first, I wanted to talk about the motivation why we changed why we replaced the leapfrog time stepping with the Wicker and Skamarok Runge-Kutta third order. This RK3 has some weaknesses, and I want to show after showing the weaknesses, I wanted to show how we overtake them before showing some numbers again. So yeah, so these plots are coming from Le Marier 2015, and they are about theoretical stability constraints. And what I like in the first plot is that it's a nice way to show a stability constraint for different processes of ocean models. So you see the maximum allowed time step with respect with the resolution for different processes. So the working framework is a NeMo framework, and here you see that at the top, so the less constraining processes are the diffusive processes. The flat line is a Coriolis process, and at the bottom you see the advection with leapfrog, meaning that 3D advection is limiting the time step into NeMo. If you look at the CFL on the right-hand side, you see that by replacing the leapfrog with the Runge-Kutta third order, you can almost double the CFL. So if you double the CFL, you're able to double the time step, and if you double the time step, it's twice less to run a 1-year simulation. Is it sufficient to say that we can speed up NeMo by 2? Not really. By a factor of 2? Not really, because RK3 also needs 3 stages, meaning 3 integrations, and yeah, so it means 3 times more computations. But in NeMo, we use some tricks to overtake that. So I wanted to show first the tricks we use on advective tracers equation, because that's where we gain the most. and that's where it's more interesting as well. So, so there are 3 tricks. The first trick is about advection. In NeMo, we can use several schemes for advecting tracers, but the most popular is the flux-limited transport. And it's really expensive in simulation. So we don't use the FCT at stage 1 and 2. Instead, we use centered scheme. So that's the first way to gain a bit. Well, not a bit, a lot. Then the second trick is the diffusive part. We don't compute the diffusive processes at stage 1 and 2. And again, it's nice because for the lateral diffusion, again, NeMo has several ways to compute that. But in a global simulation, most people use the isoneutral lateral diffusion, and it's also expensive. The same for the vertical diffusion, we treat it implicitly. So we are happy to gain a bit here too. And last, the third trick is about the forcing. So we only add the forcing at the last stage. But because we are in flux form here, so because we need compatibility with the continuity equation, and the continuity equation had mass forcing, we need to have add this mass forcing inside the system. So we add them, but we add them at the temperature and the salinity of the surface of the sea. Okay, it's rather the same for momentum. So all the processes that have to be centered are computed at each stages, and we remove diffusive processes and forcing at stage 1 and 2. One thing I want to mention is that we use the single first strategy to couple the barotropic mode and the baroclinic mode. And as Nicolas showed you, that's stable. And yes, that's all I want to say. And yeah, and the paper is about to come. Okay, so despite this, the additional calculation, an RK3 time step is only 30 slower than a leapfrog time step. So it's quite good, because if we can increase the time step by a factor of 2, then the performances will be fine. So I don't want to get into details here, but the main idea is that we gain. We are able to speed up things. Okay, so NeMo was not the only one to be optimized in this chain. So NeMo for this for dealing with inputs and outputs use XIOS code, and XIOS code has been optimized as well. So it's based on an I/O server running on dedicated codes. It has been developed at IPSL by Jan Murdoswaf. And here the results are shown for quarter degree simulation, force simulation with ocean ice and I/O. And you see on the right red bars that it adds an extra 30% gain. So in the end, when you compute, when you look at the old NeMo with XIOS 2 and the latest NeMo full power version, it's a 2.5 acceleration that we have. Okay, so now a little bit of science. I thought it was interesting to show, well, the mechanics is nice, but I thought it was interesting to show you, convince you that we didn't break anything in the code. So these are, I'm not sure if it's a good argument. So here are the meridional overturning meridional overturning circulation. So it has been done with 100-year forcing simulations. And whatever you look at, whether the maps or the time series, we are, well, I am at least happy to see the same kind of patterns. So there are some differences. Are these differences important? Are they, well, Is the RK3 performing less good as the leapfrog? I'm not sure, and maybe you can tell me at the end. Yeah, but so far we're on the same planet, and that we want to see. Okay, so to conclude, maybe I've been a bit fast. Yeah, so NeMo is more than twice faster than, has been accelerated by a factor of 2, thanks to the optimization, 20%, the change of time stepping, 40%. It's not exactly the number I showed here, but roughly, let's say 40%. And there is a paper to come soon. And the I/O management, we gain an extra 30%. The question, because we run on CPUs here, is that will this conclusion translate to the GPU case? And I don't know, the right way to do it, to try it. And for now, NeMo, there is a special group working on NeMo porting on GPU. And yes, it's running. Not sure the performances are yet satisfying, but still, we'll be able to know it soon, more or less. Okay, thank you.
Thank you. Okay, early career science. Okay, Adrien first. Thank you for the presentation. I have a small question. Since you're evaluating the FCT only at the third subtime step, do you know if you managed to keep the monotonic properties of the scheme, or how it behaves, if it's really necessary in the end?
I have no idea.
Okay, well, thank you.
Thank you.
Can I? Yeah. Maybe adding on this. Have you checked that at a quarter-of-a-degree solution, you can run stably and there's no problem happening with the centered scheme in the first 2 stages?
Actually, well, the quarter-degree simulation run, and I don't know. Maybe you will be the best place to know the results, but okay. Well, up to now, I think there were like quarter-degree simulation with the old version of RK3, and it was quite nice. But well, the results were not crazy.
Okay.
I didn't.
Thanks. I'm intrigued by your tricks because they might be tricky. So in the momentum equations in particular, but I think this happens for the traces as well. When you cross out terms for the predictor steps, it kind of changes the balance. So you crossed out the friction terms, and so you're kind of accelerating the flow in one direction in your guess. And although it's only a guess, it is nevertheless suddenly out of balance. I'm just curious about why you didn't choose to just use the old acceleration for those terms, because it feels like it's less accurate, and maybe that's the only reason you're seeing a difference.
What do you mean by?
Well, in your tricks, if you go to your momentum equations, you crossed out
the whole things.
Yeah, so you crossed out terms, which means that all of a sudden you might have a balance between friction and Coriolis, for example, in the Ekman layer, and you've only kept Coriolis, and so suddenly the flow is going whoosh. Okay. And it's a technical term, and
like this.
So,
I understand.
So although it's only a guess, it is nevertheless a less accurate guess than if you had at least lagged the accelerations, and so it would still be in balance or closer to balance than just crossing them out. And it would probably be just as efficient if you used the old one rather than recalculate it. So, but I'm just surprised that it actually worked as well as it did, because those terms do actually matter in a few places. So.
Yeah, Jérôme wanted to do that also because.
So blame someone else and you're okay.
Well, it depends on the cost as well. But well.
Can you go to the last slide, the penultimate slide?
This one?
No, next one. Is that for real, the lower left with the first name in the author list, Gervin Medak? Because I think the last time he was the first author was 1996.
I let Florian.
He won't be the corresponding author.
This is just what I say. He's the first author, and that's it.
Hi, this is Bob Hallberg. So one other possible advantage of going from Leapfrog to a Runge-Kutta scheme is that you have a well-defined conservation property. You have a well-defined state, you move to a well-defined state. Whereas a Leapfrog, exactly what your starting state was is always a little bit ambiguous because of the computational mode. Are you diagnosing the conservation of any conserved properties? And could you use that to demonstrate that you've gone from, say, oh, I don't know, I'm guessing 10 orders of magnitude of conservation to 16 or 20?
Yeah, okay, we didn't try, but.
It's worth trying. Yeah. You probably will see you are doing a whole lot better with conservation.
Okay. Maybe a last question in this case.
Thank you. Keith Lindsay from NCAR. On your tricks slides, you had one for active tracers. Do you have tricks for passive tracers also?
Well, they are the same. Well, but
So,
actually for the passive tracers, it's different because we use a muscle advection scheme. And so in the end, we only have one time step. We don't have this sub time step. We use a muscle time step at the
last step.
At
so
the last
the
step.
same advection scheme and same time scheme for.
so the time stepping for passive tracers is
different.
Is very different.
Yes, because it's a separate.
Yeah. Well, the tests have been performed with this kind of time step, but others are implemented into Nemo, and it was, yeah, and the others are except, sorry, if you don't look at the muscle time step, which is majorly used by Nemo Pisces users. Yes, for the other time step advection schemes, we use this framework. Am I clear or not at all?
But at least for passive tracers, it's an Euler step. I think this is for passive tracers, this is an Euler step, and it's not. No.
Well, but
okay.
No. Only for muscle.
Okay. But this is what is used in practice.
Yes, but there are other possibilities.
Okay. So we should move to the next. Thank you. To the next talk.
Again.
So the next talk, no, not yet. It will be given by Adrien Garinet. So working in Toulouse, and about some insight on spurious numerical mixing and how it is associated to time stepping.
Yep, thank you for the introduction. So yeah, I'm Adrien, and I'm working with my my collaborator on this work are my two supervisors, so Patrick Marsalet and Marina Mann, since I'm still a PhD student at Toulouse. So in this presentation, I'm going to talk about the things I've been interested the most in the past 2 years, at least work-wide, which are, yep, should I wait? There, like, well, I can also.
There it goes. There it goes. So now it's.
Yep. Okay. Yeah. So those are the two things I've been interested the most in the past 2 years. So spurious numerical mixing and advection schemes. And so the outline of this presentation is going to be first, I'm going to say to the people who might not know what spurious numerical mixing is about. And then we're going to move to advection schemes, first starting with the semi-discrete framework, and then what's the actual point of this presentation, the space-time framework. And yeah, So you all know that mixing plays a major role in the ocean and also in numerical models. And so in numerical models, when you solve equations using numerical methods, you can generate errors, some of which looks like numerical mixing. And when you have too much numerical mixing, you have spurious numerical mixing that can occur. And basically, it can burst the vision of the ocean that you have. So if you're interested in actually studying the mixing in the ocean, that's an issue. And if you're running long-term simulations, the mixing is going to add up, especially if you don't have any forcing at the boundaries, or so if you're using climate models. And well, that's pretty much problematic, I think. So it's a well-known problem. I mean, it's been a well-known problem, at least in fixed coordinate models for now over more than 2 decades. And yeah, so it's been since then it's been quantified in academic simulations, in global models, and well, there's a whole bunch of literature on the topic. But for me, the main conclusions are that numerical mixing is at least as high as, so it depends on how you measure it, but as physical mixing in model and all scales, and it increases as horizontal resolution increases. So basically, if you increase the horizontal resolution, you're going to get more. You're going to resolve more phenomenon that impact on the vertical, and since the usual suspect for a vertical for spurious numerical mixing, so you have many suspects, but depending the usual suspects is the vertical advection of tracer, and you can show. I mean, it's not so this is not proportional; it's more like scales, but the numerical diffusion scales with the vertical speed. So when you resolve more phenomena, you're going to have higher vertical speeds. For example, when you start resolving eternal tides, you're going to have super high vertical speeds, and so it increases the numerical diffusion. So a lot of work has been carried out to improve the vertical coordinates, and the questions I've been wondering is, can we also work on the advection scheme, which have not, I believe, really moved since the first those papers. So yeah, I've been wondering if we can actually do something with the advection schemes. We start first with the semi-discrete framework. So basically, when you have the advection formulated in finite volume formulations, which is what I've been dealing with, you can show that for when you have a linear scheme, you can split the advection into transportive parts and let's say diffusive damping parts. The damping part, we keep it because usually we want it to control dispersion errors. So yeah, I say for linear schemes, this talk is going to be only about linear schemes because you have a lot more issues occurring when you have non-linear schemes. So here I'm going to focus on this. We can talk about it later if you want. And yeah, so you want this damping to control the dispersion error. And for example, there is the well-known third of the upwind by a scheme, UP3. And this can be split into the sum of what I call the C4, so a fourth order centered scheme, discretization of the transport, and an additional, so bi-Laplacian, let's say, operator. The problem with this UP3 is that the D4 is not scale selective enough, meaning that, okay, sure, it can control, so in some way, the dispersion error at the grid scale, but it also have quite high spurious dissipation of the largest scales, which are actually physical, and that's going to be an issue. I'm going to see it after. So in a paper that is going to be published soon, you just need to send the last proofread, maybe this week. And we have shown that if we change the scheme, actually, if we move on to a UP5, so it's not a UP5 that we use, but basically, if you change the diffusion and move it to a D6 order diffusion operator, we achieved good results in a model, and a realistic model with a 5-kilometer resolution of the Southeast Asian seas. Why is this region interesting? Because that's the region I was supposed to study at the beginning before moving on, getting lost in these kinds of things. But also, it's an interesting region to play with vertical advection schemes because you have very strong internal tides happening there. Some would say the most powerful in the world. And also the fact that you have semi-enclosed basins means that when you're going to have too much mixing, you're going to see it, and if you have too low mixing, you're going to see it basically in this region. So it's not all, even if your model defaults at the boundaries and stuff. So yeah, it's pretty interesting. If you have one more information on this, so this is going to be the paper that should be published pretty soon. And in the rest of my talk, I'm going to refer to the modified scheme, so the one using the D6 at the UP3F, and I'm going to compare it to UP3 after. And it's been implemented in the Symphony Ocean model, which is a model developed at the Lagos lab in Toulouse. It's quite a small model, but yeah, that's the model I've been using for this work. So my question was, could we actually, so we have quite nice results using this 6-order diffusion, and it's not 6-order, it's like trilapelation. Maybe I'm going to make the mistake again. And could we further reduce diffusion? And actually, to answer this question, we're going to have to look at time stepping. So formally, in a time stepping framework, quickly, the value of the tracer field at time step n+1 is a function of the value of the tracer field in the previous time step and advection function. And so there are many ways to actually analyze schemes, especially advection schemes, but also time stepping schemes. When everything is linear, a quite nice one is the spectral one. And so we're going to look at solution. We're going to look at the behavior of the scheme when we put in the solution as a Fourier mode. So written like this. So you have rho, which is going to be the amplification factor, which is the thing we're going to be interested in. And yeah, you also theta, the angular wave number, which is 2 pi over the wavelengths expressed in number of grid points. So this amplification factor, if everything was perfect, it should be equal to 1 because the advection is not modifying the amplitude of the field. So actually what we're going to be interested in is the delta rho, so the error that we made, so the difference of this rho to 1. Ideally, we would have to have this delta rho close to 0 for the largest wavelengths, because we don't have spurious diffusion to happen at those wavelengths. While we should have, if we want to damp the spurious grid point noise happening at the grid scale, at grid scale, well, delta rho should be large enough. So we're going to say that delta rho smaller than 10 to the -4 is okay. So with something we want to achieve, you can say that the schemes that we analyze is good. We also introduce notation that has been used in previous talks. So we're going to call mu the complex number is equal to delta t times the spectral representation of the advection term. And basically we can solve, so if we analyze the scheme, we can solve 2 equations, and we can either have this, we have 2 frameworks and we're going to use both. I'm going to go quickly on this. Also a new, the current number, so the speed times the delta t divided by delta z is going to be equal to NC. We're going to see it often after. So the time stepping scheme that is used in Symfony is the good old leapfrog with robust at-link filtering. So it was used also in EMO before. So this is the equation for the tracer, and I'm going to pass rapidly on this. And basically we can, so if we use in this framework, we can derive this kind of scheme. So this kind of figure. And basically on this figure, we represent the error, so the delta rho that I've mentioned just before, as a function of the wavelengths and the current number. So by itself, it doesn't provide a lot of information. I think it's more interesting if we had the modified scheme that I've mentioned previously, and we can see that, so actually, yeah, I'm gonna see if I manage to do something with this. Whoop, yep. What we change here, it's like we reduce the error, basically in this part of the, so here we didn't modify anything, here we didn't modify anything by using the true Laplacian operator instead of the B-Laplacian. But yeah, here we achieved actually better results. So we made the diffusion more selective in the sense that we reduced the error on the largest wavelength. So here, it's not super, if you do the math, like 0.2 theta over pi equal 0.2 is correspond to 10 grid points. And we're going to consider that physical wavelengths are the wavelengths that are larger than 10 grid points in the rest of the presentation. So we see that there's also a depend. It's not only about when you add this, when you look at the schemes, also adding the time stepping component, you have a dependency of the error on the current number. And so we're going to look at the current numbers that we have in the model. So here is a snapshot of the vertical field, vertical speed field in, after 2 years of simulation. So just to get a sense of the vertical speed that we are encountering in the model. So you can see there are a lot of internal tides everywhere. And so basically we're going to say that the maximal speed reached in the model is 3 to the 10 minus 3 times 10 to the minus 3 meter per second, which corresponds to a few hundreds of meter, above 100 meter per day. So which we doing tests, we realized that the maximal time step that we could use was 600 seconds. Actually, in the simulations we used, it was much smaller, but we can go as far as using a time step that is that big. And in the ocean interior, we can assume that the virtual spacing is 10 meters. Actually, it's probably going to be a bit bigger, but yeah. And so this gives us a maximal current number of 0.2. And if we go back to the visualization that I just showed you, we can see that if we at the limit of this regime, in the highest regime, we're going to have an issue for the wavelengths equal to at least 10. The 10 grid pulse wavelengths is going to be, so the error is going to be larger than 10 to the minus 4, and I've said before that 10 to the minus 4 is kind of the limit that we want to achieve. So the combination of the time stepping is not, the combination of both schemes is not still perfect. We'll have to do, there's probably a way to do something better. So we have reduced the diffusion by moving on from a D4 to a D6. Now we can say, okay, maybe we can just remove the D6 operator and we're going to get something even nicer, because maybe we can just remove the diffusion at all, and if we use a purely centered scheme, it's going to be even better. But that's actually not true, because if we run simulation with only a C4 scheme, so that is an advection scheme that has no diffusion at all, what we see is that by just multiplying the current number by 2, so this is what we have here, we actually, so even without diffusion in the advection, we have diffusion from the time stepping. So this is something that is not new, but we can see it on a simulation here. So we just move back and forth these 20 grid points. It's 20 grid points, actually the wavelength of these features. So it's quite big, 20 grid points for a vertical, I mean. And yeah, we can see that there's an issue. So even removing completely the diffusion from the advection operator is not going to solve the issue. I'm not sure I have that much time anymore, so I'm gonna move quickly. So actually, so a way to find a solution is to look at the scheme in the stability domain. So we look at rho this time not as a function of the current number and theta, but as a function of mu. So this is before. So in this representation, we can also, so this is the stability domain of the time stepping scheme. We can also add information about the advection scheme in form of what I call spectral curves. So the points correspond to the wavelengths expressed in number of grid points. So here we have the representation of the UP3 spectral scheme with a current number of 0.5. So the scheme runs unstable because the spectral curve is going out of the stability domain. We can add information about, so we can represent the same curve for a lower current number, and then we can see it's stable. What we're interested in, since we are interested in largest wavelengths, we're going to zoom on this part because they are morphed in this part of the, yeah. There's also another information that can be represented on the stability diagram is the same delta rho as before. So what we can see is that as we move away from the boundary, roughly, the error is going to increase. So yeah, basically what we want is to get the advection scheme curve as close as possible to the domain's boundary. So here we look at the UP3, we are here. If we look at the UP3F, since we diminished the, we decreased the diffusion, we are a bit closer to the boundary. And now if we look at C4, we're actually stuck, like, we're, since we don't have any diffusion, the mu r is equal to 0, and we're actually stuck on this line. So, and we can see that the boundary of the stability domain is actually moving away. So even if we don't have, we're going to have error actually. This part is going to be, yeah, it's always going to lead to error. So the idea is to use a scheme which introduce like a real part of this mu that is actually positive in order to be able to reach the scheme and get closer to the boundary. So in order to do this, we use a scheme that is formulated like this. So we have the D4, and then we add a filtering that is used at the most simple part. It's a low-pass filter. So actually, we basically, if we consider alpha equal 1, it's going to remove the effect. It's going to roughly, assuming the filter is perfect, it's going to remove the effect of the D4 on the largest wavelength. And if we take now alpha strictly larger than 1, it's going to reinforce the larger scales. We can show that the scheme becomes stable if alpha equal to strictly larger than 1 is kept constant with respect to NC. So in the end, we choose, let's say, it's quite empirical, that a formulation with this kind, so using alpha as a function of NC in this form, leads to quite, I mean, good results. I mean, if we, yeah, it's yeah, with two constants to be determined, it actually depends on the time stepping. So more specifically, it depends on the filtering coefficient that you use on the leapfrog. So here is an example. So we actually designed a scheme that is able to get closer to the model, so actually reduce the error. And so this is the same representation I've showed before in the current number and theta space. And we have indeed reduced the error for the scales of interest, so the 10 grid points. We can see that when the gradient of the delta rho as a function of density is quite high here, so meaning that it's the diffusion is actually quite sensitive to the current number. But if we consider that the regimes of interest are here, we have basically reduced the error lower than 10 to the minus 4, and so we are happy, I believe. So this is the same comparison, and we show that with the modified version of the scheme, we actually get better results than using a C4. And yeah, so some conclusions. So we can add some anti-diffusions to counteract the diffusion of the time-specific scheme. And also this thing that doesn't have to depend linearly on the speed. These results can be applied also to other time steppings because, as you can see, the leapfrog filter is not the only one with which has this property of being stable for values of nu-r that are positive. So we can probably design the same scheme for, let's say Acre 3, because we've been talking a lot about this time stepping scheme this afternoon. And yeah, just some more thoughts on something I will add, because that's things, it's not related to advection scheme anymore, or only partly. Things I've been interested to and interested to discuss with interested people. So we actually want to reduce the numerical mixing, but the question is, to what extent do we actually want to reduce numerical mixing? Because as we have seen, we want it to control errors. But yeah, so how do we define what is good numerical mixing, what is bad numerical mixing? And most importantly, what is the role of numerical mixing in the good performances of numerical models? And actually, something I've been wondering if it's, especially in my region, so in Southeast Asia, can numerical mixing actually make up for a lack of physical mixing? For example, when you have tides, you use you resolve tides, we're using a hydrostatic model that is super large resolution. Do we actually resolve all the physical mixing, or is the numerical mixing that is in the model also kind of playing the role of physical mixing and leading to the good results we compared to observations that, yeah, so that's pretty much it.
Thank you. So let's keep two questions on this.
Thank you for the presentation. In our model, we actually find out that horizontal advection is what dominates the epic mixing. So I was wondering if you guys checked up, like changed the horizontal advection, or what are the results?
Yeah, so in our region, including tides, we actually, so we are in the paper, so it's we don't mention it in the paper, but actually we changed the scheme on the horizontal also, and we've seen that changing the scheme on the horizontal didn't lead to, at least on the results, at least on the diagnostic that we're running, which may be not super precise, but it doesn't lead to huge differences. It's really the vertical advection that was driving the, but as I said, if you look at the maps that they showed, we have super high vertical speed, so the vertical advection is put under a lot of pressure.
Thanks for the talk. I would say that when you ask the question, how much should we bother reducing the mixing? It's really the dipychno mixing that we need to focus on.
Yeah, exactly. Yeah.
And so
it was implicit.
I'm wondering, you are using the word diffusion, but you've never shown me a diffusivity, and I know that it's difficult to diagnose. I mean, there's 25 years of history of people trying to do that, but you are putting some numerical statement about diffusion, and I'm wondering, can you roughly translate into a diffusivity, or is it even worth doing?
No, actually, that's yeah, I don't really know. I think if you when we talk about only Fourier modes, I think the word dissipation would be better. Dissipation or like loss in amplitude. Actually, I would have should have said loss in amplitude every time, because I'm actually considering only Fourier modes. It's true, I've used the word diffusion, but it's probably not the best word, because when you look at the scheme in coupled space-time framework, I don't know. I mean, actually, when you use, so I don't know if it's doable with the leapfrog with Roberts-Asklin filtering, because the scheme is quite tricky, and so if you want to disentangle everything, you're going to have a super long equation. So like looking at the Tyler expansion is not super practical. But if you look, for example, at a simpler version of the scheme, if you look at the Lagrangian filter, so leapfrog with Lagrangian filter, you can actually derive quite easily a diffusion term, and then you can turn it into a spatial. So yeah, that's another way to see the scheme and maybe to design a solution to this, but yeah, it should be more loss in amplitude of ways, let's say.
Hi, this is Bob Hallberg. So one of the challenges is if you tune your parameterized mixing to compensate for numerical mixing, and then you use the model to run into some part of parameter space that you haven't studied and tuned it for, you have absolutely no guarantee that the numerical mixing will be changing the same way the physical mixing should. So in
referring to
the comment at the last.
Here? Yeah, maybe this.
Well, no, I was really the broader comment on your last point, saying, is there good numerical mixing?
Actually, I don't think there is. I mean, there should be some to control the grid point error.
And this is one area where we as an oceanographic community and ocean climate community have really fallen down because we have had so much numerical mixing that we really haven't done a good job of exploring the extent to which physical mixing will be changing as a result of evolving stratification, the energy of the tides, and various other physical processes, which might actually be a very substantial part of the climate change signal in the ocean.
Yeah, that's the kind of question I'm also wondering. Like, if there's been I think there's been a lot of mixing happening in the models. And if you look at the quantification of mixing in the studies I mentioned before, basically it's always like, oh, there's at least as much numerical mixing as physical mixing. So the question is, well, how much is this numerical mixing playing a role in the good results? Yeah.
So we should thank all the speakers. So now we move to a discussion session about this session 3 that happened this afternoon. If I remember well, the note taker will be, okay, Theresa, thank you. Theresa, just right here. So we will see the few questions we prepared. And probably we could include in this discussion also maybe told by Peter Korn yesterday also. Okay. So I think, yes, there are those, let's say, 4 questions more or less. So about the main challenges for numerical method, I think we saw one example with the last talk. And also how to more or less evaluate the quality of a model by combining maybe effective resolution and the computational cost or the, I don't know, energy to solution, time to solution, whatever the measure, but it has to be related to some form of effective resolution. So in this case, and what is the role of numerical method also in the performance versus software environment? Do we expect in the near future a change of direction with new method for a new generation of ocean models? And a very more specific question about the challenges for increasing the resolution of sea ice models. So it's a large overview of things. I don't know if some people want to start discussion, Alistair.
Just to get us started. So we saw a comparison of resolution, a little bit of a comparison between resolution versus order of accuracy. And in the past, when we've been talking about CPU machines, it's like kind of exchanging. There was a balance between time to solution because you're doing more work. But with the advent of GPUs, those more intensive computations are actually a lot cheaper. In fact, there's no point doing a sparse operation. So it could be that going to extremely high order and just doing much more intensive computation is the only way to, it will be very much more beneficial to us because it will cost us nothing on the GPUs. That will be new for us from a numerical formulation point. I mean, it just, it offers the opportunity to just do something completely new.
And I should add a comment also, the fact that, for example, RK3 time stepping, it's something very robust to an increase of resolution also. So you don't have to decrease your time step, even if you increase the resolution, the order of accuracy in space, actually. And this is not the case. There are a lot of schemes, maybe Advanced Bash Force is one of the example, where when you increase the order of accuracy, you need to decrease the time step. So you have a double costs, additional costs. So I think the evolution also of the time stepping is important on this, in this respect. But it's true, moving to GPU, we probably change a lot of things.
So we looked at one metric of the impacts of increasing resolution, namely the energy of the moderately resolved scales. When we increase the resolution of ocean models, one of the biggest things is just we do a better job of representing the geometry of the basins, the topography. And so I think as we're evaluating newer techniques, paying attention to that, and in particular, there are small scale structures in the ocean that have global scale impact, and making sure that we're doing a good job of capturing the geometric constraints, the dynamic constraints of the geometry of the ocean as part of the trade-off between explicitly resolving it perhaps with lower resolution techniques, or using higher resolution, higher orders techniques that are able to capture the effects of the dynamics I think is going to be an inevitable part of the considerations in realistic ocean modeling.
Yeah, maybe a point to add on is if we can explore machine learning to actually save numerical costs. Like, I think this hasn't been raised in any talk yet. Maybe I missed it. But I think this is a way to save a lot of costs, because you don't have to store stuff. And let's say for prediction correction schemes, maybe you can make predictions just with something coming out from machine learning. You don't need to calculate the stuff.
Okay, yeah, true. And I think, yes, this is a good remark, actually, what you said, and it's also valid. So I mentioned this probably the first day. Now for internal waves, for example, we are able, so before in global models, we wanted to get rid of it just for stability reasons. Now probably at some point we'll be able to have, to resolve them actually. And the numerics, for example, for the moment is second order accurate for internal gravity waves. So maybe we could explore also an increase of accuracy for that. It could be interesting. And I don't know if there are other comments.
Just one curiosity regarding the force, about the challenges involved in increasing the resolution. So if we increase it, if we already now we have a problem about numerical mixing, should that problem be bigger? It's more difficult to control the model if we have a higher resolution.
Actually, I'd like to just, I think I heard a comment and well, just now in the talk, and you just emphasized it, that the numerical mixing gets worse, it gets bigger with resolution. It does only to a degree, and then at some point we start to converge. It's a function of not resolving the mesoscale properly. So that was a result. It was actually explained very well in Griffey's, 2 decades ago, I think, that there was a kind of peak resolution where things just were. The quarter degree model at GFDL was just built as the worst resolution you could choose for that problem. So it does get better. At some point, you start to resolve that thing, and everything does get better. So just to clarify that point.
You heard it. No quarter degree resolution.
I have a comment maybe on the challenges on increasing the resolution. So that's where effective resolution is way more appealing, probably, because when you increase the resolution, then your storage space just blows up incredibly. So if you can get there with numerical schemes, that probably saves a lot of hassle and having to occupy a lot of memory.
So on this specific point of the cost of storage and the imposition that it imposes on all the graduate students and everybody who's making use of it as we go to higher resolution, I think one of the things that we should recognize is that the grid scale doesn't really have a lot of useful information. We have to have it, but it's there to make errors. One of the things that we probably should do is think carefully about not just the resolution at which we are running the models, but also the resolution that we're saving the output for analysis and which terms we're saving for analysis. So integrated terms are something you can easily decimate by a factor of 2 or 3 or 4 or 5 without losing any information content whatsoever for things like AMOC. And if you do that, factor of 5, 2 dimensions, factor of 25, you rapidly make things both easier to analyze, more accessible to students, and a whole lot cheaper to store, because these days, storage on tape costs a lot.
Thank you. So we will take the remark online. Actually, Michal, what you wanted to say?
So since you guys, yeah, thank you. Since you brought up the storage, that's kind of also my point on my presentation, that per degree of freedom, the high order models carry more information, right? Because they carry information about not just a single point in space, but it's an amplitude of a basis function. So that's kind of what I was trying to show, that you get the same, in this case, resolve energy with way fewer degrees of freedom, even though I didn't show you how many degrees of freedom we have. But the storage required for, for the 6th order HNUMO at 25 kilometer will be much lower than HiCom at 4 kilometer, even though the resolve energy is the same, right? So we hypothesize that the result is the same or similar. Thank you.
Okay. And maybe for point 4 also, I don't know, maybe there is a question about the rheology also. When we increase the resolution, I have the feeling that we should change the rheology because the viscous plastic or whatever is no longer valid, or if I remember well, but no. Yeah.
I can give a brief summary on this topic. Yeah, so there's, I think, 2 points. When just have to, sorry, I'm getting tired because of this chat lag, and then I'm losing the words. So there's the continuums hypothesis, yeah? And so this is a theoretical problem CI's modeler have, that if the resolution is too high, the continuums hypothesis is breaking down, and then there's some discussion if we should still apply continuum CI's models, because if the resolution is too high, you probably do not have enough CI's flows in a certain cell, and then the model is not appropriate anymore. So this is a theoretical problem. Then the challenge of the viscous plastic model is that solving it at high resolution is incredibly difficult. This is a numerical problem. And then I think it's also a gift, high resolution, because they can compare to satellite data. So it's actually good to do high resolution, because then, I think it's actually better to run CI's models at high resolution than at coarse resolution, because there has been a lot of studies showing that they're getting more realistic.
Thank you. They are tired about this session. Okay, sorry.
Since we were on the topic of storage and what you can save for high resolution, I had a couple of thoughts. I think you absolutely should try and decrease, this is Marin from Wisconsin, decrease the amount of things that you're storing, because it's really difficult. But at the same time, you don't want to not store things that are going to make it difficult to do any kind of cross-model comparisons. So the most fundamental fields, U, V, T, S, because if you don't have those, then you're kind of trusting that all of the modeling centers did their integrated diagnostics the same. And I hope everyone does, but things happen. And then I'd also say, saving those kind of metrics does help, introductory graduate students initially, but my whole group is on DASC and on the supercomputer using parallel computing to do analysis. And they've all been there doing that since their first year of grad school. These tools actually make it very accessible to do analysis on very high resolution climate model output without too much pain, even initially. So I don't think, I think you consider the tools that are out there and how it's really advancing students' ability to work on stuff.
So on this point of data storage, the budgets are very real. I don't know about other places, but at GFDL, we make a trade-off between tapes and postdocs. And I know which I prefer.
This is Andrew again. So the question also, I think, was originally raised by Dan Armourine about like, are there clever ways that we could store the data and compress the data? And like, very much the same way that there's not necessarily a whole lot of information at every spatial grid cell. I think the question also is like, is there a lot of information at the frequency at which we're saving the models, right? If we could afford to just do a PCA analysis and store a subset of the basis functions, how many eigenvectors do you actually have to store to do 90% of the climate science? And we know how there are algorithms out there to do distributed PCA to be able to do it in a streaming way. And is that dangerous? We are throwing away a lot of information, but is that more or less dangerous than throwing away like doing the regridding? So I'll just throw that out there. I don't have an answer for that, and I'm not advocating for it.
I was just going to say that, I mean, Keith is in the room. We are talking about most of the physical fields here. If you add ocean biogeochemistry, that's going to add a lot more storage.
There is also probably not much information in the last bits of the numbers. So there is scope also to reduce that to compress the data. There are some new advanced compression techniques that could save a factor of 60 on data storage, but then you have to see how they do in the bottom of the ocean where the last significant digit actually probably matters. So.
Yeah, kind of continuing on about those bits, but not just in the output, but also in running the model. There's this one very cool idea that I came across. I think it's from ECNWF, that if you turn down the voltage on the supercomputer, you can both save energy, so point number 2, and introduce a little bit of stochastic forcing into the model, which may be a good thing.
Okay, so Alistair.
Okay, so the bits is a good segue back to GPUs. So one of the pressures we face as numerical modelers right now is that the chipsets on the GPUs are actually very efficient with less bits in the numbers. And the machine learning people want us to get under 4 bits per floating point, which is not even a decimal point, and so it's pretty scary. We at GFGL, we're facing a real problem because our model really depends on the real star rate precision to do the calculation of the sea surface height, and we just don't know how to possibly use a low representation. So it's a challenge for us. But I mean, that's an issue that's being forced on us by the hardware. So it will be free. That our data will actually be smaller if we're being forced to actually use lower precision. But from a numerical point of view, then it asks the question: is it worth going to higher order methods if you've right?
So maybe maybe a comment, maybe to be back to those notion of effective resolution and spurious diapigment mixing. There was this paper by Mehmet İlikaç showing that, okay, the regularity of the velocity field is very important. So maybe it means that, for example, if you keep the vector invariant form versus flux form, so flux form, you have a lot of schemes that allows you to have to impose regularity constraints. And vector invariant form, it's more like global conservation, but you don't really have it built-in, except maybe in the recent work, but you don't have any built-in regularity constraint. And it is second order accurate most of the time. So I don't know what would be the rationality to keep, for example, the vector invariant form, the motivation actually, for example. I know that Peter had arguments for PV dynamics, I think. And this is the same, for example, in MUM6 to stay with this kind of form of, I don't know, Nusara.
So one completely different thing, there is a big change in the range of physical processes we are trying to address. Tides, we saw some of that yesterday. We are trying to look at interactions between oceans and ice shelf cavities. We saw some examples of icebergs that are displacing water. We have a whole range of physical processes. The diurnal cycle is something that once upon a time you just kind of got the right mean. Now we maybe start to care about the diurnal cycle because it leads to affects the convection as seen in the atmosphere. we made a whole bunch of assumptions 20 or 30 years ago about what physical processes in the ocean were and were not important to capture in the ocean models. And a lot of those assumptions don't hold anymore. And some of them are going to present very real challenges. We're looking at the prospect of running with explicit tides in a climate model. We don't know how to analyze that because you get aliasing of the tides, which are a pretty big signal if you're not careful. We are looking at explicitly propagating internal waves across the ocean basin. And when they break, if they're contributing, for instance, to shear mixing schemes, they will drive mixing in a very physical way. So I think we are seeing something of a regime change in the degree of complexity of what we are trying to numerically simulate for many of the applications that we're applying. And that's going to be mapping into new requirements for some of the numerical techniques. Lower order time stepping schemes may not have been a problem when you were filtering out everything with a high frequency anyway. But now if you actually care about it, you might want that temporal truncation error to no longer be something that you just kind of ignore in favor of stability.
Very good remark, yes. We still have 5 minutes. I don't know if there are other comments. So, yeah.
Just two comments. One is related to the coupling, because another issue important when you run coupled models is the frequency of coupling between the different components of the model within the modeling system. For example, if you want to analyze, I don't know, the Earth's interaction in the deepening of a cyclone, what is the right frequency of coupling? 3 hours, 1 hour, half an hour? Probably you get different results, and you also affect the performance of your computing system. And more or less the same thought is about the storage. For example, I'm running my coupled models, is a regional system model. We have been asked also to produce high frequency data related to the extreme precipitation, because they want to know something about that, okay? And more or less for 10 years of run, the storage now is, the data occupy more or less 15 terabytes of the storage, just for 10 years. So some people are waiting for me in Italy to kill me probably because of that. So probably the importance of the storage and the frequency of coupling is strictly related also with what you want to analyze to address, let's say.
Okay.
Yeah, I think your point about the fact that these models are sensitive to coupling frequency is something that is really problematic in terms of thinking about how we use them for long-term projections and for sort of case studies, like you said. So trying to get those physics better, more representative, hopefully means that we will be reducing that sensitivity going forward and thinking about that broadly, not just sea ice in the ocean, but the ocean, the atmosphere, sea ice, all the different components and how they interact together.
Actually, also another point for this coupling aspect, actually, I think Gökhan mentioned it yesterday about we all use a bug formulation, for example, to compute the RC fluxes. It comes with a lot of assumptions, and which makes them, in principle, not usable for super high frequency coupling, for example. And you need to add processes like maybe C-spray or whatever on top of the usual bug formulation. But and swell, yes. True.
I was going to ask a question. Has there been any systematic study of, with a single maybe modeling framework, changing the coupling frequency and how it impacts the results in what way in different time scales? Besides the one that sort of you showed, but I'm talking about like more comprehensive sort of.
Go ahead.
Yeah, obviously I showed some really idealized simulations, but we've been testing it in our quarter degree model as well. Honestly, the results are still kind of mysterious in terms of being able to predict what sort of CI state you might get based on what sort of coupling time step you use in a way that I think shows we really don't understand how that coupling time step is impacting the dynamics. And then obviously like Bob's clever 2014 paper showed really clearly how being unstable in your coupling time step can lead to a drastically bad CI state.
So I was going to answer your question thinking about time steps in general, but coupling in particular. I mean, the cloud people in the atmosphere, time steps really matter. And when we used to do convective adjustment in the ocean, traditional convective, you could get a big difference with the ocean time step. I still think you might get a difference even with large vertical diffusivities today with different time steps. But I don't know of any paper that's really done it systematically. I might be missing.
I guess I have a related question, like what kind of performance, because I see this coupling thing as a performance optimization. So I'm wondering how much gains are we getting from these schemes? Because that kind of also guides it whether it's worth it or not. I mean, there's a general assumption that coupling less frequently is more performant, but is it like way more performant or just, is it 10%, you know?
To the extent that your coupling frequency sets the timescales associated with your biogeochemical model, and that your biogeochemical model these days has many more degrees of freedom than your physical model, this is a game changer. If you can keep the biogeochemical model running with a time step of order an hour or two or something like that, which is more than enough to resolve the diurnal cycle and the growth timescales of biology and stuff like that, we can run at much higher resolution, and the biogeochemical part of the model is relatively cheap. If you have to shorten up that coupling time step for the biogeochemistry, it just limits what you can do scientifically.
Okay, thank you. I accept one last question from, let's say, already career scientists, which is maybe the case or not.
Right there, right?
So just one comment on the coupling. I can't remember if there have been a published paper on it, but I know that there is a team, at least in the Met Office, who has looked at this for the regional coupling. And I believe they are using hourly frequency, and it was basically a compromise between how much can you afford to couple it and exactly what's the benefit you get from it. And the other thing that not sure it kind of fits in here, and going back to the comment on the biogeochemistry, is ocean spin up. We are trying to get something implemented, but when I say we are trying, I mean we are just now thinking about it and trying to implement a new method. But yeah, just perhaps that's missing from the points made until now.
Okay, last comment in this case. Yeah, no,
How many last comments?
We have 2 minutes if we need to.
It's a lot.
Yeah.
Usually for the biochemistry, there are some strategies that say, let's try to do the spin up for the biochemistry using a coarser resolution. They move to the higher resolution just by interpolating. But probably in this, I never tried these strategies, but I'm not very confident in this kind of strategy, because when you move to an higher resolution, maybe you can have some problem of stability, or you increase the gradient of some biochemical properties. Usually, one of the things that we do when we do ocean biochemical coupling is to use effectively a different time step in the biochemistry. For example, in MIT GCM, we use the long step, I think, package. Using an higher, so in this way, we can use an higher time step for the biochemistry.
Okay, now it's done. We are done. So thanks a lot for this discussion session.